Hello. Good morning, everyone. Hello. Good morning, everyone. Welcome to the day two of FMFP 2020. This session will be chaired by Professor Bani Ray from IT Delhi. We request ma'am to start the session. Thank you. Hello, ma'am. Hello. Hello. Hello, ma'am. Hello, ma'am. Ma'am, can you hear my voice? Hello, ma'am. Bani, ma'am. Hello, ma'am. Can you hear me? Ma'am, please unmute yourself. Hello. Yeah, she's me. Hello, ma'am. Hello. Hello, ma'am. सुनाई दे रहा है? सुनाई दे रहा है? सुनाई दे रहा है?
You please check your setting.
Okay, okay.
If go-
I can hear now.
Yes.
Yeah.
Yeah, yeah, yes, ma'am. Yes, ma'am. You can hear now. Yeah. Thank you, ma'am. Uh, Good morning, everyone. Welcome to the day 2 of FMFP 2020. This session will be chaired by Professor Bani Ray from IT Delhi. Thank you.
Yeah. Good morning, everyone. I think I'm audible. Am I audible?
Yes, ma'am.
Yes, ma'am, audible.
Okay,
Good morning,
fine.
ma'am.
Yeah. Good morning. Yes. So, can you just check that all the speakers are present?
Yes, ma'am, I am present. It's my first presentation.
Yeah. No, we have to just be sure that all are present. So,
Yes.
paper number 170, 171,
Yes, ma'am.
191,
Yes, ma'am. Present 191.
207, paper 207. Okay. Paper 227.
Paper 207 present, madam. I guess I am audible.
Yes, yes. Now you're audible. Yeah.
Yeah, thank you, madam.
Paper 227. Paper 246. Paper 264.
And
Paper
actually,
260. Paper 265. Okay, maybe they're muted or something. So the rule is that if the presenter is not present, then we may not show the presentation. So let's start. Okay, so good morning. And today is the second day. And as you see in this session, we have a range of work from droplets to microchannels, as I could see. And there are experimental, numerical, and analytical works. So it will be interesting. So let's start with the first talk. Yeah, you could start.
Good morning, ma'am, my fellow researchers and the respected dignitaries. Droplet impact near millimeter-sized channel. Understanding droplet impact is relevant for several applications like inkjet printing, spray coating, pesticide deposition, spray combustion, and so on. Research has identified the following outcomes for a droplet impinging on a dry solid substrate. First one is spread, observed when a low energy droplet impacts or hits a solid substrate. Here, a thin fluid film, also called lamella, is ejected from the base of the droplet post-impact, which spreads till it attains maximum spread. Second one is a splash. A splash is observed when a high energy droplet hits a solid substrate and disintegrates into tiny secondary droplets. Again, splash is categorized into two types. First one is corona splash. In this case, the lamella ejected from the droplet base lifts in air, forming a cone shape before disintegrating into tiny secondary droplets. Second one is prompt splash. Here, the lamella does not lift in air, instead develops undulations or perturbations along its boundary, which again disintegrates into tiny secondary droplets. Fourth one is rebound, observed commonly when a droplet hits a superhydrophobic surface. Research has also shown that surface roughness elements and texture influence the perturbations which appear on the rim of the expanding droplet lamella and also affects the lamellar flow behavior post-impact. Understanding how surface roughness elements affect fluid flow behavior is quite a challenging task. Instead, researchers started investigating droplet impact on solid substrates containing a single obstacle. Jocelyn in 2005 introduced the obstacle as a single step change in surface elevation. He impacted water droplets on inox coated with Teflon. The impact velocity was fixed as 3.3 meter per second and the step thickness taken was this. From his experiments, he found that the angle, width and velocity of the liquid that shoots up post-collision with obstacle varies based on the distance between the droplet impact point and the obstacle and also the obstacle's height. Reisman in 2010 conducted experiments on substrates containing open pores. He impacted water droplets on surfaces which had varied surface wettability. The impact velocity was also varied here and the pore diameter was fixed as 1 mm. From his experiments, Reisman found that the surface wettability affects the fluid lamellar deviation as it passes over the hole or the pore. Zhong in 2014 conducted experiments on surface containing closed pits. He also used water droplets which were impacted on perspex plate. The impact velocity was fixed as 3.0 meter per second and the pit diameter and depth were varied. Zhong found that by varying the distance between the pit and the droplet impact point, the impact outcomes can be varied, like a splash can be obtained or a combination of splash and jet can be obtained or a splash accompanied by a air bubble formation can be observed. The present work is an extension of research work carried out by Zhong. In our case, we introduce millimeter-sized channel as the obstacle, which is placed in the path of droplet fluid post-impact on the solid substrate. This is the schematic of the setup that was used in our experiments. The droplet impact was captured through high-speed camera at 10,000 fps and this was the resolution. Water droplets were dispensed through auto-dispensing module with a diameter of 2.8 mm. The droplet impact velocity was fixed in our experiments as 2 meter per second and PMMA was used as the test substrate, having a static contact angle value of 67 degrees. Two channels having a length of 0.5 mm and 3 mm were machined on the PMMA substrate through a CNC micromilling machine. This is the channel geometry. The width and the depth of the channel was fixed in both cases as 0.25 mm and 0.3 mm. With the help of 3D optical profilometer, we measured the average surface roughness of the channel, which was found to be 2 plus minus 0.1 microns, while the outer surface roughness was 30 plus minus 10 nanometers. The droplet was made to impinge the substrate at various points along channel's length. So as can be seen here, the droplet was impacted at some distance from the channel and a new parameter named eccentricity E was introduced, which measures the distance between the droplet impact center and the reference, which is the channel midpoint. With the help of parameter E, we defined the various points at which the droplet was impacted. So these are the results. For a droplet impact near 0.5 mm length channel, we observe two types of outcomes. One is droplet spreading and second one is droplet jetting. When eccentricity E was taken as 0.125 mm, we observed that the droplet spreads over the channel. T is the time here taken as 0 when the droplet impacts the channel. For droplet spreading, we did not observe any major changes in the fluid flow behavior. However, when eccentricity E was taken as 1 mm, we observed that the water droplet hits the channel and a protrusion is developed at the outer periphery of the droplet, which enters and wets the channel, and in the next frame it is observed that it lifts up at high angle and disintegrates into tiny secondary droplets, almost appearing like a jet. Because the initial spreading velocity of the lamella is very high post impact, we can expect that the protrusion that developed at the outer periphery of the droplet hit the channel at very high velocity, suffered a great change in momentum, and thus lifted in air at high angle and disintegrated. In case of droplet impact near 3 mm length channel, we observe that when the eccentricity E is high, that is 4 mm, the droplet spreads over the channel. A protrusion is still developed at the periphery of the droplet, but it does not undergo any major change post collision with the channel and wall. This is possible because the kinetic energy of a spreading droplet decays with time. So, when the distance between the droplet and the channel is high, we can expect that when the droplet protrusion hits the channel, it is almost out of energy to undergo any major change. However, when eccentricity E is reduced to 2.3 mm, we observe that the protrusion hits the channel, still has some sufficient kinetic energy, because of which post collision it lifts up at certain angle and disintegrates into tiny secondary droplets. And as the distance is further decreased, that is the eccentricity, if it is further decreased, this breakup which we termed here will shift to jetting. However, when eccentricity E was reduced to a very low value, that is below 1.5 mm, we observed an unusual change in fluid flow behavior. After impact, a protrusion was created at the periphery of the droplet that was observed to be gliding in the air, and in the next frame it disintegrated into secondary droplets. Besides that, a second protrusion is also created following the first protrusion, and that wet the channel, collided with the channel end wall and disintegrated into secondary droplets. This observation depicted by the first protrusion that disintegrated in the air was termed as droplet splashing in our results. We believe that the air entrapped inside the channel is responsible for this unusual behavior. For eccentricity below 1.5 mm, the droplet impact point is inside the channel. So, which means that the pressure exerted by the droplet fluid on the entrapped air inside the channel will be more, and thus the escape velocity of the air is also going to be more. Assuming that lubrication theory is applicable in this case, the pressure created by the lubricating air film is going to be proportional to the escape velocity of the air. So, it is possible that the entrapped air inside the channel sustained the incoming fluid pressure for a brief period of time, which resulted in this droplet splash. All the observations which were recorded are shown in this schematic here. In case of 0.5 mm length channel, we saw that with decreasing eccentricity, the impact outcome changes from spread to jetting and then again reverts back to spread. And in case of 3 mm length channel, the impact outcome changed from spread to first breakup, then jetting, and then splash plus jetting till eccentricity was reduced to 0. This is the summary. In future work, we plan to construct a model that will be able to describe the physics of the droplet fluid flow post impact near the channel, and also the effect of change in channel dimensions, substrate permeability, and fluid property will be investigated. These are the references which were followed. Thank you.
Yeah. Thank you, Tushar. So it's I have forgot to introduce the presenter. So it is by Tushar from IIT Bhubaneswar who did the talk. So I will take some questions from the audience. So please raise your hand if you have any question and then could ask. Anybody have any question for Tushar? Okay, so let me ask a question. So Tushar, so you did this experiment and you used the droplet size which was bigger than the channel length in all the cases?
Yes, ma'am.
Okay, so is there any specific reason for that?
We just wanted to check, like we just wanted to investigate. This was actually a extension of the work, as I said, after the report which was given by Jong. So just we wanted to see if we extend the length of the obstacle. So what will happen? The width being the same as 0.5 mm. We just wanted to investigate because in his case he just took a closed pore with a diameter 0.5 mm. So we just wanted to extend and check what will happen.
Okay, and did you see the same kind of phenomena which previous report has shown? You have tried to replicate that?
Yes, jetting which was reported, the same we got for 0.5 mm length channel. But apart from that, when we extended the length, we got these new observations which I reported here.
Yes, yes, yes. Yeah, and one last question, just for the present scenario, everybody asks, what's the application? So I also would want to know in which case you could apply this physics, whatever you are getting.
Actually, my intention was that basically, if a surface is rough, we cannot actually study or know how each surface roughness element is affecting the fluid flow. So just to break that thing, going step by step, I just my intention was that to study how a single obstacle will affect the flow instead of introducing multiple obstacles, which like which is being done like introducing patterns or pillars.
Okay,
uh,
okay.
yeah.
Okay, so this channel length represents some kind of roughness in a surface.
Yes.
Okay, okay. Thank you, Tushar. It was a great talk. Thank you.
Thank you, ma'am.
Yeah. So we'll go for the next talk, and it is paper number 1721. It is by Dungali Srihari and Yogesh K. Prajapati. The title is Numerical Simulation of Heat Transfer and Pressure Drop in Two Different Configurations of Pin-Fin Microchannel Heat Sink. So let's start the talk. I think Yogesh is the presenter.
Yes, ma'am, sure.
Yeah, let's start.
Respected session chairs, delegates, presenters, organizers, warm greetings to all of you. This is Yogesh Kumar Prajapati, Assistant Professor in the Department of Mechanical Engineering, NIT Uttarakhand. My topic of presentation is numerical simulation of heat transfer and pressure drop in two different configurations of pin-pin microchannel heat sinks. This work has been carried out by me along with my colleague Dr. Dungali Srihari. Now contents are as follows. Introduction. I will give some brief idea about microchannel heatsink, objective and problem definition, methodology, results and discussion, conclusions and reference. It is well known that with time, the tendency of miniaturization is increasing in various fields of engineering and technology, especially in electronics. At the same time, it is desired to increase the performance and output of the engineering devices. Henceforth, it becomes challenging to remove high density heat from a confined area. Inefficient cooling causes overheating that may reduce lifespan and damage the device. As shown in figure 1, it is very much evident that with advancement in technology, how number of elements are increasing, keeping the same chip size or even smaller. Figure 2 provides the Moore prediction and certainly it has closely predicted the trend of increasing number of transistors on a chip. In view of current trend and to meet the future demand, thermal management of electronic components and high-speed server is challenging and crucial. Since new generation advanced device may generate up to 1000 watt per centimeter square of waste heat, figure shows here that temperature is a major factor responsible for failure of the electronic devices. Hence, effective cooling is required to be maintained. Moreover, it is also established that 10 degrees Celsius reduction in junction temperature halves the failure rate of the electronic components. Microchannel heatsinks have been identified as one of the important cooling techniques for electronic devices and other similar components. It holds inherent property of higher surface to volume ratio, and the characteristics of fluid flow is slightly different from conventional channels. Figure below shows a conventional design of microchannel. Channels are of rectangular type and heat flux is provided from bottom. Since the first study conducted by Tuckerman and Pease, tremendous modifications have been done. Basically, geometrical modifications, coolant type, operating conditions, and surface texture. One of the modification is implementation of pin fins. So figure 5 shows in pin fin also several design amendments have been made, like alteration of geometry, aspect ratio of fins, orientation, porosity, density and pitch of the fins. Based on the introduction, the objective of the present work is to understand the heat transfer characteristics along with coolant flow behavior in two different heat sink composed of circular and rhombus micropin fins. One additional bare channel has been simulated to compare the results. Figure 6 shows the schematic diagram where it can be seen that total length is 30 mm and width is 12 mm. Both fins are arranged in inline manner and total number of fins are 70. Figure table below shows the detailed dimensions of both the configurations. Isometric view of all these three configurations are shown in figures 7. It is worth mentioning that all three computational domains consist of bottom wall of thickness 0.5 mm along with side walls of thickness 0.5 mm. Fluid and solid zones are clearly identified from these diagrams. Circular fins are inscribed over rhombus fin and diameter of circular fin is 1 mm and each side of rhombus fin is 1 mm. Primary and connecting passes are clearly shown over here. Conjugate method of commercial code ANSYS fluent is used to solve three-dimensional model of the computational domain. Following assumptions have been considered: laminar and steady flow, incompressible flow, thermal conductivity of copper substrate is constant, all outer surfaces are insulated. For the coolant, density and viscosity is varying with temperature. Momentum and energy equations were discretized by second order Kaplan scheme. Pressure velocity coupling is solved using the Simplex algorithm. Grid independency test has been done, and as shown in the table 2 and highlighted row, these cells have been considered for simulation of the problem. Inlet temperature of the coolant remains constant, that is equal to 300 Kelvin, and inlet velocity is calculated based on the Reynolds numbers. So Reynolds number is varying from 100 to 500. Accordingly, inlet velocity has been taken. Outlet atmospheric pressure is considered, and uniform heat flux is provided from the bottom of the heat sink, and the rest of the walls are insulated. Calculation of average heat transfer coefficient is done from this expression, where Q is heat flux provided from the bottom, TAW is average wall temperature. Average wall temperature is the average surface temperature which is coming in contact with the coolant, and TAF is the average fluid temperature. Once H bar is calculated, based on that average Nusselt number has been estimated. In order to validate the model, work of Wang et al. Has been reproduced. So as shown in figure, a single channel has been simulated, and methodology of the current model is used for the same geometry to predict the result. Temperature control is closely matching with the deviation of 2 to 5%. Here it can be seen that the channel path where fluid is flowing is clearly identified from the solid zone as significant thermal conductivity difference exists. In figure 10, pressure drop is compared, and again pressure drop is in very close concentration with the pressure drop of Wang et al. Coming to result and discussion section, figure 11 shows the variation of average bottom wall temperature in all three configurations at Q is equal to 300 kilowatt per meter square. It may be noted that initial slope of the curve for RE 100 to 200, it is quite steeper compared to rest of the higher value of RE. Possible reason may be significant transformation or alteration of coolant flow nature during this RE range that supports the more heat dissipation. Furthermore, average bottom wall temperature in rhombus fin heat sink is consistently lower, followed by circular profile and bare channel. Lower values of average bottom wall temperature indicates that a particular heat sink has dissipated higher heat. Hence, it is evident that corresponding to all RE, rhombus profile has highest capacity to transfer heat from the heat sink. Similarly, in the next figure number 12, average Nusselt number is maximum in case of rhombus fin, and it is followed by circular, and lowest NU is reported in case of bare channel. Pressure drop is of course increasing with RE, but the maximum increase is reported in case of rhombus fin, and this may be due to the fact that rhombus fin holds the sharp edges, and due to that edges a drop in pressure occurs. However, smooth flow is there in case of circular fin, and due to that it is having lesser pressure drop. Now coming to contour of temperature profile of all these three configurations, it is evident from the contour plot that the solid zone and fluid zone is having different temperature, and they are clearly identified. Now, prevalent temperature gradient between coolant and solid section reduces, especially in the rhombus configuration. Since bare channel has no fins, temperature contour shows only the coolant temperature at the selected plane in addition to side walls. Maximum temperature range is increasing from rhombus to bare. Coolant flow characteristics is shown in figure 15 and 16. Velocity profile is in both the configurations is slightly different. Unlike circular fins, primary flow passes of rhombus fin holds sharp edges of the fins. Two consecutive sharp edges along the lateral direction creates confinement in the primary flow path, resulting it acts like series of nozzles placed one after another. Moreover, connecting passes in rhombus fin is more participative and allowing the coolant to pass through it. Such flow behavior favors more mixing of the coolant. It is also evident from the velocity contour shown across the cross section in figure 16. Streamlines are shown over here. The main reason for the evolution of eddies is obstruction created by the fins in the flow path. It should be noted that two almost symmetric type opposite rotating eddies appear behind the heavy pin fin. Nature of aegis is slightly changing from inlet to outlet, which is more prevalent in rhombus fins. Because at the outlet side, more exchange of coolant happens between two successive primary flow passages. Now with this I am coming to conclusion section. Comparative numerical analysis of three different configurations of the heat sink has been carried out. Based on the results obtained, following conclusions may be drawn. Alteration in geometry of the pin fins causes considerable change in the heat transfer rate. Heat sink with rhombus fins exhibits 30 to 40% higher average Nusselt number compared to other two profiles. Order of higher to lower heat transfer is respectively in rhombus, circular and bare channel. Although rhombus profile exhibits maximum heat transfer rate, it also offers highest flow resistance, resulting maximum pressure drop occur in this channel. These are the references for the current study. Thank you very much for your patience.
Thank you, Dr. Prajapati. So I will take questions. So please raise your hand if anybody have question. Yeah, so let me ask one question to you. So you have done in ANSYS and you have validated with Wang's result. So was the Wang's result an experimental result?
No, ma'am, it was actually numerical work that we have reproduced, but they also have validated their numerical work with their previous experimental work.
Okay, okay. And what was the number of fins you gave in both the cases, in circular and rhombus?
70.
70. And what was the reason for taking this number 70? Is in literature also it's 70?
Actually, we have gone through certain literature and we found that most of the people are taking a number of fins from 50 to 100 or even more. So it was just a comparative between two different configuration of fin, how they are behaving. So our sole objective was to look to analyze the performance of these two configurations. Actually, a lot of work has been done, but still we were trying to make it comparative. We are further going for experimental work. So before going to experimental work in such type of work, we are planning to do and go for numerical.
Okay, okay, yes. The results were really interesting. The vortex behind the circular and the rhombus, they were quite interesting how different they are. I was just curious, like if you have different heights of these fins, will it help in mixing? Means say now you have same height, but if you differ it, will it help?
If, as per my experience, since I am working in microchannel since my PhD duration, if you go after a certain range of height, it is not going to help you much. What I have observed and seen in the literature that if you can make some tip clearance, means rather than taking the fin up to the top wall, if we have tip clearance, a small tip clearance, it will certainly increase certain amount of heat transfer. That work we are actually doing, analysis with tip clearance, and that is of course giving some better result.
Okay, so these results were with tip clearance or it was?
No, ma'am, this is complete close.
Complete. Okay, 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 great. So next time I think we will see those results as well.
Sure, ma'am.
Okay. Yeah, thank you, Prajapati.
Thank you,
I think somebody else do not have any question, so we could go to the next talk then. So paper number 191. It's the liquid droplet morphology on fiber of a fog harvester mesh and the droplet detachment conditions under gravity. So it's from Jadavpur University, and the speaker will be Dr. Parthasarathi Datta. Yeah, welcome, and please let's start.
Hello everyone, my name is Parthasarathi Datta. I am a second year master student of the Department of Power Engineering, Jadavpur University. I thank the FMFP organizing committee for giving me an opportunity to share our topic of research. The topic of our research is a liquid droplet morphology on the fiber of a fog harvester mesh and the droplet detachment conditions under gravity. Water crisis means the lack of adequate freshwater resources to meet the standard water demand. In 2015, the World Economic Forum cited it as one of the major crises humanity has ever faced. Fog has the potential to substitute traditional sources of water. Traditionally, fog harvester was used in coastal mountains and highlands, but now fog harvester can also be used in a cooling tower power plant. It has been shown that for a typically 500 megawatt power plant, if we are able to capture about 40% of the drip losses, then we will be able to conserve about 10.5 meter cube of water per hour. The typical challenges in fog harvesting are clogging. Talk about clogging, let's talk about set coefficient first. Set coefficient is a fraction of the mesh projected area occupied by the mesh material. It can be thought that higher is the setting coefficient, higher will be the interception of the fog-laden wind and the mesh material, and higher will be the water collection. But this is not the case always, as higher setting coefficient also means that it will offer an additional resistance to the path of fog flow. It will offer an additional impedance to the path of fog flow, and the fog-laden wind might change its direction. Similarly, the next is the premature dripping. It has been found that for larger sliding length, the larger droplets have a tendency to fall down, and it has also been found that the water collection for a sliding length of 240 millimeter mesh is greater than that of a mesh which is having a sliding length of 340 millimeter. Next, to talk about re-entrainment, the water droplets that get collected on a mesh, some may get escaped due to the oncoming wind drag, due to the oncoming fog streams wind drag. So this phenomena is called as re-entrainment. So all this clogging, premature dripping, as well as re-entrainment is related to droplet morphology. That's why we are motivated to understand the droplet morphology first. So we have seen the transition of one droplet shape to other droplet shape, as well as we have studied parametric variation, and we understood the conditions influencing the droplet morphology. We also did a study of the effect of the bond number on droplet detachment. So there is something called as contact angle, which is when a liquid sits atop a fiber, the angle found between the solid liquid interface and the liquid gas interface is called as a contact angle. Now there are two possible shapes of a droplet on a fiber. The first one is a barrel-shaped droplet, and the other one is a clam-shaped droplet. Barrel-shaped droplet in which the liquid completely wraps the fiber from all sides. It is a symmetric shape, and whereas a clam shell, it simply sits atop the fiber. The barrel shape is preferred when the liquid volume is large and the contact angle is small, whereas a clam shell shape is preferred when the liquid volume is small and the contact angle is large. We will later see that in the presence of asymmetric forces like the force of gravity, it is a clam shell shape which is more energetically preferred. Now, when a liquid is bounded by a curved surface, it experiences pressure, which is excess pressure, which is given by this equation. Now, this equation has been solved for a barrel-shaped droplet using elliptic integrals to obtain certain parameters specific to droplet geometry. Whereas no such solution exists for a clam-shell shape, which warrants the use of the Surface Evolver software. Surface Evolver is an open-access finite element package that moves triangulated surfaces iteratively to minimize the user-defined energy of a described geometry using gradient search algorithm. The user input comprises of an initial energy defined over a surface or volume. It also depends on the boundary constant. So for our case, the choice of the initial geometry is dependent such that it tries to minimize the number of iterations required for the final convergence. So for our barrel shape, we started with a cylindrical shape and it ultimately converged into a barrel shape. So for our simulation purposes, we have considered the edge length to be varying between 5.33 into 10 to the power minus 5 meter till 1.6 into 10 to the power minus 4 meter, and any edge length that was greater than this value were refined, and edge length that were lesser than this value were deleted. Next, to compare our work with the existing numerical model, we compared the work with Meckel and Newton, and we did a comparison of the reduced thickness and reduced length. So to talk about reduced volume first, it is a ratio of the droplet volume divided by the cube of fiber radius. Similarly, reduced maximum thickness is the maximal thickness of the droplet divided by the radius of the fiber, and we got a deviation of only 0.8% from the existing work of Meckel and Newton. Similarly, we did a comparison of the reduced length. Reduced length is the length of the fiber weighted by the droplet divided by the fiber radius, and we got a variation of 4.3% from the work of Maxwell and Newton. So we then studied the transition of a barrel to clamp. So initially we started with a low value of contact angle, and we progressively increased the value of the contact angle till the shape morphed into a clamshell. And we did it for various volumes, various reduced volumes, and we were able to obtain this red curve. So the region on the right hand side of this red curve is the absolute stability of clamshell, and the region on the left hand side of the red curve is a metastable state when both the barrel and the clamshell can be independently stable. We then studied the transition from a clamshell shape to a barrel shape. So initially we started with a higher value of contact angle. We kept on reducing the value of contact angle until the shape changed into a barrel shape. We then repeated it for various sets of reduced volume until we obtained this black curve. So the region on the left hand side of the curve is the barrel shape, which is absolutely stable here, and the region on the left right hand side of this curve is a metastable state when both the barrel shape or the clamshell can be independently stable. Then we have started the detachment volume. So initially we started with a clamshell shape, and we kept on increasing the value of the reduced volume by 1 unit until we obtained that particular value of reduced volume when the droplet got detached from the fiber. So when the droplet got detached from the fiber, there was no portion of the droplet attached to the fiber. We did it for a lesser value of bond number, for a fixed fiber radius, and for a contact angle of 30 degree. To talk of bond number, it is a dimensionless number which signifies the relative importance of the force of gravity as compared to the surface tension. Next, we observe the transition of a barrel shape to clamshell shape in the presence of gravity. So initially we started with a higher value of lesser value of contact angle. We kept on increasing the value of the contact angle by 1 degree until we got the clamshell shape. We repeated this for various sets of reduced volume until the black curve or the rightmost curve was obtained. We then repeated the same procedure for higher value of bond number, and we saw that the same curve shifted leftwards. Further we increase the value of the bond number, we see that the curve further shifted leftwards. So one important conclusion that can be drawn from here is, if we keep on increasing the value of the bond number, the absolute stability region of the clamshell shape keeps on increasing. The other important phenomenon that can be observed here is re-entrant behavior, which is possible at say lesser value of contact angle and higher value of bond number. Let's say for this line, which has a value of bond number of 0.0218. So for a contact angle of 15 degree and up to a reduced volume of let's say 35, we are in the absolute stability region of clamshell. Now if we keep on increasing the value of the reduced volume till 130, we are in the metastable state when both the barrel shape or the clamshell can be independently stable. If we further increase the value of the reduced volume, then we again enter the absolute stability of clamshell region. We then observe the transition from a clamshell shape to barrel shape in the presence of gravity. So again, we started with a higher value of contact angle as it was a clamshell shape, and we keep on reducing the value of the contact angle by 1 unit until we obtain the value until the shape morphed into a barrel shape, and we got this curve. Now, if we repeat the same procedure for a higher value of bond number, then the curve shifted leftwards. And the further, if we increase the value of the bond number, the curve again shifted leftwards. And also we observe the re-entrant behavior here for lower value of contact angle and higher value of bond number. So a conclusion that can be drawn from here is also that if we that for higher value of bond number, the absolute stability of barrel region keeps on reducing, and re-entrant behavior is observed at higher value of bond number and lesser value of contact angle. Then we studied the effect of the bond number on droplet detachment. So initially we started with the lower value of bond number, and for a fixed value of contact angle, we got the reduced volume. We then repeated the same procedure for different value of contact angle, but for the same value of bond number. We then repeated the same procedure for different value of bond number, and we see that the curve kept on shifting bottomwards. So the bottommost curve is of the highest bond number. So an important conclusion that can be drawn from here is, if we keep on increasing the value of the bond number, the detachment volume keeps on reducing. So the summary of our research is that whether it is a barrel shape or whether it is a clamshell shape, it depends on the reduced volume, contact angle, and the bond number. And in the presence of gravitational forces, it is the clamshell shape which is energetically preferred. And if we keep on increasing the value of the bond number, the detachment volume kept on reducing. And the reentrant behavior is observed both for absolute stability of barrel shape and for absolute stability of clamshell shape. These are the references. So we thank DST ACRB for providing us funding, and I thank all of you for your patient hearing. Thank you.
Thank you, Mr. Datta. So I will take questions first from the audience. Please raise your hand and you could ask your question. Okay, so let me ask one question. So as you said, you are trying to find the drop impact on a fiber. So how will you take account of the porosity of the fiber?
Ma'am, till now we have considered the fiber to be continuous, and we have not considered other factors like porosity and roughness. So we have considered a simple
fiber. So in this presentation it's not there, but have you thought of? Just I was curious.
Ma'am, that can be thought, but before that, our final objective is to design the fog harvester. So the analysis that we have drawn for a horizontal fiber, that we will extend for a vertical fiber, and then yes, but ma'am, that's a good thought, and we will definitely think on it. Thanks, ma'am.
And another question, because I also work on similar topics, and I thought of this topic, so I have some ideas. So I was just thinking, what would happen if you increase the contact angle more, like make a super hydrophobic kind of solid? What will happen?
Then for higher value of contact angle, it was the clamshell shape was more preferred, and for lesser value of contact angle, it was a barrel shape. And in the presence of gravity, means if for a bond number in the range of, let's say, 0.044 and higher, it is a clamshell shape which is preferred. So, ma'am, for higher value of contact angle, it will be the clamshell shape which will be more preferred.
Yeah, and your final goal is to have the drop breaking and it should fall, no? That is the final aim.
It can slide also. Means,
okay, it can slide and fall. So, okay, yes. Okay. So according to your results, which will you prefer? Means if you have to suggest someone, which contact angle and which bond number should you recommend? Not particular, in the value, in some range you could say.
Ma'am, as we have not completely designed the fog harvester, so right now we cannot comment on any particular value of contact angle or bond number. Some more research is also required. For now, the analysis is simply on a horizontal fiber. We have to still continue the research, but then we can.
I think it is for more bond number it is preferred, because in that case it will the drop will break and fall. Do you think so?
Yes, ma'am, absolutely.
Yeah.
It will lead to a clamshell shape, and then it will lead to the droplet detachment.
Yes. Okay. Best of luck for your further work, and thank you.
Thanks a lot, ma'am.
Yes, so let's go to the next talk. So paper number 207. It's analysis of magnetohydrodynamic slip flow of non-Newtonian fluids through circular microchannel. And who is the presenter?
Yeah, am I audible? Am I audible?
Audible, yes. Yeah. Let's start. Yeah, thank you.
Hello, good morning ladies and gentlemen present here and respected session chair Dr. Bonhi Roy. This is Satyabrat Poddar. Myself along with Mr. Sushobhan Mishra and Dr. Arunabha Chanda have worked on the topic analysis of magnetohydrodynamic slip flow of non-Newtonian fluids through circular microchannels. This is the presentation of the work. As all of us know, microchannels are fluid passages of very small dimensions, typically in the order of 10 to the power minus 6 to 10 to the power minus 9. They are very popular in the application of MEMS and various types on the basis of their sizes and shapes. In our work, we have worked on circular microchannels. Circular microchannels are useful for biofluids for various reasons like low operating pressure, absence of flow stagnation problems which are present in rectangular and square microchannels. Microchannels mostly find its applications in the areas of handling biofluids and heat transfer. The concept of microchannels first proposed for the cooling of microchips. Later, it develops its area of applications in the field of MEMS, lab on a chip devices, cell analysis, etc. Most of the biofluids, when they pass through microchannels, show flow characteristics of non-Newtonian liquid flow. Here in the present work, Oswald Dewale model of power law fluid has been used to model non-Newtonian fluid flow. The equation shows the mathematical form of the power law in which flow consistency index and flow behavior index are two parameters which are useful to describe a non-Newtonian fluid. Slip flow is a physical phenomena which can be seen in microchannels. This phenomena makes a notable difference than that of macroscopic flow. The reason for slip flow has been a popular topic of research for the last few decades. Molecular dynamics has pointed out a few reasons for the slip flow, among which the concept of surface energy corrugation, atomic stick slip, and the threshold value of potential energy barrier are popular. Surface roughness and the nature of microchannel wall, whether it is hydrophobic or hydrophilic, are also few parameters on which the possibility of slip flow depends. Slip flow was first described mathematically by Navier using a general boundary condition which shows slip is a local phenomena which happens in the near wall region. Microchannels have few advantages and disadvantages. Comparing both, it can be observed that microchannels have advantages of handling biofluids and heat transferring fluids in micro devices, which makes it popular in the research of fluid mechanics. Present investigation has been done after a thorough literature review, among which few has been described here. Few literatures were studied for the required parameters for modeling biofluids. Few literatures, like the work of S.J. Temer, have been studied for numerical simulation of slip flow through microchannels. A group of researchers is now working on the effect of magnetohydrodynamics on the fluid flows, which are good conductor. The investigation has considered the flow through circular microchannels, which can be described by the following popular governing equations. Here, all the notations used carries their usual meaning. After simplifications, these governing equations can be reduced to a simple equation for the expression of tau rz. The boundary conditions of slip flow have been used, in which velocity at the wall is not zero. Rather, it catches the value of slip velocity at the vicinity of the wall. Following are the non-dimensional parameters which have been used for converting all the equations in their non-dimensional form. Here, the term beta is known as slip coefficient, which is nothing but the ratio of slip velocity and average velocity. Following are the non-dimensional momentum equation, which is without considering the effect of magnetohydrodynamics. Here we also describe the dimensionless boundary conditions, and we can observe beta over here, which is nothing but the slip coefficients. Also, we can see the role of dimensionless slip length over here, and which can be described as follows. By solving the momentum equation with the help of slip boundary condition, we can get the equation for the velocity distribution through circular microchannels for non-Newtonian fluids. Here, the following expression shows the expression of Poiseuille number, which is nothing but the product of friction coefficient, and Reynolds number. For the analysis of the effect of magnetohydrodynamic slip flow, we have considered a fluid which is nothing but xanthan gum. This xanthan gum is nothing but the extracellular heteropolysaccharide which can be produced by the bacterium Xanthomonas campestris. Now, this xanthan gum has a ingredients of glucose, mannose and glucuronic acid in the ratio of 2:2:1. When this xanthan gum is mixed with formic acid, then it exhibits electrical conductivity. The properties of the solution at 25 degrees centigrade is described in the following table. When the magnetohydrodynamics is considered in the analysis of the flow of non-Newtonian fluids in the form of xanthan gum mixed with formic acid through circular microchannels, there we have few deviations from the earlier equations which can be summarized as follows. Here we have showed the dimensionless continuity equation and momentum equation where we can see dimensionless parameter like Reynolds number and Hartmann number. This is a schematic representation of the numerical solution what we have performed to analyze the present work, and here also we have provided the basic mesh information for a better understanding. To start with our work, at first we have validated our results with the standard results available in the past literatures. Following are two diagrams which shows a good agreement of our work with the previous one in the form of validation. This table shows a good agreement between the analytical and numerical result as available with the previous literatures what we have discussed is earlier. To analyze our results, we have compared different velocity profiles. These two figures are the velocity profiles without magnetohydrodynamic effect. In the first figure, when the slip coefficient beta is held constant to 0.1, then the comparison of different non-Newtonian fluids has been shown. In the next figure, when a flow behavior index is held constant at 0.5, then the comparison of different velocity profiles of different slip coefficient beta from 0.1 to 0.3 has been shown for the understanding of the variation of the flow characteristics. At the next level, we have applied magnetic field externally to the microchannel. The first figure describes the effect of externally applied magnetic field on the velocity profiles when the xanthan concentration is held constant at 0.5 weight per volume percentage. It is observed that with the increase of externally applied magnetic field, centerline velocity decreases and corresponding slip velocity increases. The effect of the variation of the xanthan concentration on the velocity profiles has been given in the next diagram. When the applied magnetic field is held constant, then it is observed that with the increment of xanthan concentration, centerline velocity decreases and slip velocity increases. We have drawn few conclusions from our present work. Like, to conclude, at the very beginning, pseudofluidic fluids have higher centerline velocities and discharge than that of dilatant fluid when they are exposed to the same slip coefficient beta. Next, we have observed that slip coefficient varies for a constant flow behavior index, then centerline velocities increases and slip velocity decreases. Slip coefficient is also affects the flow parameters like dimensionless slip length, centerline velocity and wall friction coefficient. When we have applied magnetic field externally, then it is seen that slip becomes more predominant near walls and centerline velocity decreases. When electrical conductivity of the solution increases with the xanthone concentration, then also slip flow increases and consequently centerline velocity and average velocity decreases. Here are few literatures what we have during our literature survey. At this moment, to conclude our today's presentation, all for your patient listening.
Thank you, Dr. Poddar. It was a nice, informative talk, and you have done analytical and numerical both, so it's really interesting. So let's first take question from the audience. So any question from the audience, please raise your hand and you can ask your question. Okay, so let me ask one question. Yes, as you said, that this is applicable for blood flow in a vessel. So how can you relate your present results with such situation, like the blood is flowing through a vessel, and what could happen?
Yes, madam. Actually, in our studies, we have seen that blood also shows behavior of non-nutrient fluid flow, and we have also studied that if words are also available showing the type of fluid behavior, and now when we have considered other biological fluids, like we have taken xanthan gum over here. Now in a present days, high values of magnetic induction is becoming applicable in MRI tests and all, where now in present days we are only applying the value of 0.1 Tesla, 0.2 Tesla, 0.4 Tesla. But presently, what we are finding, the maximum value is now reaching up to 5 Tesla is a very common, and the people are working on the effects of applying more values like 10 Tesla and a maximum value what we have applied till date, that is 20 Tesla. So inspiring from their work, I have also worked to find what is actually happening with the high values on a biological fluid. Those are the examples and applications what we are observing.
So for high values of magnetic effect, so you are seeing that the velocity of the slip velocity is increasing at the wall. Okay.
Yes.
And what about the center velocity? You said it is decreasing.
Velocity, corresponding centerline velocities decreases.
Okay. So what is your further approach to this work? How are you going to further work on?
Actually, this is this work what I have presented today. This is actually very initial results we are showing. Now we are extending those work with comparing the parameters like flow behavior index, consistency index, then concentration. If we increase concentrations in the fluid, then what is happening? If we add nanoparticles there, actually main application is to carry different molecules in the form of nanoparticles to the organ. That is actually that is called a drug delivery in the with the application of magnetic induction and all. Those are our future planning. We have partially succeeded, but the work is still we have to do.
Okay, great. So best of luck for your future work for this.
Thank you,
Okay,
madam. Thank you very much.
thank you, Dr. Purta. So yes, so we'll go for the next talk. So we are already halfway and we have 4 more talks. So paper number 227, numerical simulation of two immiscible liquids flow in T microchannel using level set method. And the presenter is Mr. Tarachand Kumar Maurya. So please start.
Hi, myself Tarjan Maurya. I am research scholar in IIT Roorkee, working under Professor Sushanta Datta in Mechanical Department. Here I am presenting my research work on numerical simulation of two immiscible liquids flow in T microchannel using level set method. These are the topics have been covered in this presentation. In the past few years, technology-related microfluidic has become essential in many fields, like microreactors and lab-on-chip. In the path of development, these technology, many researchers have done numerically and experimentally work. Few researchers have the idea that micro droplet can work as a microreactor and the indication of some characteristic. So I am interested to analyze the droplet formation at micro level, droplet diameter and droplet formation frequency and initial droplets breakup time are the key parameters which have been studied here. These parameters or droplet uh, is depend on various factors. Those parameters are like geometrical parameter of channel and fluidic properties such as viscosity, surface tensions, and other parameters like flow rate of the fluids. It is already known the idea of T microchannels among the researchers uh, to use for two immiscible liquids at the micro level in controlled condition. Flow rate of these fluids affect them greatly. Droplet of liquid which is formed addressed by the dispersed fluid here and the other fluid which is in main channel is addressed by the continuous fluid. There are two models which are being used generally, LB method and LSM method. LSM method has been improved greatly in previous work by the many researchers. They have used few arrangements such as like phase initialization. The phase initialization techniques has been introduced by the Schumann, and he found that he could reduce the error in mass from 80% to 5%. My objective to study the immiscible liquid interaction at T junction and simulation of the droplets formation. The flow patterns are explained through simulation. Droplet formation and flow field were analyzed and explained. The dispersed flow rate is optimized for the given a continuous phase flow rate. In level set method, for tracking the interface, I have considered the level set function is 0.5. It was defined that phi is equal to 1 for the dispersed phase and phi is equal to 0 for the continuous phase. The interface, the properties of fluid depend on the both liquids, which slide number 10, and the diameter of droplets has taken only those regions where the level set function is greater than the 0.5. In this model has been applied on the T microchannels which have a dimension 0.2 mm into 0.2 mm and length of is 5 mm and the side channel is 1 mm. Other important physical parameter has been also taken during the in the model during the simulations, which is given in the slide. From the simulation result, droplet formation with the time at a T junction has been shown in the figure. Initially, when the fluid start to 0. At 0.0025 second does not affect the fluid filled into main channel, but as we goes time with time up to 0.0275 second, it start change the flow field in main channel and dispersed fluid is getting the shape in the main channels. Fluid in the main channels grows up to the 0.065 second and after that form the droplets. This is a complete cycle of droplet formation at the junction point. Same steps has been followed in the next droplet formation. During droplet formation at the junction, velocity field in the main channel for a continuous is changes with time, which can clearly see in the diagram. We see that at the time 0.002 second, flow field is completely symmetric, but as the dispersed fluid enters after the sometimes the flow field get distorted, then after the breaking droplets it regain their shape. This also can be noticed in the velocity profile. The velocity profile has been taken in the diagram. The velocity profile has been taken different time at the same cross sections and observe that the unsymmetric variation in the velocity profile. Initial, the pressure change in main channel along the axis in downstream direction is decreased, but after the sometimes we found a crest. This crest because of the present droplets in the main channel. By the simulation results, I got that if we increase the dispersed phase flow rate, the droplets diameter is increased. Can be explained through the filling volume. Filling volume for dispersed fluid is greater because the flow rate of dispersed fluid is getting increased. Breakup time of the droplets is also getting decreased with the increasing flow rate of dispersed phase. It is because the penetration time is getting shorter with the dispersed flow rate, as well as the droplet forming frequency is also increasing. We can say that the interval uh, time between the two droplets is getting decreased when we increase the flow rate of dispersed phase. And after the 0.501 we will find a continuous flow of the dispersed fluid in the main channels Conclusion. It was found that droplet formation is going to delay with a decreasing dispersed flow rate and the droplet size is getting smaller. Pressure along main channel length first decreases linearly before the formation of the droplet and increases during the formation of droplets. And after breaking the droplet, it goes to decrease. It has been found the velocity field in main channel at the T junction is unsymmetrical during the formation of droplet, which exhibit the unsymmetrical velocity profile. The effective droplet diameter increased from 125 micrometer to 227 micrometer when the flow rate of the dispersed phase increased from 0.263 ml per hour to 0.501 ml per hour. The droplet breakup time decreases from 0.092 second to 0.055 seconds. Similar trend follows in the droplet breakup interval. It tends to decrease from 0.133 second to 0.008 second when the flow rate of the dispersed phase increase from 0.263 ml per hour to 0.501 ml per hour. 0.313 ml per hour of dispersed flow rate and 5 ml per hour of continuous flow rate would be one of the optimized parameters. This work was supported by the Ministry of Human Resource and Development and the Institute of Computer Center IIT Roorkee. And also, I want to thank my guide who gave me a clear vision about.
Thank you, Mr. Maurya. So we have one question from the audience. So yes, you could unmute Dr. Sharma and you could ask.
Yes, ma'am. Hello, sir.
Please unmute the audience who have the question. Please unmute yourself and you could ask your question.
Yes, shall I ask now?
Yes.
Yes, sir.
Yeah, Tara, I appreciate in-house code development through level set method, but there are certain lot of numerical details which are expected when you present a numerical work, which I was just wondering, and I want to ask you, you have used a staggered grid or a collocated grid?
Sir, I have used a structured grid in my simulation and during my simulation.
You have developed this code from scratch or you have inherited from somewhere else?
I have done my simulations at the console 5.4. It is a software package. It has a module of LSA method with reinitialization. So it generated the structured meshing throughout the domain. So I am just using that.
So you are using a software, you have not developed your code, correct?
Yes, sir. Yes.
Okay. Then the second question comes is that I was, if I'm not missed, I was looking for some validation, grid independence, time independence.
Sir, I have validated this numerical work with Graph, who has done this work experimentally, but he has used in this. But he has done also numerically, but he used different methods like LB method. So I have using LSA method in this in my work and validated with his experimental work.
Whether you have shown that validation in this presentation?
Sir, it is not mentioned in this presentation slides, but it is already addressed in the papers.
Yeah, note that wherever you are presenting, this is one of the things audience expect to gain confidence in your work.
Yes.
Okay, so make sure in future you should include that. It's very important in a new work. Okay, now the last question which I would like to ask, Bani, you have some time? Can I ask?
Yes, sure.
So the last question is, you said that you obtained the droplet breakup diameter, breakup time. I just want to ask you, since you're using a software, what is the procedure you use to obtain this? Because it's a little critical. From the code, how do you obtain it?
Sir, actually, in LSA method, the model has already included uh, those like it has included Navier-Stokes equations and level set equations. It has already in that, and and a part of this I have given like initial values for the and like level set functions.
I would suggest that make sure to test this also, huh? Because just to confirm, because you're using a software, so there is a danger that you blindly do certain things. So, which you are a
Yes,
PhD student or you're an MTech student?
yes, sir. I am PhD student.
Yeah, especially since you are a PhD student, it is
Yes, sir.
expected that you should test these calculations also to make sure, most importantly, yourself feel confident
Yes,
that whatever
yes,
you're doing is correct. And
yes, sir. Thank you,
thanks.
sir.
Thank you, Dr. Sharma.
Thank you, sir.
So we'll take another question from Mr. Santosh Kumar Jaina.
Yes, ma'am. So can I have time, sir? Ma'am.
Yes, you can
So
ask.
my question is the figure what you have shown for velocity profile and pressure profile at
Yes,
what
sir.
capillary range particularly you have worked already? The image profile, the
Pardon?
pressure profile and velocity profile you have shown for which regime? Squeezing, dripping, jetting, or which regime you have shown?
In at the junction in main channel, at the junction in main channel. So during the drop formation at the different time, I have just shown the velocity profile.
No, means at what regime? That different regime you show na, initially. Some capillary, some squeezing regime, dripping, jetting. These are, I
It
think,
is
occur at different capillary numbers.
it is squeezing reason.
Squeezing, but the images what you show, the droplets is not in the squeezing regime. It is just like some jet kind of things. Length increases and then breakup occurs. So I think squeezing regime is a little different or the same what you have shown in images. The little jet and breakup occurs. That is squeezing regime. So that's my confusion.
Uh, Sir, exactly.
And okay, let it that way. What capillary number can you tell me? The range you are working? You have shown that velocity profile and pressure profile. The capillary number range.
Yes, sir. I have not calculated that capillary number exactly.
Okay. Because that is also, I think, important because that range of capillary number shows the different regime. I think so.
Yes, sir. Capillary number and Reynolds number both is important for the categorize the regions. But I didn't mention this number right now in my slides, so I just not remember that.
Okay.
Yes.
Okay. So, ma'am said that is the question I want.
Thank you, Mr.
Thank you, ma'am.
Yes, so Maurya, you got so many suggestions, and you are the only one till
Yes,
now
sir.
with suggestions.
Yes,
So please
yes,
obey to that, and let's meet in the next FMFP and let's see some more work of yours. Thank you. So we'll go to the next talk, talk number 246. So it is transient dynamics of liquid jets during droplet impingement on superhydrophobic surface. So it's from IIT Guwahati itself, the organizing committee is Mr. Amrish Dalal's group. So the presenter is Mr. Bhaskar Jyoti Sharma. Yeah, let's start.
A very good afternoon, everyone. Myself, Bhaskar Jyoti Sharma. So I am presenting a paper titling Transient Dynamics of Liquid Jets During Droplet Impingement on Superhydrophobic Surface. I am a PhD scholar in the Department of Mechanical Engineering, IIT Guwahati. So first, let us talk about superhydrophobicity. Superhydrophobicity is the extremely water-repelling behavior of any surface, which helps in easy movement of the droplet over the surface, and this has been used in numerous purposes in the last many years. And as you can see, the people have studied droplet impact conditions, and people have studied for many other applications such as self-cleaning, anti-icing, anti-fogging. And this has very high impact in pathogen transfer, dark cleaning, electronic cooling, and inkjet printing. So what is the or usability of superhydrophobic surface is that it provides an air layer between the underlying substrate and the liquid droplet, and this air layer maintains one gap and helps in easy movement of the droplet. On the other hand, the jetting dynamics of liquid droplets has been studied extensively in the past. One of the pioneering study in this regard is done by Waddington et al. In 1908, who studied the impact of milk droplets on a milk layer and found that a liquid jet is formed upon the impact. Here we have in a GIF we are showing the liquid jet generation process studied by Waddington et al. However, this has been repeated later on with high-speed camera, and this is the process in which Waddington observed liquid jet dynamics. Similarly, Bartolo et al. Studied the formation of singular jets, which has a similar dynamics like the jet studied by Waddington. However, these are produced by the collapse of the cavity, internal air cavity. This is shown, and these are very high-speed jets which can reach up to 30 times higher than the impact velocity of the droplet. Similarly, this is one of the studies where liquid jet production has been studied on the impact on superhydrophobic surface. These are some kind of special jets. This is studied by Pearson et al. Who obtained two thong jets having two thongs, and later these thongs merge and produce two secondary droplets. And this is one of the jetting instabilities produced from a single droplet attached to a nozzle, and this process has been observed by Taylor first, and this is the whipping instability, and this has been used for many electrospraying or many other technologies. So as such, we can see the jetting process after the impact of a liquid droplet, or as such any jetting from a liquid droplet, has extensive applications, and this has been studied in many circumstances. However, what is the gap in literature? Many reports have studied jetting the dynamics from numerous surfaces. However, with the behavior of these jets, with the variation in the liquid viscosity, as well as during the impact on superhydrophobic surface, its variation with the impact velocity has not been studied exclusively, and in this work we have studied this phenomena. Here we are showing a simple experimental setup used for the present study. This setup consists of a syringe which produces liquid droplets. This is the superhydrophobic surface that we have produced from carbon soot particle. Here we have shown the complete production method. This production method is borrowed from the work of Iqbal et al., which is recently published. This method is extremely helpful in producing low-cost superhydrophobic surface from candle soot, and this is one of the brilliant work done by this assistant group. And other than the superhydrophobic surface, we have very high-speed camera which is capturing this impact dynamics at 12,500 frames per second. We have a bright backlight, and interestingly, this candle soot coated superhydrophobic surface has a fractal-like surface structure, and this is the surface structure produced by Assis et al., and this is the surface structure produced in this study, and both have very strong similarities, and they have also shown that this is a hemiophobic surface. That means it can repel even liquid droplets, which has a very high viscosity. So we can say that by candle soot method we can produce a very high superhydrophobic surface, and this is used for the present study. Moving forward, these are some of the non-dimensional numbers which we will be saying in this study. This is the Weber number, Reynolds number, and Onsorge number. Weber number shows the effect of liquid inertia and surface tension. Reynolds number expresses the competition between the liquid viscosity, inertia and the liquid viscosity, and Onsorge number shows the effect of liquid viscosity with respect to the surface tension forces and inertia forces. So these are the four liquids that we have been studying or used in this experiment. We have neglected the effect of gravity in this study, and because the average diameter of the droplets, which is around 2 millimeter, is very much less than the capillary length for this study, which is around 2.73 millimeter. So impact regimes. So before moving to the jetting dynamics, we would like to show what we have studied a whole droplet impact regime in this study. However, for this present paper purposes, we are showing only the jetting dynamics. But before going towards that, I would like to explain the different regimes observed in this the impact of liquid viscous liquid droplets with a huge range of impact velocities. And we can see this is for the DI water droplet, this is for the glycerol 50 droplet. This corresponds to the a very highly viscous 65% glycerol liquid droplet, and this is totally viscous, it is around 80% glycerol droplet. And we can see that this is the this is a whole range of dynamics we can see. This is the complete rebound regime in which the droplet impacts and then it lifts up totally. This is the splashing condition where we observe liquid splashing. This is the splashing condition at a very high velocity for 50% glycerol droplet, which has 6 times more higher viscosity than that of DI water. And for similarly, in between we observed a simple partial pinning region, and for the 65% glycerol droplet we use only complete rebound and partial pinning regime, and for the higher viscosity droplet we observe only sticky vibrating droplet. So this regime for the DI water droplet has been shown in detail in this regime, and these are the some of the features. And this feature, rebound plus air cavity, corresponds to the singular jet formation and this cylindrical jet formation. And we will be studying this singular jet formation with the help of air cavity, and cylindrical jet formation with the help of capillary wave focusing in this paper. And in this, all these regimes are shown for the correspondence of the reader, and we can see at the very high velocity one observe liquid splashing for DI water droplet, whereas this is suppressed, and we observe partial pinning for 65% glycerol droplet, which is 20 times more higher viscosity in the water. And similarly the jetting dynamics are shown, and we can see at comparable velocity for DI water droplet we observed complete rebound, and whereas in 65% glycerol droplet it is nearly partial pinning, and the dynamics take more time than that of normal DI water. So this is the schematically we are showing the jetting dynamics on superhydrophobic surface. So first the droplet impacts, then it expands, then it forms a different liquid dome type shape, and then this liquid column is formed. However, depending upon the impact conditions, in some cases we observe complete rebound after the generation of secondary droplets. However, for very high viscosity droplet and at very high velocities in certain conditions, we observe partial pinning, and the liquid jet partially bifurcates and then it partially move upwards. So here we are we're showing the experimental snapshots. We are showing this snapshot for two viscosities, which has been mentioned earlier for DI water droplet and glycerol 65 in a more illustrative manner, and we can see that the dynamics of this viscous droplet are much slower, which is due to the effect of liquid viscosity. And also the less number of droplets are generated in this second process. Here in this map we are showing the variation of the liquid jet height of for DI water droplet at different impact numbers, and we can see the jetting dynamics are initially similar irrespective of the impact conditions. However, the dynamics of the secondary droplet generation, which is this process, is different, occurs at different time instance. So on the initial portion we will be talking about the singular jetting dynamics, which we have earlier shown that this is occurred due to the air cavity formation, the air cavity collapse, and singular jets are formed. These jets are originally studied by Bartolo et al. As shown previously, and they we can reach a very high velocity up to 14 meter. As in this study we have gone up to 20 meter per second, which is 20 times more than the impact velocity, whereas in Bartolo et al. They have shown they had been able to reach up to 30 meter per second, or 30 times higher than that of the impact velocity. In this paper, we are in this plot we are showing the variation of the jet height velocity, and this corresponds to the columnar jetting regime. Singular jetting regime we have shown earlier, and for three different liquid viscosity corresponding to DIW, glycerol 50 and glycerol 65, we are showing this the variation of the jet velocity. We can see overall the jet velocity decreases with the increase of the impact Weber number. However, in between there are some local maximum are observed, and this corresponds to the transfer of the dynamics from the this cavity formation regime to the capillary wave focusing regime, and then later on due to the splashing. So the difference or the presence of the local maximas ensure that there are different transition regimes, and also which are present for all the liquid viscosities, and also we can see the magnitude of this liquid viscosity mediated jetting is similar in the initial portion for all the liquid viscosities. However, the later portion, this is different. On the other hand, this is the secondary droplet size also initially increases and then decreases with the impact of Weber number, and these are the droplet sizes produced from columnar droplets. And we can see that this jetting map is matches similarly the obtained by Pearson et al. And we can then conclude this. We can devise one regime map based on the jetting dynamics of liquid viscosity, and we show that beyond an Onsenzo number of 0.06, no jetting is observed, which corresponds to this curve of the given by Bartolo et al. In his work. And this jetting dynamics further affects the droplet rebound process, which is very much essential for the heat and mass transfer regimes. And we can see as the impact number increases, the jetting dynamics more prominent, more secondary number droplets, or more number of secondary droplets are generated, and which result in lower coefficients of restitution, which is the mark of this rebound dynamics. So we can see that different type of jets are formed in this study. And we acknowledge Dr. Dipankar Bantopadhyay and the co-authors of Amrish Dalal and Dipankar Basu for this paper. Thank you.
Thank you, Mr. Sharma. So we will take some questions from the audience first. Please raise your hands and we could ask your question. Okay, so let me ask the question. So this topic is very close to my topic, so I am very much interested to say this. So this candle suit used for this super hydrophobic thing is really interesting. So what is the contact angle for this you mentioned?
Yeah, the contact angle is around 161 or 160 degree, but it varies depending on the liquid viscosity. For DI water droplet, it is around 161 degree plus minus 1 degree.
Okay, great. And as I saw in the Reynolds number definition, you have used twice of the radius. Means you have used the diameter to define Reynolds number, and you have used radius to define Weber number.
Yes.
So
Actually,
what was why? Yeah.
No, actually, it's a mistake. It's a mistake in the slide. Actually, I have used radius only to define the non-dimensional numbers.
Okay, fine. And you said there are a few regimes like bouncing, and so for low velocity impact, it is the bouncing you see and the sticky thing you see. Which one do you see for velocity?
This for low velocity, we observe this bouncing regime for all the viscosities.
Okay. So minimum, how much Reynolds number did you go?
I have gone up to Reynolds number 12.
Okay. So you do not see those partial coalescence kind of thing which happens in normal substrate, no?
No.
Okay. That's interesting. And yes, and this air cavity, can you explain why this air cavity is forming for those columnar jet?
So basically air cavity is forming for the singular jet process. So this like when the droplet impacts the superhydrophobic surface, so it spreads to a very larger extent, so that air is entrapped within the droplet. So if this from the side view which we are showing, this formation of this cavity is not possible, but if we take a top view, then it is possible to see that just due to the spreading of the droplet to a greater extent, because there is entrapped air in the bottom of the droplet which get entrapped within the droplet, and this cavity collapses, and the second this singular very high speed jets are formed.
Yeah, and to see those singular jet, it's really difficult as I see through high-speed camera. So are you planning to do some more refinement in the pixel for that?
Yeah, now actually this thing is the camera.
Bhaskar Jyoti as well. So we'll take
Yes.
the next talk.
Yeah. Yes.
Paper number 264 by Dr. Pranab Kumar Mandal, effect of rib structures on the mixing characteristics in a microfluidic channel. Yeah, please start.
In this session, I'm going to present my work on the effect of reef structures on the mixing characteristics in a microfluidic channel. This is the brief outline of my presentation. I will try to discuss the pertinence of this analysis, and then in this area, most important work, those are reported already in the literature. Then what will be the objectives of this analysis? Since this is numerical work, so just I would like to briefly touch upon the theoretical formulation, the numerical methodology, and finally I'd like to discuss the results of this particular analysis, and then the 2 or 3 main conclusions. So here we can see that the objective, rather the topic of this talk, is the effect of restructure on the micromixing analysis. Now question is, when you are talking about mixing in a microfluidic channel, then it is very unlikely that we will have efficient mixing following active methods that we normally see in the domain of macro flows. So we need to go for some other, I can say methods. Rather, we need to focus on some other methods, some other avenues through which we can enhance the mixing in a microfluidic pathways. There are many applications, mostly in the area of biochemical and pathological system, wherein biofluids are taken for their complete analysis, and to do that we need to mix different reagents, and when we are allowing different reagents to mix with the biofluids, at times we need to make sure that the reagent which are being mixed should have proper mixing with the sample which is being transported. So now to ensure in the microfluidic domain, it is, as I was talking about, it is very difficult to have mixing using chaotic environment. That means what is done in the domain, rather in the macro domain. So normally what is done in the context of microflows, mostly if we can if we look at the figure which are shown at the right panel, we can see there are different electrodes, basically which is used in the paradigm of electrokinetically actuated transport. Otherwise different structure which are nowadays possible because the sophisticated fabrication methods available today. These methods are really capable of providing different structure, artificially textured surface, artificially textured, what I can say, different post ribs of desert dimension to be grafted, to be positioned inside the microchannel. So largely used in the point of care diagnostics, that is I was talking about, and micromixing, which is very important in this domain. And as I was talking about, that active mixing like electrokinetic mixing is there. On the other hand, we also need to think about passive mixing, that will enhance even in the paradigm of electrokinetically actuated transport. If we allow this kind of built-in structure inside the microfluidic pathways, these structures will allow to have efficient mixing. Okay, so a quick review of the literature available in this paradigm suggests that these aspects, that is the mixing which is induced, which is initiated in the microdomain using rough structure, using different built-in structure it's not new. So the people have started research, I mean, already. And so I wanted to show that these are, I mean, just the reef structure, microfluidic channel with built-in solid, built-in structure of desired dimension are nowadays possible using this sophisticated microfluidic technique. Okay, so objective is to, I mean, provide different structure of different dimensions and to see how they are really, enhancing the mixing at the cost of resistance to the flow. Because if we, in fact, there is, we know that for the flow through a microfluidic channel, there is a huge pressure drop. Now, in this context, if we allow this, kind of reef structure, that will enhance the, pressure drop further. So another option could be to, enhance the interfacial sleeve, which is not new and which is not really difficult, because there are many, I can say, chemical treatments are nowadays possible. So if we try to make the, surface bit hydrophobic, I mean, then that hydrophobicity may results in with the results in the interfacial sleeve, which in a way will try to reduce the pressure drop. Okay, so the objective in this analysis is to investigate the effect of interfacial sleeve. That means, because why we are providing interfacial sleeve? Because to reduce the flow resistance that will be offered by the reef structure to the flow. So this is the theoretical formulation that we can see that we have considered 3 different types of flow configurations. I mean, only by varying the micro reef structure that we can see. So basically this is the one kind of structure. Then this is the second one where just small reefs are added. I mean, if we look at the first one, there is, I mean, there are reef structure, there are posts which are there. But in the second one, we are also having another small reef structure which are placed in between 2 big structure. And the second one also, I think that is again the first one, but I mean, this is the combination of first and second, where the small reefs which are placed, which is having higher dimension. So these 3 different structure I have taken, and again I'm telling these structures are, nowadays, I mean, it is possible to have this kind of configuration using the fabrication techniques available. Okay, so this is the continuity equation that we had to solve. Then momentum transport equation, we are trying to solve the equation, I mean, steady. So this is the dimensionless momentum transport equation. Then because we are looking for the mixing analysis, so we had to solve the species transport equation. Again, it is written in the dimensionless form. And these are dimensionless term I have considered to make the equation dimensionless. And these 2 dimensionless number, Reynolds number, Peckel number, also defined here. Okay, so what we have given boundary condition at the inlet, that is velocity profile. And for the mixing that we have given, that I mean, there are 2 different stream as if at the lower half and upper half, they are, that is, the C mixing index that was assigned values 0, 1 to denote 2 different stream. And at the wall sleeve and at the outlet gauge pressure 0, that was taken. So numerical method that we have considered in this analysis is that we have used commercial software COMSOL to solve the governing transport equation, and for the relative residual criteria is taken as 10⁻⁶ for the convert to obtain the convert solution. So this is, I'm not going to discuss this part again because this is bit on the numerical analysis part, the number of elements taken to obtain the convert solution, and then mixing analysis. So we have seen that after taking this, M3, I mean the number of elements, the change in mixing efficiency is very small, and that is why we have considered this number throughout this analysis. Okay, so this is before, since this is numerical work, so our objective was to validate. So what we can see that present study, the numerical framework can replicate the experimental results which is reported in the literature quite effectively. So having benchmarked this analysis, now we proceed to present a few results. So what we can see that because of this rough structure, in fact, we have shown here 3 different configuration, that we can see importantly that these vortices are forms. These vortices are in a way responsible to enhance the mixing in the flow domain. Okay, so what we can see that, okay, fine, as I was talking about that these, when you are trying to insert this kind of reef structure inside the flow domain, that will definitely enhance the pressure drop. So to reduce the pressure drop, what we are doing are considering interfacial slip. So we can see that if we increase the slip length, beta represents the dimensionless slip parameter. So now beta 0 represents the no slip condition, while beta non-zero finite value 0.1, which is that indicates that we are having slip. So you can see with increasing the slip length that velocity increases at the middle, also the velocity which is increases where vortices are formed. Okay, so here also we are trying to show the concentration field. So we can see that with a change in slip from no slip condition to the finite slip, the concentration is getting changed, and that is not clearly, I mean, from these two figures, it is really difficult to demarcate the very insignificant change. Probably it is from these two figures, it is apparent that the change is, very insignificant. But when we will be discussing about the efficiency, then it will be clear with a change in slip length, there is a difference in the efficiency. So this is the mixing efficiency we have plotted for different geometry. Different geometries we have considered: model A, model B, model C, and model D. We have considered only to see that there is a plain micro mixer. So basically, what we have calculated efficiency using this formula. What we can see with the increase in slip length, the efficiency increases for all three different cases we have considered. Most important, and that is obviously because with increase in beta, what will happen? That the important question is this recirculation velocity will increase. The vortices when vortices are formed, so there will be a recirculation velocity. So recirculation velocity will increase with the change in slip length, and that enhances the mixing. But in case of a plain micromixer, we see the opposite trend. This is quite obvious because in a plain microchannel with a change in slip length, rather with a slip finite slip, the flow velocity will increase, and that in a way will reduce the retention time of the reagents which are being mixed. So that will reduce the mixing efficiency. So again, we have tried to compare the pressure drop, because as I have mentioned that this artificially textured surface will increase the pressure drop. So we can see that as compared to the plain micromixer, if we try to look at three different models, three different configurations we have considered, the pressure drop increases. Okay, so mixing performance, that was, so now what is important to know is that, okay, with a change in slip length, we are getting higher mixing for three different configurations having leaf structure, but at the same time we are also going to have higher pressure drop. So to check, what is the increment in mixing efficiency at the cost of higher pressure drop, to compare these two different indices, we have defined another important parameter, that is mixing performance. That is nothing but eta by del P. What we can see with increase in Peclet number, mixing performance decreases. That is obvious because Peclet number increases. So basically, that will be higher advection as compared to the diffusion, because mostly in this case that is a diffusion dominated mixing. But what we can see is that with a change in slip length, the mixing performance decreases. Now with a change in slip length, if we increase, then delta P will increase. Why? Because delta P increases, then the mixing efficiency mixing performance will, maybe with a change in slip length, eta increases. That is what we have seen from the previous slide. But at the same time also delta P will increase. So this delta P increment that means the vortex recirculation velocity will increase. Recirculation velocity will increase the mixing efficiency, that is true, but at the same time it also will leads to further resistance to the main flow, and as a result of which pressure drop will increase. So what we can see, the relative increment of pressure drop will be higher as compared to efficiency, which in turn will eventually result in a lesser mixing performance that we can see from this diagram. So if we now go to the conclusion, and that is important, that interfacial slip enhance the recirculation zone strength of the reef microstructure. And then we have seen that mixing efficiency increases with increase in slip length, but it also leads to increment in pressure drop due to the recirculation zones being formed in the fluidic pathways. So we need to consider these two important effects simultaneously while we are looking for the mixing enhancement. So these are the conclusion that I wanted to convey, and a few references that I have given over here. Thank you very much.
Yeah, thank you, Dr. Mandal. So it was a great topic of mixing with different geometries. So very quick question if somebody has, because we're running out of time as I see. If audience have any question, please raise your hand. Okay, so just one quick question is like, Dr. Mandal, have you thought of non-dimensionalizing these different models which you took, models A, B, C? So can you have that it is?
Yeah. Okay. So basically, that is what I have tried to identify that fine, because objectives should be, because if we can play with different structure, different geometry, but at the same time we are also having huge pressure drop. So basically now we need to have a judicial selection. So sites and their configuration should be in such a way that pressure drops we need to compromise, but we need to compromise the pressure drop to the extent possible, because
the speaker is Mr. Kaushik or Dr. Mandal. Yeah, please start.
I'll be presenting our work on analytical framework for a slightly elastic Maxwell fluid, which is squeezed and extruded between two infinite parallel plates. So before going to discuss a few results of this analysis, I would like to discuss that this aspect of classical fluid dynamics, that is the extensional flow dynamics, which finds many applications, I'd say many practical applications, which include pharmaceutical process plant, compression molding processes, and different other bioengineering applications. Now, what we did, we had literature survey, and we found that the existing work on this particular topic mostly considered Newtonian fluid for the analysis. Also, sometimes they have, in fact, in some cases, researchers have considered non-Newtonian fluid, but they didn't consider effect of elasticity. But the different areas that we have found, like pharmaceutical process plant, compression molding processes, where this extensional flow dynamics is an important topic of the research. The working fluid is non-Newtonian in nature. To be precise, in some cases working fluid is non-Newtonian fluid having elasticity. So to understand the effect of elasticity on the extensional flow dynamics. Okay, so here I am going to briefly discuss about the physical problem that we have considered. So you can see from the schematic depiction is that a slightly elastic Maxwell fluid, which is there in between two parallel plates, while the top plate is having downward movements with a velocity v, while the bottom plate is having axial movement with a velocity u. Now the coordinate axis, the coordinate system is chosen that the x-axis, is in the direction, of the parallel, rather x-axis is the parallel to the plates, while the y-axis is taken along the perpendicular direction. What we assume that the most important assumptions that we have considered for this analysis is that the plate, length of the plates is very large compared to the height, compared to the gap between two plates, and also the top plate, the top wall, in this particular case we have given name, the top plate is moving almost quasi-statically, and that is, we have given the name squeezing. And since the analysis is valid for a case wherein the length of the plate should be much higher than the gap between two plates, that is L much greater than H, and we are invoking the concept of lubrication approximation to solve the transport equation, essentially towards obtaining the velocity distribution in the flow field. Okay, we also have considered that the fluid is free from any stresses initially. That is very important. And also the fluid properties do not have dependency on the temperature. Okay. So the work is analytical as the name suggests, because in the beginning, the name of the topic is analytical framework. So what we have tried, in the framework of lubrication approximation, we have tried to solve the transport equations. So the transport equation governing the fluid dynamics for the present analysis is the x momentum and y momentum equations. So if we now try to look at the equations which are shown, at the left panel of this slide, top one and these two equations. This is the x momentum equation, this is the y momentum equations, and there are two other equations relating the stress. So the other stress equations. Now, considering the stress equation into the momentum equation and using this dimensionless parameter, we have used a reference parameter to make the velocities and length scales dimensionless. So that is, we have used, this is extrusion velocity u to make u velocity dimensionless, squeezing velocity v to make v velocity dimensionless. Similarly, these are the dimensionless, these are the length scale which are used to make the coordinate system dimensionless, and this is the time scale. Now, using this dimensionless parameter, we get this dimensionless equation. And for the solution, we have considered initial solution where there is no flow initially. There is no stress, because that is what I was talking about. Fluids are free from stresses initially, and this is the boundary conditions, because at t greater than 0 at y equal to 0, there is no penetration condition. V is equal to 0, no penetration, and also at t greater than 0 at y equal to 1, u is equal to 0. That is no slip condition. Okay, so using this initial and boundary conditions, we have solved the transport equation which are shown here, in the right panel, and we have tried to obtain the solution in an analytical framework. For that, what we did, we have considered, and we can see that the elasticity number is coming here. That is nothing but lambda eta by rho square, where lambda is the relaxation time scale. So this elasticity number indicates that their elastic effect is there in the flow dynamics. Now, we have considered elasticity number should be very small throughout the present studies. That is why the name we have given slightly, elastic Maxwell fluid. So to obtain the exact solution, what we did, we have decomposed the velocity in a solution in two different parts, one is steady and unsteady part. So, and that we can see from these two equations. And the steady part solutions are given over here, while the unsteady part solution we have considered, we have obtained in a series solution, while different coefficients are listed down over here. I'm not going to discuss in detail about the solution method, because these are not very difficult things. Our objective was to capture the physics, to capture the effect of elasticity on the fluid dynamics. Okay, so here I'd like to show a few important results which we have obtained from this analysis. Is that now if we try to look at, there are two figures I have shown over here. The left panel figure is showing the variation of y versus u, that is the extrusional flow velocity, while the right panel figure shows the y varies as v, that is the velocity of v velocity variation within the flow field, that is the u velocity variation within the flow field. Now, these two figures are obtained for the elasticity number which is very small. Okay, what we can see from this figure is that, when t is very small, 10 power minus 2, then we can see that effect of, I can see that the effects of extrusion, at y equal to 1, that is the top plate which is region near to the top plate. So effect of extrusion is not being felt in the region which is very close to the top plate. But as time progresses, because of this viscosity, that is the there are two important effects. One is the viscous effect, other is the elastic effect. Viscosity will try to diffuse the momentum. Now, in this particular case, the elasticity will try to elasticity will respond, but it will create resistance against the response. Now, what we can see as the time progresses, we will definitely get a quasi-steady state. That is what we can see from this figure. Similarly, we can see from the right panel figure that, as the time progresses, the effect of the squeezing effect is slowly, getting percolated into the entire flow domain. Okay. Now here, another important figure, that is what I'd like to discuss, is that, here we have shown the, distribution of u and v velocity within the flow domain, but here we have considered 3 different values of elasticity number, which includes, elasticity number also equal to 0. So this special case we have considered to indicate, rather to, demarcate the difference between slightly elastic and the Newtonian fluid. Here, elasticity number 0, which denotes the Newtonian fluid, while the non-zero finite value of elasticity number that we have considered signifies the fluid, rather elastic effect, viscoelastic effect. So what we can see from this figure is that, in fact, if we try to look at the zoomed in part, rather which are given at in the inset of these 2 figures, what we can see that, for the non-zero finite value of elasticity number, right? So it takes some finite amount of time for the diffusion. So basically, this is definitely due to the elastic effect. So the elastic effects, it takes certain amount of time to respond against the external disturbances, right? So here, if we talk about in this particular case, there are 2 different types of disturbances which are, perturbing the flow domain. One is the squeezing, other is the extrusion. Now, the elastic effect, which takes, because of this elastic effect, the fluid takes certain amount of time to respond against the external disturbances, and that is why, which we can see from these 2 figures. Similarly, if we look at the figure which is shown at the right panel, we also see that for the non-zero finite value of elasticity number, still we can see that the fluid takes certain amount, rather some time to respond against the disturbances, and that is because of this elasticity effect. Okay, so basically, these 2 figures are obtained at time t is equal to 0.05, that is shown at the bottom of the slide. So if we try to, the conclusion, what we'd like to discuss is that this analysis is done considering the simultaneous effect of squeezing and extrusion, which find many applications in different practical scenarios. And we also have considered the effect of transiences. So this is not the steady case. So we have tried to understand what, this coupling between elasticity and the unsteady effect. So what we can see that the v velocity reaches at steady state faster as compared to the u velocity, which is due to the effect of normal stress of the axial fluid, and which is twice as strong as the shear stress developed in the flow field. And that means if we try to look at the slide where we have discussed about the stress equation, where it is clear that, the normal stress, which is twice as of the shear stress, and because of that, v velocity will be reaching faster steady state and as compared to the u velocity. And also the time taken to reach the quasi-steady state is strong function of elasticity number, and that is what we have discussed, just minutes back. And with increasing the magnitude of elasticity number, there is a larger lag in both the effects of the extrusion and squeezing being felt within the flow domain, and that is of course due to the elastic effect of the fluid. Okay, so these are the references we have listed down over here, pertinent references. Thank you very much for your presence to complete this presentation.
Thank you, Dr. Mandal. So if we have any question, just a quick one question we could take, because we already are 15 minutes late. Yeah, so I think we do not have. So just one small question, very quick. So Dr. Mandal, have you not considered the viscosity of the fluid? Only the elasticity is considered?
Yeah, because of fluid we have considered viscoelastic.
Yeah. So viscosity also plays role when you are changing the elastic number?
No. That is the question because of course, because when you are considering elastic effect, viscosity also is playing a role. So that we try to see that we are having two different disturbances, that is squeezing and extrusion. So the effect of disturbance will be percolated to the flow domain because of the viscous diffusion. Okay. So now the elasticity will try to resist that diffusion. It will take certain amount of time. Only then it will try to resist. So that is what our objective was to find out.
Okay. So it's this kind of counteracting kind of.
Yes. Okay. So viscosity will definitely try to diffuse the momentum quickly as the perturbations are created, while because of the elastic effect, it will be delayed.
Yeah. Thank you, Dr. Mandal. It was a little really enlightening kind of talk, and we finished this session. So thank you, everyone. So I will hand over to the organizer, and thank you.
We thank you, Professor Banire, to chair the session. Thank you, everyone. Now we will be having one plenary session by Professor Durst. I request everyone to please join that.
Thank you very much. So I appreciate actually participants or presenters. They have quickly actually finished their thing and make up the thing basically at this moment. Thank you all.
Thank you, sir.
Thank you very much.
Thank you
very much, Professor.
Okay,
Thank you.
So then I'm leaving. Okay.
Okay. Thank you, sir. Good morning. Hello, Professor Talukdar.
Good morning. Good morning.
Good morning. So can we start the session of Professor Drush?
Yes, I'm ready.
Okay, sir, you can introduce about Professor Drush, then we'll start the video.
Sure. Good morning, everyone. A very hearty welcome to Professor Drust, organizers and participants of FMFP. It gives me immense pleasure to introduce Professor Drust and sharing this session of FMFP. Thanks, Professor Dalal, for giving me this opportunity to share this session of Professor Drust. It's not easy for me to introduce Professor Drust with a few sentences. I met him back in 2002 at IIT Guwahati, just in front of the guest house, which was used temporarily as a conference hall at that time. I came to know about this person a lot when I worked with him at his institute for a longer period of time. He headed this institute of fluid mechanics with more than 80 staff, out of which probably about 50 plus people were basically PhD students, postdocs, and many guest professors. More interestingly, there were always a lot of Indians in his institute at any point of time. If you see any of the old IITs in India, you'll find at least 2-3 faculty who worked with Professor Drust at some point of time. If you see, he's a professor full of ideas, full of enthusiasm, extremely hardworking,
and one of the renowned person in fluid mechanics in Europe. A brief bio about him. Professor Just studied aeronautical engineering at the Technical University of Stuttgart in Germany and completed his MSc and PhD degree at the Imperial College of the University of London. Afterwards, he worked as a special research center at the Technical University of Karlsruhe, Germany, before he became a full professor at the University of Erlangen-Nuremberg, also which is in Germany. After retirement in 2007, he opened up his own company, FMP Technology, as a CEO, where he is still active. He continued there his research work in fields like laser Doppler anemometry, laminar and turbulent flows, extended Navier-Stokes equations, microchannel flows, coating and drying equipment, etc. For his work, he obtained various national and international prizes and is a member of 5 scientific academies. I request Professor Drust to start his lecture, which is solutions of some unresolved problems of fluid mechanics. Professor Drust, please.
Thank you. Good morning, everybody. Welcome to my presentation on solutions to some unsolved problems of fluid mechanics. I'm glad you could come. Usually I see in the audience whom I am talking to. That's now not possible, but I hope that quite some people will listen to this presentation. Let me start out to thank Professor Dalal and the organizing committee to invite me to this presentation. And I was hoping that I can use the conference as an excuse to visit India once more and meet many friends here who usually come to this meeting. Let me now briefly explain what I mean with solutions and unsolved problems. But before I do this, let me show you some historical picture here. I have drawn here on this picture the names of the various contributors to fluid mechanics. As you can see, it is quite a number of people who have contributed to the development of fluid mechanics. Usually we start out with Leonardo da Vinci, up here, and go then down through Bernoulli, through Euler, through Laplace. But I think the major contributions and the ones most important for my presentations is Navier and over here Stokes. They derived the Navier-Stokes equations, and we are using them these days for getting solutions to fluid mechanics problems. I'm asking whether they are really problems. Are they not just tasks which we can now solve with these equations, and we can solve them with numerical methods, analytical methods, and experimental methods? We are in this time now, where the necessary methods for measurements, methods for computations have been developed. The golden age of fluid mechanics exists, but as you will see, there are still some problems we cannot solve properly in fluid mechanics. Let me start out to explain the kind of problems I would like to tackle, at least to introduce you to some ideas about these problems. A problem does, in my opinion, not exist if you can solve it analytically, if you can solve it numerically, or investigate it experimentally. That is a fluid mechanics task, and we can get a solution by these methods we have available and the suitable equations or the test equipment. But a real problem is in fluid mechanics if we get theoretical solutions by solving the Navier-Stokes equations here, the continuity equations and the energy equation. And if you then investigate the flow experimentally, and there is a difference. And now you have to decide what is the problem. You have two solutions. Both solutions are correct, but there is a difference. That are the kind of fluid mechanics problems I would like to talk about. Here now, one of these problems, micro-channel or micro-capillary flows. Here you see on the left-hand side, the results of Maurer for mass flow measurements, the mass flow through the microchannel. Theoretically, solving the Navier-Stokes equation, we get this solution, a parabolic velocity profile. If you go to smaller and smaller channels, and of course, higher and higher pressure differences, as you can see here, you find you get a difference between the solution to the Navier-Stokes equations and the measurements. This is now the kind of problem we have. And of course, we can not solve this problem really by modeling, because we would have to model the molecular interaction with its rough surface. So here is now the kind of problem I think we have and we need to solve somehow. You get a higher mass flow rate through a small channel than you should get solving the Navier-Stokes equations. Now, very often we think this is a microchannel flow problem particular to this flow. This is not the case. Have a look here. There is no channel. You have an obstacle in a supersonic flow, and you get a shock. And this shock wave, as it's called, has now an ideal solution, which is this line here. So the pressure, the density in this case, changes at this location. Experimentally, you find a change given by these points. And the line is the solution coming from the Navier-Stokes equations. The difference is there between experiments and theoretical solutions of the equations. And of course, now we have the kind of problem we would like to solve. There is a third problem I've indicated. This is a flow through a pipe. The flow is turbulent and it is heated from the wall. You can see this from the temperature distribution. Of course, as you go downstream, what you have is the velocity U increases because of the expansion of the flow, and also the temperature increases because the flow is heated from the walls. And again, you see now the theoretical solution and the experimental findings disagree. Of course, here now it can be that the K epsilon equation is incorrect, but some hints are also there that we have a similar problem to microchannel flows, and this is what I would like to explain to you. Have now a look at the equations. See if the equations, the predictions are not agreeing with the experiments, and we have the initial conditions and also the boundary conditions correct, then there must be a defect in these equations. And this I would like to point out. Let us start out with the Navier-Stokes equation. You have here on the right-hand side, you have the molecular transport of momentum. Don't call it friction. It is the transport of molecules of momentum. Similarly, you have in the energy equation the molecular transport of heat, of energy. But have a look at the equation here of the mass. There is no molecular mass transport in these basic equations of fluid mechanics. This is the major reason why we get these defects in some of the flows. Some of them I have indicated. So with a conventional Navier-Stokes equation, we have no mass diffusion. And if we now introduce this mass diffusion, we get the extended Navier-Stokes equations. And I will use these shortenings here to explain which kind of equations I'm using. Here now, the explanation for the missing term of diffusive mass transport, so molecular mass transport. Have a look at this checked area. Through this checked area, this can be the area of a cube. Through this checked area, you will find that molecular motions will transport mass. So there's a mass transport from here to through the checked area. It's indicated at that point. The last time the molecules interact with other molecules is one mean free path away from the checked area. So then the properties um and rho at this location are transported up. There's also a transport of the molecules down through from this upper area. And this is now that combination of properties that enters the mass transport by molecules. Minus if the transport is downwards, plus if the transport is upwards. is given here for. You can now take series expansion, and then you will end up with these terms. And you can now build the products between these terms, and when two terms are different, have these difference operators in them, we take them out, being smaller than the terms that consist of these terms here, or combinations of one term with a gradient. At the end, you end up with this mass transport by the molecules. And you can see it depends on the mean molecular velocity and the mean velocity of the molecules and the gradient of density, or the density and the gradient of the velocity. So you end up with this equation. Now you can use the ideal gas law and get now the correct derivations here, expressed once in density and temperature and once in pressure and temperature. Outcome two term, this is fixed mass diffusion term. And then the temperature term here is Sore's mass diffusion term. So both terms are known, for example, in physical chemistry, and they are used there, but we are not using them in the mass transport equations of fluid mechanics. If there is mass transport, there is also energy transport, heat transport. So we can now do the same thing. There is heat transport from the bottom, there is heat transport from the top, and this is the top one down, and this is the bottom one up. And you can again take the difference, and then you get the diffusive transport of heat by molecules. Again, you can now derive this expression, and you might see that this is the mass transport, and multiplied by Cp times T gives you now the additional heat transport there is. This heat transport comes from the mass transport, which we are missing in the in the mass transport equation. And at the end, you get an expression here for the ideal gas, and you can do it also for the ideal liquid, as I show later on. As the last term, we have the transport of momentum. Here you can see the transport of momentum we usually have. It's this frame one. And then you have now again, due to the mass transport, which we are missing in the continuity equation, times uj and ui, that are the momentum transport terms that you get additionally in the Navier-Stokes equation. So we have different equations, and they are now shown here. And you can, they are very similar, but in this velocity, you have now the convective velocity and the diffusive velocity. Here also. And this is now the tau Ig term, which is also expressed in terms of total velocity. If you now put in the ideal gas law, you get this equation. And then you end up with a full set of equations you can also solve, but for total velocity, you get the convective and the diffusive velocity. That's the diffusive part, or this is the diffusive. For an ideal liquid, this is the equation. The T here should be an Xi, so I'm sorry for this. Now, let's take now this extended Navier-Stokes equations and solve it for microchannel flows. What you get now is this solution for the pressure difference Maurer used. And if you now do the computation for that pressure difference, you see that the numerical solution goes, also the analytical solution, which is possible here, goes directly through the data of Maurer. We do not need any modeling. We do not need to take care of this complex structure of the wall in order to get slip flows introduced. I can also not imagine how you can deduce slip flows from this kind of a rough wall interacting with molecules. Now, let's look at the shock wave. Here you see the Navier-Stokes equations. That's the ideal gas without any viscosity, you would lie here. Then if you take the solution by the conventional Navier-Stokes equation, you end up with this line. So there's a difference between the experimental results and this numerical solutions to solve shock waves. Of course, you can now model again what I have done here with a combination, but you don't make it quite. But if you now solve the extended Navier-Stokes equations, the line goes straight through the experimental results of Maurer. Here now let's look at the turbulent case. The dark points are the numerical solution with a classical K omega model. The points here, the circles, these large circles, are the experimental results. And if you now take the extended equations and you solve it with the K omega equation, you get some improvement. Of course, it's not perfect. Part of this might be due to the modeling of the K omega equation, which is the conventional one, and it should possibly be modified to when you use the extended Navier-Stokes equations. Nevertheless, you get an improvement, and more work is needed in this field in order to see how one can get better predictions when high temperature gradients exist in heated pipe flow. Let me now come to a second problem. In the first problem, basically, there was a defect in the Navier-Stokes equations, and I explained this, and I showed that you can overcome this defect. We can extend these equations. I'd say, why did nobody else find this? The reason is, in my opinion, quite simple. We have a tendency to believe these equations and then find outside of the equation reasons for the discrepancies, which I have shown you on microchannels, channel flows, on supersonic flows, and strongly heated flows. The other problem I would like to tackle is indicated here. It's the laminar pipe flow. Here you see the pipe. Inside of the pipe, you see parabolic velocity profiles. And we know from many theoretical investigations that these parabolic velocity profiles are inherently stable. So you can knock them, but the viscosity will damp this disturbance out. An excellent summary of the existing work is provided by Schlichting. And if you look at this work and also some additional publications in the literature, you get these results. On this side, you get the critical Reynolds number, and at the bottom, you have the diameter of the pipe. And you can see there is not a single critical Reynolds number coming out, but a whole set of Reynolds numbers. And you also find the bigger the pipe, the higher the critical Reynolds number you can get. So if you want high Reynolds number, stable laminar pipes to be investigated, take big pipes. Of course, then you need big blowers and you need all kind of big apparatus. But nevertheless, this is what the literature presents. Now, why is this so? So there is definitely a discrepancy between the theoretical results here and the experimental findings. So we have a problem in the sense I have said I will consider them in this presentation. Here now, once again, what do we compare? We compare a pipe flow, which is infinitely long in the theoretical treatments. It has a set parabolic profile. And now we disturb this velocity profiles and the disturbances are damped away. And we compare this with a blower, which provides the flow through this test rig. It has some flow control, a diffuser, plenum, chamber, and nozzle. And then it has a long pipe, and the length is different from one experiment to the other. There's also equipment, measuring equipment, associated with this test rig, and we blow this air into a laboratory of different size. The laboratory walls are indicated here, and it's quite clear the differences which you have just seen here in Reynolds number come from these differences in the test equipment employed by the different investigators. Let us have a look at the cause of these differences. I start out with a blower. This is a blower which you have on one side of the test rig, here, and it provides the flow through the pipe. Now, what property must this blower have to get the laminar to turbulent transition of pipe flow investigated? Here you see the friction factor of this blower is going down. At the point where the transition occurs, the friction in the pipe must go up. And this, of course, there's no means to do this. So basically, you can expect flow jumps. It finds now out it should increase the pressure, but this blower cannot do this for this flow rate. So it will go back, and at the end, you get all kinds of disturbed flow, but not the kind of disturbance you would like to have to go from this low point here up to the upper point. This is now the result. You have a laminar flow, and if you now increase the velocity by increasing the power output of the blower, you find that the flow finds, well, I should go turbulent. But then the conditions of the blower are not there to do this, so it jumps back. And this happens, and basically you get these kind of flow phenomena that are called in the literature slugs. Puffs are also there. They have a very similar behavior. Now, if you want now to study what really happens here, you must build up a test rig of this kind. In this case, we are using here a mass flow controller. So this mass flow controller can allow us to blow out air, and you use the increase on the high pressure side, the increase of the pressure, to increase the flow rate here. In this case, it is a slow process, as slow as our blower. You can, however, have another means to control this mass that is faster, so it can react very fast to the requested change in pressure or in flow rate. That's the plenum chamber. I will say something about that plenum chamber. And here you have an iris diaphragm where you can disturb the flow. We know if you don't disturb the flow, it will not turn turbulent. So since we want to study transition to turbulence, we must have some kind of a disturbance here. We have chosen this iris diaphragm to get the disturbance generated. It's automatically controlled, so you can close it, so put in a disturbance, remove the disturbance, and in this way get short disturbance, and we can see how these grow in the pipe. We used pipe between 0.5 and 8 meter in length, giving us longer times to observe these disturbance-caused flow disturbances. Everything was controlled by a computer, and we recorded everything and evaluated the data afterwards. And here's now the test rig. The test rig is, here is the test rig is quite normal apart from this disturbance element here. So what you now see is this mass flow controller. This I would like to explain here. The flow goes in the test rig here. In these sketches, I have drawn it in this direction. You have here a 3 millimeter closed ball, and this ball can be opened so that a pressure increase or a pressure can be used here to get force flow in this direction. If you increase this pressure, more flows goes. And this mass flow rate is now depending on this pressure change. If you change pressure, it is a slow change of mass flow rate. However, this mass flow controller can also be operated by changing the position of this ball. This ball is the same as here. So if you now leave this pressure constant, you can open and close this fast and therefore control the mass flow rate by this area change. And this allows us now to see what the blower or the airflow generator is causing in terms of transition. Now, this is what happens. You open and close this device, and then this disturbance grows, and I show it here for the 8 meter long pipe. Over the distance, here you open and closed the, let's say this iris diaphragm, and then afterwards the flow or let's say the flow grows in length, and at this point it leaves the pipe. So we only measure at the end of the pipe, and then it leaves the pipe. Before and after, the flow stays laminar in spite of these disturbances. So the laminar flow is there for the parabolic velocity profile, but there is a region where we can force the flow to become turbulent. Why that is so, I explain in a moment. Now, here is this length growth indicated. 8 meter, here you have triggered the flow. This is now the turbulent region. Here you close, not you close, here the flow leaves the pipe, and of course the flow afterwards is then laminar again. Very structured turbulent flows. It's very repeatable. This flow has about 20 trials, so 20 slugs, very precisely generated, very precisely observed, and they lie over each other. What you can also see is here, the front part of the pipe grows faster. The back part grows smaller, and this velocity difference is the reason for this growth of slug flows. So you can study turbulent flows in a well-controlled manner. Now let us have a look at some other situation. In this case, we have used the mass flow control system like this blower, and we obtained the kind of flows we knew from our pipe flow, but well controlled. In the other case now, which I would like to study, I use now here the fast change possibility of our air supply device. And I look now, in this particular case, at a plenum chamber. These plenum chambers have a tendency to oscillate. I've taken the results of Maura. I've written the results of Maura, and I've looked at the oscillations he measured. These plenum chambers with pipes going out behave like Helmholtz resonators. So they oscillate, as indicated here. And this oscillation depends on the length of the pipe, on the pipe diameter, on the shape of the plenum chamber. Everything influences it. If that frequency agrees with the mean velocity divided by 2 times the pipe length, you get a resonant. And it is now this resonance that controls your flow. This is what we have investigated and what we have measured. Here you can see now what you can produce with this test rig. If you run the flow now with this fast change in flow rate device, you get a completely different critical Reynolds number distribution than if you run it in terms of high pressure with a high pressure device. So this explains why you can have different results as you have them in the literature. Nevertheless, all literature uses blowers, or they use mass flow control systems, but the mass control systems are used very similar to the blower. So that's why all the data in the literature look alike. The highest critical Reynolds number we found is that of Fedinger. He used about 50 millimeter pipe, and the critical Reynolds number was measured to be about 1,000. In our case, when we run now the critical, the mass flow controller by that small ball, what you find out is you get 100,000, or you should get 100,000 if you run it with a fast control. But apparently at this Reynolds number, we already trigger some other device. So we could get this 100,000, but for some reasons, sometime later, it jumped down to a smaller value. It never jumped back again. So when you had once this critical Reynolds number adjusted, it would not go back. Nevertheless, it is interesting that you can manipulate the laminar to turbulent transition, the critical Reynolds number, by changing the blower, if you want, in this particular way. What do you now get? Here you see we have a critical Reynolds number of 7,000. That's what you get if you run this test rig with the pressure device to control the flow rate. If you now increase the flow rate, it jumps up and you get puffs and slugs. If you now use this ball bearing to encross the ball to control the flow rate, you get now oscillations. And these oscillations are fantastic, but the flow never turns turbulent. It oscillates and it stays turbulent until it catches sometimes another mechanism that turns the device turbulent. Look also at the Reynolds numbers. Before we had Reynolds numbers of 5,000 to 8,000. Now we have Reynolds numbers here of 53,000 to 41,000. And you see, sometimes you can drive that flow in a laminar oscillating manner into up to Reynolds number of 60,000. And then when you try to adjust it again, coming from the upper side, it only goes to 53,000. Nevertheless, with these fast changes, you can keep flows laminar, but oscillating, of course, up to 50,000. Let me now come to an end. I started out by explaining that the Navier-Stokes equations, the Navier-Stokes equations, the continuity equation, and the energy equation have a defect. This defect comes from the mass transport equation. There you can see 0, 0 on the right-hand side. On this case, you have on the right-hand side a molecular transport of momentum, a molecular transport of energy, but we have no molecular transport of mass. This is also the reasons that you can see in some of the textbooks on heat and mass transfer, that the heat transfer section has, let's say, 400 pages, and the mass transfer section has 50 pages. Why? There is no mass transfer. And this is, I think, a defect that we need to eliminate. I've done this for the extended Navier-Stokes equations, and I could see that discrepancies for microchannel flows can be eliminated. Discrepancies for shock waves can be discriminated. And discrepancies, or if you want, problems for heat transfer in turbulent pipe flows could be at least improved. Here are now, for these conventional equations, conventional form of the basic equation of fluid mechanics, the diffusion terms, no mass diffusion. The Fourier term represents the heat transport, and this is the Newton, the molecular transport term for momentum for Newtonian fluids. This is wrong, at least for laminar, this is wrong for ideal gas flows. If you take ideal gas flows, you can derive these terms. And this MI is now introduced on the continuity equation, where on the right-hand side it was 0. This term also influences the heat transport. It influences the momentum transport. And if you put these diffusion terms into the basic fluid mechanics equations and you solve them, some of these equations that cause problems these days, the problems are eliminated. If you now look at microchannel flows, which I started out with, you can now see that the world is more perfect now. Down here, above Knudsen number 1, we have molecular dimensions in our flow cases. Down here, we are quite some distance away from molecular dimensions. And we are still using nowadays the, let's say, methods of modeling in order to get agreement, although molecular dimensions are not in place yet. This is not the case if you use here the extended Navier-Stokes equations, and as I have shown, you can get a good agreement. So my suggestion is to use extended Navier-Stokes equations, at least in those cases where you have high pressure and high temperature gradients. I hope I could show you that the Navier-Stokes equations require extensions. Introduce them when necessary and get good results. Thank you very much. Good morning, everybody.
Thank you, Professor Drust. It's quite an interesting discussions of extended Navier-Stokes equation. Basically, to summarize, you have considered 3 different things. One is like the flow through microchannel, where conventional Navier-Stokes equation doesn't work. Then when there is a transition from laminar to turbulent flow, then also the Navier-Stokes doesn't work, and of course with the shock wave. So before, and of course there is one interesting thing is that in application, in books of heat transfer, as you were mentioning, that if there are 400 pages, there are only 20 pages per mass transfer. Even in our lectures also, we do the same thing. We have 40 lectures in heat transfer and finally 2 lectures in mass transfer. So that tradition still continues now also. I think before I ask you something, I'll take it to the audience because there will be more enthusiastic people in the audience to ask you a few questions. Please go ahead if somebody have any questions to Professor Drust.
Hi, I'm Shraman here. I have a question. The extended Navier-Stokes equation for the mass diffusion, you have a term for temperature. So how does that play a role? Density, I can imagine something, but for the temperature, how does that play a role in terms of mass diffusion?
You know that the molecular motion, the velocity of the molecules, depend on the temperature. So what you have, if you have a temperature gradient, you have on one side of that checked surface I have shown, you have a higher velocity, because the temperature is in the velocity term, and you have a lower velocity just on the top of that checked surface, and that gives you differences in the velocities in the molecules, and if you enter that into the equations, you get this temperature term. This temperature term is the reason why you have Sorey heat transport in fluids.
Okay, so is that equation derived from kinematic theory of molecules, kind of?
I started out with the Boltzmann equations, and I integrated and did all the kind of situations or all the kind of derivations, and at the end I did not understand what physically happens. Then I went back and I used mean velocity, molecular velocity considerations, and I got the same results. So what I have shown you is not the treatment of each individual molecule, but the treatment of the mean motion of the molecules, and it comes out perfectly. You get all the terms right. And if you look at the equations for Sorey, you also see you get the Sorey diffusion coefficient, which is amazing.
Yeah, thanks. It has been a very nice to go through your presentation. Thank you so much, Professor.
Good afternoon, sir. My name is Saroj Kumar Panda. I am a researcher in Department of Atomic Energy, Government of India. So we used to talk, my supervisor used to talk about you and your work many times during my PhD in IIT Delhi. So so it's a dream come true seeing you, listening you in a live session. So my query is, many times we generate experimental results, and also we generate predictor results from simulations. So sometimes we call it, it's a good result. Agreement is very good, and sometimes we call it as agreement is poor. So my query is, what basis we are judging it actually? Is there any parameter to judging it actually? Because that question is there in my mind since years. And what percentage error is acceptable, sir?
You see, the situation, if you do numerical calculations, presumably that's what you have done. Yeah. Now you get some additional things in. That is the accuracy of your numerical computation. So you get numerical errors coming in addition. So you first have to make sure that you get good numerical results with sufficient agreement, let's see, with the sufficient or accepted errors. And now what is accepted, that's very much depending on yourself. If you have a lot of money and time, you can get very precise computations. If that is not the case, sometimes in industrial computations that's the case, then you have to accept somewhat less good results. Now, there are two things. One thing is definitely the case. You can look at these ingots, which I have given here in the equations. And then what you can put in is your numerical results because you know your gradients. And if n dot comes out to be small, then you're sure you're not having these effects I was talking about. So that's possibly one way to see how good your computational results are in comparison to the real solution using the extended Navier-Stokes equations.
Okay, sir. Thank you, sir.
You see that sometimes when I came out with these extended Navier-Stokes equations, I got very much criticized, and I took the attitude, well, criticize. I know that these derivations are right, and if you don't accept them, then that's your business and not mine. Then I found out, however, that we have a lot of very good students doing their PhD with us in fluid mechanics, and we should point out this shortcoming of the existing Navier-Stokes equations and ask them to look into it. And I'm sure then people will find out that possibly, or clever people will then contribute to this and get this topic further. Okay. Important to me is also the second case, the laminar to turbulent transition. Basically, what I've shown there, it cannot be that we have the Navier-Stokes equations and let's say a set parabolic velocity profile, and we predict inherent stability.
Okay.
And then in the experimental case, we get turbulence. Now, why is that so? The turbulence comes from the equipment and not from the laminar profile in the pipe. I think this is also a topic one should put some clever students on it and see what comes out.
Okay, sir. Thank you so much, sir. Thank you.
Is there any more questions from audience? Professor Viswas.
Good morning, Professor Dorst. It was really, a delight to meet you again, although not physically through virtual media. I think Professor Wang is also present in the audience. Anbang Wang. This is really not a question, maybe in the form of discussion. This formation of slugs and plugs in transition, this is a very well-known classical problem started with Professor Rota, and probably it was concluded by you through your students and through very good publications. My point is that this slug formation and plug formation and this part of transition, this has really the paradigm where inherent disturbances come from ambience. Like this happened in the case of, if we go by the classical experiment of Professor Reynolds, Osborne Reynolds, that in the Cavendish lab, when he used to do experiments in the night, he used to get transition around 3,000, 4,000 Reynolds number, and in the day, and in the night, the transition used to take place. Flow used to be stable even for Reynolds number of 8,000 or 10,000. He got once 10,000. So basically, the disturbances that come from instruments, that come from surface, that comes from disturbances that come from surroundings, those disturbances can create a difference. But finally, that transition again, we get back to the laminar regime if the kinetic energy is not sufficient to support the disturbances. And this was very nicely done through this, almost like a super pipe you used, and I know all the equipment used there. Even this disturbance was created by this aperture controlling this aperture of the disturbances. Fraction of a second, it created disturbances and it went out. But with all this, I'm just, what I'm trying to say, that probably this has no apparent connection with the modification of Navier-Stokes equations that is proposed.
I agree with you. The second problem has nothing to do with the first part. So I did not use the extended Navier-Stokes equations because I had felt what we are studying there has nothing to do with strong pressure gradients and strong temperature gradients, but it has to do with the equipment we apply. And we should be clear, I always didn't say this, turbulence is a question of the equipment we use and not so much of the jet we are studying or of the pipe flow we are studying. It is the equipment we have to drive the flow cannot do what the transition requires. That's basically the message of the second part. Right. So turbulence, we are trying to look at the local phenomena in a pipe, and it is driven by the blower in the back. This is, in my opinion, something we should look closer at in future investigations.
Absolutely correct. And probably I can add something, that the pipe which you used is really a super pipe. Its manufacturing accuracy is absolutely amazing. And that is why this just the elimination of creation, puffs and slugs were possible, and it could be shown that it comes from the artificial disturbance that was created at the entry.
Yes, yes. I should mention Professor Pishwas was also involved in some of these investigations. Quite a number of people I did not mention here. I had one slide where I had all given them, but to get this lecture here recorded was quite something. And at the end, we had to take it out because even in the third trial to get a good presentation going, it didn't work.
No, that is not the point. But point is really, having such accurate equipment like the pipe you used and your historical experiment of this backward facing step. They are also the accuracy of the positional accuracy, dimensional accuracy is really amazing, and it is to be appreciated for the years to come. Creating such absolutely accurate test facility, it is probably not possible anywhere and everywhere. It was only possible in under your tutelage in LSTM. I do not know whether such equipment can be given to or this are being used by others, or it should be continued such accurate equipment.
Now we're just standing around doing nothing, which is a pity. Yeah.
Thank you, Professor Durst. Thank you.
Thank you also. Thanks for the last word.
And let me also tell to the audience that Professor Durst, all of us can wish him for belated happy birthday. No.
Yes, thank you.
Belated happy birthday.
Happy birthday, Professor Durst.
Thank you.
Professor Dalal, you have some question.
I don't have any question. Just thank you, Professor Durst, for the wonderful lecture. I would request Professor Biswas to switch on the video, so it will be nice.
Okay.
Sorry.
I thought that I know the bandwidth problem. Okay.
Yes, yes. Now it is looking fine. And also, I request Professor Wang to switch on the video. Then it will be very good.
You are muted.
Professor Talukdar, you please go ahead. Professor Talukdar.
Yeah, yeah. No, I have a simple question because I work in heat transfer. So by using extended Navier-Stokes equation, will there be a change in Nusselt number at the fully developed regime?
Ask you again. You are using the extended equation, and in which case you are asking you get the same results?
For example, in a microchannel, if I apply an extended Navier-Stokes equation where you have a mass diffusion, so will it increase the Nusselt number compared to a conventional Navier-Stokes equation?
It depends. It will. It will, because what you have is now you have also let's say if you do not have any strong temperature gradients, then it will only through the pressure term increase the transport. If you have now the temperature and you have, let's say, if you have a high pressure gradient but a small temperature difference, you will have a higher number because of but it's driven by the pressure gradient. If you now have a very strong temperature gradient, you get an additional term coming from the temperature gradient. Okay. If you do this kind of work, take these equations in, and it is very amazing what you can see that come out. And you could see by comparison with Mara's data that you can agree with the experimental results, and this shows that the numerical or analytical expressions allow you to get it inside what you observe experimentally.
Okay. Thank you.
Let me say one thing. I just realized now, in the turbulent case of the laminar turbulent transition, the Blenheim results were by Mesmer, and I said Mara. This was a mistake.
Okay. I think there is no more question from the audience. Amrez, we can close this session by thanking Professor Durst.
Okay, thank you, Professor Talukdar, and thank you, Professor Durst, and all other audience here. And Professor Biswas, if you want to continue, means the session, it is open for us, means just to discuss in any topic. So we can go ahead with that. And Professor Wang, if you also if you can participate, it will be very nice.
I mean, I'm not really prepared for this impromptu discussion, but having Professor Durst among us is really amazing and absolute delight, because we can get ourselves enriched with his knowledge, with his suggestions, with his advice. and especially people who are planning for newer experiments or who are thinking about converting some paradigm into correct experimental paradigm from where the real conclusions of long-lasting value can be drawn. They can probably get in touch with Professor Durst and discuss their problems, and I'm sure they will benefit a lot. Professor Wang is also here, so I will leave the podium for Professor Wang. Professor Wang.
Thank you very much for the response.
Yeah, Professor Durst.
Hello.
It's nice to see you, although not physically.
Yeah, thank you very much for coming to this meeting, and at least it gives me an opportunity to see you through television once again.
Yeah, it's really nice talk. I've heard. Yeah. But it's only a pity. Here is a little bit in Taiwan. My system, I have some echo to disturb my hearing about this. But in any case, I saw from the slides and to enhance the hearing problem, I cannot catch quite of that. And have you any suggestion for the future, especially for the young generation, when they are making, for instance, they are making microfluidic and so? And have you any suggestion, direction for them?
One of the things is sometimes we get annoyed if we get two different results for one solution of a let's say of a flow phenomena. And we should not. We should think about the difference and see where does it come from. This was basically the message I was trying to get over. Let's say if we're doing fluid mechanics, the following, let's set up paper problems of a particular flow and we solve them. Results. Definitely, this is also necessary because we have now these fantastic methods and we can use them to solve tasks in fluid mechanics. And if we do this as an only let's say, way to deal with fluid mechanics, then we will have no progress. We need this progress that we say it's impossible that people who did not have the numerical methods available, also some of the analytical means or the means, that they have obtained all results of basic results of fluid mechanics in the 18th century. That I don't believe. We should look at these equations, the background of these equations, and see that we can use them, use the differences to find out where we can put in place and get improved equations, improved methods for the measurements, or for the investigations.
Okay. Yes, thank you. I think this will be a very delightful for the young generation to think about and progress further in the future. Yeah. And I heard you have birthday in this December, and happy birthday for that. And
thank you.
And it's really nice to see you are still so healthy as before, without any change.
Well, you see, I have learned that if you want to become old, then you must have a lot of birthdays. So that's if you want to stay healthy, you must do some
activities, and possibly the best activities you can have is in fluid mechanics.
Okay. Yeah. And sorry, I have a meeting in 3:30, and I need to leave. And I thank all of the organizer and all participants. And I hope you could have still a very interesting talk with Professor Durst. Professor Durst, I need to leave and say goodbye to you.
Thank you for coming to this presentation. Yeah.
Yeah. Thank you. Goodbye.
Goodbye.
Thank you, Professor Wang.
Yeah.
Any discussion or any from audience? I think there are no questions. Professor Talukdar, so please go ahead.
Yeah, Professor Bruce, hopefully we'll see you very soon. When pandemic is over, definitely we'll see in Germany for sure if you are not coming here.
Yeah, I would have really come to this meeting because, as I said at the initial part of my lecture, this would have been an excellent opportunity to meet you all. And I also hope it happens once more somewhere in the world.
Sure, yeah, it was exciting for me also. And and in the morning at home, I told I am going to, sharing a session for Professor Drust, which is a good news for my family too, because
How's your family? Is it fine?
All good. My son is working now. He is a mechanical engineer working for a startup company in Bangalore. And my daughter is in class 11 now.
Oh, wow, they go, huh?
Yeah, we are going out.
Say hello to your wife and also to the children. My wife is also sitting here, so she also says hello to all of you. And also Professor Bishwas, hello from myself and from my wife.
Yes, my heartfelt greetings to you, Frau Durst, and the entire family. It is, as I said, absolute delight to see you even from distance, and I look forward to meet you personally, whether in India or in Germany or elsewhere. I'm looking forward for the next opportunity to meet you.
Thank you very much. Thank you. And thanks for coming to this presentation. Yeah.
Okay, then Amresh will close this session here.
Professor Dalal.
Yeah.
Yes, thank you. So I would like to thank the speaker, Professor Drust, for accepting our invitation and means delivering this wonderful lecture. And also I would like to thank Professor Bishwas for attending this lecture and Professor Wang. And I thank Professor Talukdar for chairing this session. And I thank all the participants who attended this lecture. So thank you very much. So we are now means again we will meet at 1:30 for the keynote lectures. Thank you. Thank you very much. Bye bye.
Thank you very much, and have a nice conference. Yeah. Thank you. Bye.
Have a nice day. Bye.
Thank you.
Hello everyone. This presentation I am going to deliver is on the topic droplet impact near millimeter sized channel. Understanding droplet impact is relevant for several applications like inkjet printing, spray coating, pesticide deposition, spray combustion, and so on.
Let me
Research has
quickly
identified the following outcomes for a droplet
introduce
using
the
two
problem
pressurized
and its
test tubes.
background and where we currently
First
stand.
one is spread.
Thin leaves,
Observe
paper
a
cuts,
low
they
energy
actually
droplet
fall
impacts
under their own
or
weight.
hits a
However,
solid
when the
substrate.
density
Here,
ratio between
a thin
the
fluid film,
object
also
and the
called
surrounding
slag, is
fluid
ejected from
is
the
near
center of the
about
droplet
1,
post
then the
impact, which
trajectories
spreads
through
until it
which
attains
the
maximum
object
speed.
fall
Second one is a
becomes
splash.
complicated and
Splash is
it's a
observed when
subject
a
of
high
fluid
energy
mechanical
droplet
studies.
hits a solid
It
substrate
involves complex
and
fluid structure
disintegrates
interaction,
into tiny
stability
flexible
of the
droplets.
trajectories.
Again,
In
splash is
trajectories, the
categorized
established
into two
regimes are
types. First
mainly
one is
three:
corona splash.
flutter, which
In this case, the
tumble,
lamella
and the
ejected
chaotic
from the
region.
droplet base
To
lifts instead,
universally
forming a cone shape
obtain
before
different regimes,
disintegrating into
different
tiny
shapes
fragmentary
of
droplets.
plates are
Second one
actually
is prompt splash. Here,
are
the lamella does
unified
not lift or
according to
tear.
the
Instead, develops
dimensionless moment of
undulations
inertia,
or
which will be
perturbations along its
defined
course.
later on. From
Before
point
it
1.6 to
disintegrates
point 0.4,
into
it is
tiny
known as
flexibility
flutter,
droplets.
which is
Fourth one
shown
is
in the
ripple,
right here.
observed commonly
Tumble,
when a droplet hits a
sorry, the flutter.
super hydrophobic
The
surface.
tumble proceeds from point 4 to
Research
3,
has also shown that
which
surface roughness elements and texture
which gives us an
influence the
impression
perturbations
of
which appear on the rim
complete
of a
rotation,
corresponding
and
droplet
the
lamella
flutter to tumble
and
transition occurs generally
also
near
affect the
about point
lamella flow
4,
behavior
which is
post
generally known
impact.
as chaotic regime, which shows the
Understanding how surface
signs of
roughness
both flutter
elements
and tumble.
affect
In the
fluid flow
current study,
behavior is
we
quite
have
challenging.
added multiple plates to see
Researchers
the effect
started
of
investigating
the
droplet
proximity
impact
of
on
each
solid
plates
substrates
each
containing
plates on the
NSFMFP.
stability of the trajectories
Macerant in
and the
2005 introduced an
role of
article assessing
complex
the
vorticity
stability
dynamics
against
in
surface elevation.
deciding their
He impacted water droplets
trajectories.
on inox coated with Teflon. The impact
As the
velocity was
current
fixed at
study
2.78
involves
meter per
multiple
second
plates,
and
it
the
is
study
essential that we
was this. From his experiments, he found that the angle, width and velocity of the liquid that shoots up post-collision with obstacle varies based on the distance between the droplet impact point and the obstacle and also the obstacle's height. Reisman in 2010 conducted experiments on substrates containing open pores. He impacted water droplets on surfaces which had varied surface wettability. The impact velocity was also varied here and the pore diameter was fixed as 1 mm. From his experiments, having a static contact angle value of 67 degrees. This value having a length of 0.5 mm and 3 mm in a maximum high polymer substrate known as silicon aluminum polymer
Tu es trop grand pour comprendre des choses aussi petites.
Energy to undergo any major change. However, when eccentricity E is reduced to 2.3 mm, we observe that the protrusion hits the channel, still has some sufficient kinetic energy because of its
हाँ ये हॉल में प्रेजेंटेशन क्यों चल रहा है आप देख रहे हैं
Vous allez écrire un instant.
Yes.
trop grand pour comprendre des choses aussi petites.
Hello, good afternoon. Welcome, Professor Pradeep and Professor Tagi.
Hello, Professor Amrez.
Good afternoon, Professor Dalal.
Good afternoon.
Good afternoon,
So
Professor
let us
Pradeep.
wait for a few minutes, okay?
Sure.
Yeah. And also more participants in the YouTube.
Yeah.
So let us wait for another 3-4 minutes, then we'll start.
Right. Sure.
Yes. Thank you. So Professor Pradeep, I think means already you have checked how to present, and I think you are using
Yes,
Microsoft
we
Teams.
use it for our classes, so I can just check if this connectivity works.
Yes.
If my audio is okay, then I will just check if my slides are.
Yes, audio is fine.
Yes, Professor Pradeep, we can see the first page
of
your
great.
presentation.
Sure. That's fine. Thanks.
Okay, so let us wait for a few minutes, and then Professor Tagi will start. Okay.
Sure. So I think Professor Pradeep is also chairing the next session in the same hall, right? Hall
That's
3.
right.
Yes.
That's
Okay.
right.
Yes.
And one small question I have, that the time is given from 1:30 to 2 p.m.
Yes.
So should we keep 2-3 minutes for question answer? Like Professor Pradeep, how long would you?
It depends on time. Say you can means 5-7 minutes is flexible. There is no problem because we have break in the year, so you don't worry. So another 5 minutes if you want to take, no problem after 2.
Okay.
Yeah, I have time for 25 minutes, so I can wind up by 1:55.
Yes. So it is because we have some time for break, so that will be adjusted.
Okay.
Thank you.
Thank you, Professor Pradeep.
Hello. Hello, Professor Tyagi.
Yes,
So we
I'm here.
request you to start. We request you to please start the session.
Okay. Thank you very much. Very good afternoon to all the participants to this keynote lecture by Professor Pradeep, whose title is Understanding Instabilities in Axial Flow Compressors. Professor Pradeep is currently professor in the Department of Aerospace Engineering at IIT Bombay. He completed his bachelor's in mechanical engineering from Calicut University in 1998. Subsequently, he pursued master's and PhD from the Department of Aerospace Engineering at IIT Kanpur. After completing his PhD, he joined IIT Bombay as an assistant professor. His research interests are in the areas of turbo machinery aerodynamics, design and performance evaluation of turbo machinery using passive active flow control methods. Professor Pradeep has supervised 8 PhD and around 58 master students at IIT Bombay. He has over 90 publications in international journals and conferences. He is also a co-inventor in 3 granted patents. So it gives me great joy in welcoming Professor Pradeep, and I invite him to please share his screen with the members and kindly start the presentation. Thank you.
Thank you. Thank you very much, Professor Tyagi. And before I begin, I would like to first acknowledge the organizers of this conference, Professor Dalal and his team, for giving me this opportunity to share some thoughts on some of the work that we have been doing on this interesting topic. Of course, I also have to acknowledge all the contributions that my students have made. I get an opportunity to present their work. It's their hard work that I'm essentially presenting today. So before I get started, I also want to congratulate the organizing team for taking up this challenge to have this conference conducted on a virtual mode. That's a very bold step, and we are used to FMFP in the physical mode, and we hope that next time it will be indeed that way. And so before I get started, just to set a tone, bird's eye view of what this area is all about. Essentially, what we are trying to do here is to understand some aspects pertaining to instabilities in compressors, and where does it fit in the overall aviation scenario. So my talk is essentially biased towards aviation. And if you look at this chart here, which shows sort of progression of how aviation has come about from the time it's essentially a tube and wing configuration, but that is expected to change in the years to come. So what is also to, sorry?
Yeah, please continue, Professor Pradeep. I keep their mics on mute. Presentation is going on, and there will be opportunity at the end of the presentation to ask questions. Thank you.
Thank you, Professor Tyagi. Turbines and compressors, and today's talk I'll essentially focus on the compressors. And what you see here are typical efficiencies that modern day individual compressor or turbine efficiencies touching 90s and beyond. So the question is, is there really enough scope to make any further improvements beyond their incremental? And the years to come, the engines that are expected to, some of the aspects which will need significant attention are to do with emissions, efficiency, as well as stability control. So the Advisory Council of the European Union came up with a set of guidelines long back, stating that by the year 2020, that is the current year, we should have achieved some of these targets, which are quite substantial in terms of how these are going to be achieved. And they also came up with a roadmap as to how this can be achieved. And some of the crucial areas, of course, not all of them, some of them which are listed are to do with aerodynamics, heat transfer, materials, and cooling. And our interest is primarily in the aerodynamics of turbo machines. And I will primarily focus on one of them in today's talk, which is to do with stability in compressors. So I'll begin with a classical cartoon of complexities in turbo machine. This is from textbook by Professor Lakshmi Narayana, who is sort of considered as a guru in turbo machines, which highlights all kinds of complicated flow features that one would normally encounter in these kind of flow situations. One of the prominent ones being tip leakage flow, and you will hear this throughout the talk today, which I will refer to as TLV, tip leakage flow, and tip leakage vortex, which is basically the flow which leaks from the pressure surface to the suction surface and forms a vortex, and obviously results in a certain amount of efficiency loss. So in today's talk, I'll focus on a few of these aspects, largely tip leakage flow and tip leakage vortex and its interaction with the leading edge shock wave, which you would normally see in a high-speed compressor. We will also try to see how the inflow distortion or inflow non-uniformity interacts and affects the performance by having influence on the way the shock and the leakage vortex interacts. I'll also talk about a little bit about the scrubbing loss in one of the slides later on. So those of you who are familiar with compressor performance map would be able to relate to this chart shown here, which is a very important map as far as aero engine designers are concerned. This is a very significant aspect in the overall engine performance itself. So compressor performance map is expressed in terms of mass flow rate, which is corrected or non-dimensionalized in a certain way, and pressure ratio, and also the various speed lines, constant speed lines, which are shown here in purple, and the efficiency constant. So without going into details of the performance map itself, what we are interested in is this blue line that you see here, which is sort of the instability limit or the stability limit, whichever way you look at it. So this is the limit of stable performance of a compressor. So if you try to reduce or throttle the compressor beyond this, the compressor is going to go into stall or surge, which are essentially instabilities in compressors. And there are a lot of work which has happened over the years to understand these instabilities. One of the famous work from MIT, which came up in 2009, talks about how one can correlate the tip leakage flow with the shock wave, and the way they interact would essentially dictate whether the instability is going to be induced abruptly or whether it will be induced in a gradual manner. So there is spike inception versus modal inception, which came up around 2009 from MIT. So with that background, I will first begin with some of our very recent work, and then I will probably flash back a few years to highlight some of the work we did several years back as well. So this is a typical bypass turbofan engine, which usually has a fan in the front, which is what you would see normally when you board an aircraft. This is what you see, the fan of the engine. And we have tried to understand how the fan behaves under various inflow conditions and how the leakage flow and the shock wave of the fan can have a very strong coupling, and that sort of dictates the stability mechanism in fans. So what is shown here are essentially the relative Mach number plot, which is from our computational simulations. We'll talk about RANS simulations as well as unsteady RANS in a few slides later, and our understanding of what the physics is from this. So if you look at it closely, you will see that this is the fan blade and the direction of rotation. The leading edge of the fan has a shock wave, and there is also a leakage flow which is from the pressure surface to the suction surface. So the leakage flow is going to be this way. So there is going to be an interaction between the shock at the leading edge with the leakage flow, and the resulting blockage actually changes its characteristic as you go from the peak efficiency point towards the vortex breakdown or the instability point. So at some point, the compressor, as you throttle the mass flow, the leakage vortex is going to disintegrate, resulting in increase in the blockage in the passage, causing instability to be incepted. So this is something we observed as part of our work rather recently. Now, we further extended this work to understand what happens if the flow itself is non-uniform. An example could be this: an aero engine which is cruising at some altitude would have a flow which is relatively uniform, and if it happens to be at an inclination, let's say during climb or even at high angle of attack flights, a part of the flow is likely to be non-uniform or distorted, which is what is shown here. So if I take a section at the engine face at the compressor entry, this sector there where you can see a non-uniform flow coming in will show up like this. So if you take 4 different sectors in this plane, one which is right in the core of the distorted sector, one is upstream of it, one is at the inlet of the distorted sector, and this is far away from distortion. What happens to the flow in these different sectors? So if you look at this a little more carefully, the region A, which is essentially in the core of the distorted sector, you will notice that the shock wave is detached. So you can see here the dotted line indicates where the location of the oblique shock is. It is a detached shock there. The interaction between the shock and the leakage vortex in this region happens to be weak. Whereas if you look at the region which is just outside the distorted sector, which is sector B, the oblique shock is attached, it is closer to the leading edge, and there is a stronger interaction between the leakage vortex and the oblique shock, resulting in increased blockage. And you move further to the other sectors, the sector C, which is the undistorted sector, as well as the sector D, which is where the distortion is just beginning, you will see that the way the leakage vortex and the leading edge shock interacts are quite different. And each of this sector does have a different effect on the way the compressor is going to behave. So let me, and if you look at the way the shock wave is a little more closely, we also notice that the shock angle itself is different between the distorted sector versus the undistorted sector, and that also gives us significant clues as to what is likely to happen when this shock wave interacts with the leakage flow downstream. So I hope the animation is coming through given the bandwidth. So what we tried to do as we did an unsteady RANS to understand how these different sectors behave, and as the blade approaches the distorted sector and as the blade leaves the distorted sector, how the distortion sort of behaves. So we get an idea as to how the breakdown of the leakage vortex happens when the interaction between the leakage vortex and the shock wave is strong, versus when the flow is in an undistorted sector, the leakage vortex and how it sort of moves through the passage is something that we can visualize in time. So we do see that in the undistorted sector, over a period of time, the blockage sort of grows in time to an extent that it starts forming patches of what are called stall cells, which eventually cover the entire annulus of the compressor, resulting in onset of the instability. So that was sector A and C versus D and B. So without spending more time on this, I essentially wanted to highlight the fact that the interaction between the leading edge shock versus the leakage vortex is a strong function of the quality of the flow that the compressor is going to face. So distortion is indeed going to have a very significant effect on the way in which the leading edge shock wave interacts with the leakage flow. So that was rather recent work that it's still ongoing, and I would like to go a few years past, in sometime around 2007, 8 to 9. That was the time we started looking at instabilities in little more detail. One of my first PhD students who was working at that time looked at instabilities in a low-speed compressor, and also to try and sort of figure out mechanisms by which we can control these instabilities. So this is a test facility we used to have in those days, which has undergone a lot of changes now. And using casing-mounted Q-light transducer, we had the unsteady pressure traces, and using the pressure data, we came up with a mechanism by which we can inject air from the casing to see if we can energize the casing boundary layer and prevent the instability. So you can see the actuators here close to the leading edge, and we had a feedback control mechanism which helped us in delaying stall by a certain amount of time. So before I go into that, the nomenclature that we've used, this is there are two types of disturbances that we are interested in. One is what is referred to as a long length scale disturbance, LLSD, which is when the disturbance covers about 40% or more of the circumference of the fan. And if it is less than that, this is referred to as short length scale disturbance. So this is a nomenclature which around late 90s, a lot of work happened where people have come up with this kind of nomenclature for these disturbances. So when we started this work in those days, we had these pressure traces, and just based on visual inspection of the pressure traces, it was becoming very difficult for us to make much sense out of the data that we had. And so around the late 90s, we also saw that there was a lot of work on trying to use better methods of signal processing to see if we can make better sense out of this data. So one such tool that we came across, which was very interesting and useful, was wavelet analysis. So we used wavelet analysis in those days back in 2009 to convert the pressure traces into a frequency spectra. And from this, we found that we could indeed get better information about the stability mechanism and the onset of those. So from the frequency spectra, we could identify the short length scale disturbances that you see here, as well as long length scale, and infer what causes the onset of these instabilities. And based on this, we came up with a mechanism to control these instabilities. As you can see here, this is the pressure trace, and we see the disturbances beginning to grow, which is when, if this is allowed to continue, we would have the onset of instability that you see here. So using the casing injection, we could delay the onset of stall, and that was essentially through our understanding of instability through the wavelet analysis. Let me skip this in the interest of time. And the other interesting thing that we worked on is on casing treatment, which essentially looks at what we did in the previous study was to externally inject air. Casing treatment uses air which is already there in the flow downstream where the pressure is higher, divert it in an efficient manner upstream to energize the flow. So this is already used in Eurofighter, in one of their the military jets. Problem with this is efficiency penalty. So we had a fairly long collaboration with NAL Bangalore where we developed quite a few innovative casing treatment methods, which not only improve the stability margin, but also without the loss of penalty, which is rather unique in terms of the other contemporary work which has happened so far. So this is the geometry which was developed, which promises fairly substantial stall margin or stability margin improvements with little loss in efficiency. And what it does is basically there is a chamber here which is upstream above the compressor blade itself, which efficiently diverts the flow from downstream to upstream without too much loss in efficiency. So we see that we can actually shift the stall frequency, and the amplitude as well as the frequency is shifted substantially with the use of these casing treatment geometries. So what was done here was essentially the fact that the flow from the downstream is diverted through the plenum above the casing through these slots which we had carefully optimized without the loss of efficiency. So this is something that has resulted in improved stability of the compressor with minimal loss in efficiency. In fact, in some configurations, we actually see about 1% improvement in the efficiency. So moving on, I would also talk about some aspects pertaining to blade shape modifications that we did as part of our study. We have also come up with some innovative blade shapes that you see here, which are relatively less sensitive to tip leakage flow effects and losses thereof. So that's some work we did a couple of years back. And some of the recent work, I'll spend another 4 to 5 minutes highlighting some of the recent ongoing work. This is a picture that you saw in the very first slide, which is an open rotor demonstration, which is currently underway in Europe, which promises substantially higher fuel efficiency. So we have been doing some work in contra-rotating fan for some time now. And some of the recent work where you can see the blades mounted here, the rotors rotate in the opposite direction. We started this work about 7-8 years back. We had some initial work on various inflow conditions on a high aspect ratio fan. And we have now developed a new fan, which is a medium aspect ratio fan, and trying to continue our work on stability analysis in this. So here again, if you look at the unsteady pressure traces at different rotational speeds, depending upon the speed of rotation of both the rotors, the stability mechanisms could be quite different, and that's something that we have attempted as part of the ongoing work. So we observe that if you change the rotational speed of either of the rotors, the instability inception could change from a long length scale weak strong to a weak long length scale depending upon how the rotors are rotating. So what we have seen is that if the downstream rotor rotates at a higher speed, it allows the stability margin to be of the compressor stage to be better would be if they were all rotating at the same speed. So we have also done some analysis of the leakage flow and the mechanism of this thereof, and I will not really go into details of this. So the wavelet analysis, we have made further improvements from what we did in 2007, 8, 9. We have a much better understanding of how we can use wavelet analysis to infer the inception of instabilities in these kind of applications. So the other ongoing work is on tandem blade. In fact, a lot of work has happened in IIT Bombay long back. Professor Saha, who is in the audience, I believe, had done a lot of work in tandem blades long back in the 90s. And we have now extended much of this in terms of understanding of the placement of the tandem blade. So this is how a traditional blade would be, a single blade. A tandem blade is basically splitting the blade into two so that the flow from the pressure side can leak into the suction side and energize the flow on the suction surface. So that is the basic concept of tandem blades. So current work involves understanding the flow physics as well as eventually extending it to a contra-rotating situation. So combination of the previous work as well as a tandem work. So the test rig that we have currently looks at how we can optimize various parameters ranging from the spacing between the blades as well as the axial overlap and so on. So what we see here is a very interesting flow physics. This is a single rotor that would normally see the leakage flow from the pressure surface to the suction surface. We also notice that there is a scraping vortex here, an enlarged view is shown here. And in a tandem, of course, we have not been able to locate a scraping vortex because of the fact that the chord is much lower than what it would be if it was a single blade. So scraping vortex is absent in a tandem blade, and therefore the associated mechanism of interaction of the scraping vortex with the leakage vortex is absent in a tandem blade. We have also looked at how the various clearances of the front blade versus the aft blade can influence the interaction between the leakage vortex from the front blade with the leakage vortex from the rear blade. So unlike a single blade where there is just one leakage vortex, in a tandem blade you will have a leakage vortex from this blade, you will have a leakage vortex from the second blade. One would also have a flow which is coming from the passage itself. So there is a very complex interaction between these three different flows which one would see in a tandem blade. So this work is still ongoing, and one of my PhD student is currently working on this as well. So before I go to the last slide, I would also like to highlight one aspect pertaining to not just the compressor, but a component which comes downstream of it in the engine configuration that we saw in the very first or second slide, that the flow from in a bypass turbofan, a part of the flow goes into the core of the engine, what you see here as the red path. And this is a duct flow which derives its flow from the fan. And so instabilities from the fan can also get transmitted towards the downstream component to the further stages downstream. So we are also trying to understand how the instabilities can get carried through the duct to the downstream stages. And what we have seen is that depending upon how you do the analysis, much of it can get attenuated. If you just use a radial profile, this is what you get at this station. Whereas if you do a steady RANS versus unsteady RANS, the amount of information that is actually translated downstream could vary depending upon what kind of analysis methodology is used for the kind of study that is being done. So this is something that also we have done in the recent past. So in the interest of time, I will go to my concluding slide here. As I said in the very first slide, This is a very interesting and challenging area because we are looking at components which are already nearing its peak performance. Turbine efficiency is close to 95, compressor close to 92, component efficiencies. Scope for further improvement is going to be incremental. That is already known, but those incremental performance improvements are also important from the aviation perspective. So stability of a compressor, as we have seen, is very sensitive to the tip clearance flow and how it interacts with the leading edge vortex or the non-uniformities that you can see. So that the complex interaction between them plays a very important role in the overall physics governing these flows. And the presence of non-uniformities, as we have seen, further complicates the already intricate flow physics in these kind of applications. So ongoing work as well as future work will essentially look at some of these unconventional concepts like tandem or contra-rotating casing, many more as well. The mechanisms are yet to be fully understood, and I think there is enough scope to understand our the complicated flow physics in these kind of flow situations even better, and that's where we are headed in the years to come. So the takeaway message is that a better understanding of instabilities can possibly lead to better design strategies, and that's very important for future aero engine technologies which are going to come up, and that's where this incremental improvement will indeed play an important role in the performance of the engine itself. So with that, I would like to stop here, and thank you very much for your time and patience in hearing me out. Especially post-lunch session is always a challenge, and I would be happy to take any questions that you may have.
Thank you very much, Professor Pradeep. I extend a big thanks to you on behalf of all the participants. I think large number of participants are there, so let me open it up for questions. So any participant now, they may feel free to ask questions. They can unmute their mic and please go ahead and ask some questions. In addition to that, I think many participants are also participating through the Facebook Live and YouTube. So I would request the volunteers that if they ask any question in the chat box there, they can also communicate it to us over here through either text or somebody can read it out. So in the meantime, when some people are thinking about question, I have one question related to the stability, Professor Pradeep. Yeah. In one of the slides, like slide number 19, if I remember, you had mentioned that by injecting some extra air, then significantly reduction, I think it was delayed.
Yeah.
So can you explain a little bit about that? Is that injection continuously taking place or only when the instability reaches above some threshold?
Right. So the injection kicks in when the instability exceeds a certain threshold, which we can define. But then there is only a certain amount of time limit within which one can keep injecting. You know, in an aero engine scenario, one would not look at this favorably till we can be assured of the benefit itself. So what we saw is that we can, if we inject close to about 0.05% that of the primary mass flow, the stall inception is delayed by a few seconds. So it gives us some amount of time to possibly recover from the instability. That is when we sense that the instabilities have exceeded a certain threshold. If you allow it to continue, the compressor will indeed going to surge. And by an intervention through external injection, one could delay that by a certain amount of time. So that was a proof of concept study that we did, that it is possible to energize the casing boundary layer and delay the instability by a certain amount of time. But that requires external air injection. Yeah.
Okay. And another question, are there any questions from the participants? If not, then I'll ask one more question because I think we have 1 more minute. That you had mentioned toward the end that it is going to be very challenging to model this thing computationally, because there's a lot of multi-physics going on over there. So can you just briefly share that what are the main challenges and how do you overcome them?
Yeah, so from our experience, we have in our group been using commercial softwares, and we have had experience with almost all the commercially available softwares. And our experience is that as you try to simulate flow field close to the instability, that is close to rotating stall or surge, steady RANS is simply not capable of predicting the onset of instabilities for obvious reasons. So if you start doing an unsteady RANS kind of simulation, the amount of time and resource required for that would be quite substantial. And therefore, that's one of the challenges. And second, of course, is how do you validate the results that we have with the test data? Depending upon the type of turbulence model that you use and the default parameters which are there, which are tweaked, the results that you get could be slightly different depending upon these. So there is no universal SOP that one can follow, depends upon the geometry itself. So that's probably a challenging thing that will need to be addressed.
Thank you. Okay, so last chance. Any questions from the audience
I have
members?
a question.
Please go ahead.
Yeah, I'm Shravan here from Honeywell. So regarding that skewed slots that you have shown in one of your presentation, I think it was done years back. So was it there was a plenum chamber on top of that where flow is recirculated through it, or it was just like a normal passive circumferential grooves?
No, so the casing itself had the slots with a certain bend and skew, and above the casing there was a chamber through which the flow is diverted. So it's a plenum plus the slot together that did the trick. So it's not just the slot, but it also has a plenum above that.
Okay, maybe because of the recirculation that is already energized air that you have got after downstream of the rotor, you are putting it back there.
That's right.
That might be one of the reasons why we have seen some loss in efficiency in that, right?
That's right. So it depends upon how efficiently one can divert the flow without incurring too much loss. And that's probably how one can manage the loss in efficiency that is normally seen in casing treatment applications.
Okay, thank you.
Thank you so much. Yeah.
Okay, thank you. As chair of this session, let me formally thank Professor Pradeep for giving an excellent talk where he talked about the instabilities in axial compressors. He presented the numerical simulation animation as well as showed the experimental setup and the results from his group. So on behalf of all the participants, the conference organizer, and on my own behalf, I thank Professor Pradeep. Thank you very much.
Thank you very much, Professor Tyagi. It was my pleasure to talk about this. Thank you.
Thank you. With that, we formally close this session. And I think the time has started for the next session, which I will invite Professor Pradeep. He himself is the chair of session. Please take over. Thank you.
Thank you very much. Thank you.
Thank you, Professor Himanshu Tyagi, for chairing this session.
Thank you very much. So I think it's already time to start the next session. So let me go to the program. Sure.
Okay. Yeah. Shall I start? Yeah, sir. You please.
Yeah. So this is a session on turbo machinery, and we have 8 interesting papers in this session. And I believe all the authors of these papers are already there in the audience here to answer any questions that may come up after their talks. Vignesh is already here, who is going to be talking, who's the speaker for the first talk, and I hope the other authors are also here. So without further ado, so let's get started with the first paper here, which is going to be presented by Vignesh Kumar, who is going to talk about investigation of high cycle fatigue failure, risk of small geometry turbine housing using Fourier analysis method. So Vignesh's talk is the first one, so we can get started with Vignesh Kumar's talk.
Everyone, this is Vignesh Rana. My topic for presentation is investigation of high cycle fatigue risk of turbine housing using Fourier analysis methods. So let us first consider the turbocharger turbine in which the exhaust gases are entering through the inlet, and while passing through the turbine housing, the exhaust gases pressure is continuously reducing. So this area is called the tongue of the turbine, and turbine wheel is continuously rotating inside the turbine housing. So as mentioned in the figure, just left of the tongue having very high pressure region area and just the right of the tongue having very low pressure region area. So when we maximize this area, then whenever the turbine wheel leading edges is passing around the tongue, so because of this critical geometry of the tongue, the turbine will experience a vibrational stresses and high temperature fluctuation nearer this tongue geometry. So after the 10 raised to 7 and 10 raised to 8 cycle, this effect of vibrational stresses are maximized and the turbine wheel is subjected to failure in the two side of turbine. One is the exducer of the turbine and the another is the inducer of the turbine. These two pics shows the effect of high cycle fatigue in the turbine. So these are the vibrational contours of the individual turbine blade nearer the lower, moderate and higher frequency. So as shown in the figure, the lower frequency have the maximum vibrational point around the wheel trailing edge, and the moderate and higher frequency, the maximum vibrational point is around the wheel leading edge. So as we know, the turbine wheel failures occurs at the maximum higher frequency to moderate frequency. That is why maximum chances of failure of turbine is nearer the wheel leading edge. That's why the parameter or the physics nearer the wheel leading edge is important to capture. In this slide, we will see how Fourier analysis is used to calculate the vibrational amplitudes. So these are the figure after the CFD simulation of the turbine. So as we discussed in the last slide that the turbine, the wall physics nearer the turbine wheel leading edge is important to capture. That's why we created the 20 polylines nearer the wheel leading interface, and with the help of CFD post software, we extract the pressure data of each polylines and we take the average of all the 20 polyline to generate a regenerated curves which are the generalized the pressure distribution curve around the 360 degree of the turbine. So this curve is the pressure difference which the turbine will experience around the 360 degree while rotating a one cycle of operation. In this curve, this is the peak which is shown the area in which the maximum pressure of the tongue means just the right side of the tongue having maximum pressure, and this is the through of turbine which shows just the left of the tongue which is having a very low pressure. So while the turbine will leading edge is passing through the tongue, it experiences this much amount of the pressure variation. So our intention is to minimize this pressure fluctuation data, means this pressure fluctuation around the wheel leading interface. So what we did in Fourier analysis, we assume this curve is made up of the infinite number of the constant frequency called order. So in which one order represent the one revolution around the cycle, the two order represent the two revolution around the cycle. So subsequently this curve is disintegrated to constant frequency order term, and later we will distinguish the which order is responsible for high cycle fatigue failure of the turbine and extraction of the each amplitude data of the particular order. This is called a critical order which are responsible for high cycle fatigue failure. Here are some formula of the Fourier analysis in which the complex waveform means the regenerated waveform can be broken down into simple harmonic waveforms of sine and cosine by this generalized formula, and below are the formula of constant used in the generalized formula. So and the amplitudes of and the vibrational amplitudes of each orders are calculated as the first order formula is this and the second order formula is this. So subsequently the third, fifth or sixth order formula is calculated by this generalized formulas constant. Here are the flowchart representation of turbine housing modification, in which the complete turbine housing is divided into 4 sections. The first section is a higher pressure region, and subsequently our area of interest is the fourth section, which last quadrant modification. So as we know that the higher pressure difference is obtained because of the area variation nearer the tongue. So the first quadrant having very high area and the last quadrant having the very low area. So what we are going to do, we are increasing the area in the last quadrant by some extent, so that can minimize the area difference nearer the tongue. Subsequently, that minimize the pressure difference around the tongue geometry. So first we have the original turbine housing that create the vibrational amplitudes that have the high vibrational amplitudes. Then because of the high vibrational amplitude, the high cycle fatigue of turbine wheels are generated. Then we modified the last quadrant of the turbine by means of increasing the area of the last quadrant. We got the modified turbine housing. Then we again extract the vibrational amplitude by the earlier method which I explained. Then after the we are having vibrational amplitude, then we check the whether the new amplitude is less than the original amplitude, then the design is finalized. And whenever the new amplitude is greater than the original amplitude, then the same cycle of modification of the last quadrant of turbine is repeated. Here are some methods of modification of turbine of last quadrant is explained, in which the software like PTC Creo and Sculptor are used for modifying the last quadrant, in which this color portion are represent the incremented area in the subsequently in radial direction as well as the axial direction. Till this time we saw amount of increment in the last quadrant can affect the Fourier amplitude. But by having our analysis, what we found, the meshing structure in the increment region is also affect the Fourier amplitude, just because the finer amount of mesh provided in the increment region can have the better wall physics prediction nearer the increment region. Then that's how the reason of maximum reduction of Fourier amplitude for working orders. So the main idea behind this analysis is to check whether which meshing approach provide the perfect correlation with the experimental strain prediction of the turbine strain. Here are the result of percentage reduction in vibrational amplitude by the coarse meshing and fine meshing approach. Here the 5, 6, 7, 8 and 9, 10 are the critical working order which are responsible for high cycle failure, and our intention is to reduce those amplitudes of this critical order. So as we found, the percentage amount of reduction in coarse meshing approach is so much variation, and for the 8, 9, 10 it is gradually increasing, but with the fine meshing approach it is quite uniform, and the all order the amount of reduction, the percentage reduction is decreasing. So that's why the fine meshing approach having the better correlation with the turbine strain data in experimental analysis. And the below table show the while adopting a finer meshing approach, there are no change in mass flow parameter, the percentage change in mass flow parameter, and then no change in efficiency. Here the mass flow parameter and efficiency change is within the limit of 0.1%. We can go ahead with the fine meshing approach. Now here are some result of original housing and the modified housing with fine meshing approach. So in the first figure we see the percentage reduction in Fourier amplitude are nearer to 30 or 40%, means the high cycle fatigue of failure is reduced by 30 to 40%. The figure 2 represent the pressure variation around the tongue, which is situated nearly at 180 degree, is now reducing. The red curve shows the pressure fluctuation is more earlier, but with the modified turbine housing, the pressure fluctuation is lesser for the modified turbine housing. And figure 3 and 4 are experimental analysis data in which shows the while having the modification, no percentage change in mass flow parameter and no percentage change in efficiency found. The percentage change in mass flow parameter are within the range of 0.9%, and even the efficiency change in mass flow parameter in efficiency change with the modified housing is within the range of 0.4%. And here are some conclusions regarding the project, in which the turbine housing modification is reducing the vibrational amplitudes, and the percentage reduction of Fourier amplitude is found nearer the 30 to 40%, and later it can reduce the pressure fluctuation around the wheel leading interface, and the proper amount of morphing and high quality of mesh element increase the alignment of CFD result with telemetry test data, and the percentage change in performance of turbine is also less than the plus minus 0.1%. So at last, the amplitudes is also reducing, and the performance of turbine is also not changing. That's why the turbine housing modification is further used for small size turbine with finer meshing.
Okay, thank you, Vignesh. It was a very interesting work that you have presented.
Yeah, thank you.
Vignesh is here for answering any questions. Shyam Shukla, you have a question, please go ahead.
It is nice presentation, and the performance change which is said as within 1% with the change of the gap. Do you have any, have you checked with any validated case results? Because it looks to be too less change of performance with too much change in the geometry.
Yeah, so yeah, Shyam. So that is the only concern, that yeah, this is a nice point that high cycle fatigue is reducing, but ultimately what the case that performance should not be changed. So that's why we have to balance both things. So while analysis, we are having the same case, which is reducing the Fourier, reducing the high cycle fatigue up to 70 to 80%. But what we end up, the performance is changing around 5%. So we neglect those cases. I understand, because in this case, the high cycle fatigue is reducing around 30-40%, and in the subsequently in experimental analysis, the percentage changes it is conditioned that it within the range of 1%, plus minus 1%. So that is the change.
What was the gap change between vein and tongue?
What was the gap
change between tongue location and vein tip? Because when you are increasing the area, it means there will be change in the gap, increase in the gap.
Yeah, so basically we use the two methods to maintaining or checking the design turbine. So in which we have to maintain the minimum acceptable distance, whether we are using the casting method for manufacturing the turbine or the machining. So what we do, we have some minimal acceptance distance. So what our area of concern, that we should design the turbine housing or increasing the turbine housing within the range of those minimum acceptance distance. So it is different from the different case. The turbine which is our use, we used in a small size of turbine. Later it is implemented for medium size turbine as well as the higher size, higher turbine, means higher size turbine. So it is a different from different case, but it having the minimum acceptance distance. Without checking the minimum acceptance distance limit, we can't go ahead with the our analysis.
You have presented two cases. What is the difference in those two cases? One is modified and one is original.
Yeah, so original cases is there. The original cases, the failure is we saw failure in experimental analysis. So what what the suggested problem, you should design a turbine in such a way that reducing the high cycle fatigue. So the modified turbine is like that, which changes the geometry of the turbine, which reduce the high cycle fatigue, and plus which is not changing the performance of turbine. So in original turbine, we saw high cycle fatigue failure, which is recorded after the 10 raised to 7 or 10 raised to 8 cycle. But with the modified geometry of turbine, those intention of high cycle fatigue is reducing up to 30 to 40%. So that is the main concern.
So in the interest of time, I think we should move on. Let's thank Vignesh. Thank you very much.
Thank you.
Do keep up your good work.
Thank you, FMFP, for providing a good opportunity to present. Yeah, thank you, Pradeep. Yeah.
Thank you. Let's move on to the next talk. This is from, I think, the IIT Madras group. The paper is going to be presented by Saddam Hussain. We're going to talk about flow visualization and measurements in a lube test rig for an air turbine starter. So let's get started with this presentation now.
Yeah, very good morning to all. It's my pleasure to introduce myself. I'm Saddam Hussain. I'm a research scholar. I'm doing my PhD program in the Mechanical Engineering Department, Indian Institute of Technology, Madras. I'm going to give a presentation on flow visualization and measurements in a loop test rig for an air turbine starter. Co-authors BVSSS Prasad from IIT Madras, Milan Dave from GE, Subrata Nayak from GE, and Ramkumar P from IIT Madras. Orientation of the presentation. Start from introduction, objectives, experimental setup, flow visualization, flow rate measurement, temperature measurements, and then summary and conclusion. Let me start with the introduction. In any rotating system, heat is generated at several critical components which may lead to their failure. The major purpose of lubrication system is to minimize power loss, heat generation, and wear and tear of critical components. The proper operation of lubrication system is critical for reliable functioning of an air turbine starter. The ATS consists of rotor, gearbox, and clutch, which are supported by multiple ball and roller bearings. As you can see, typical view of pneumatic starter or air turbine starter. Here, this is the air inlet. Here is the air outlet. This is turbine rotor. This is reduction gear. This is clutch. This is engine drive shaft. And the ATS, when high pressure air expands in the turbine stage, which rotates the turbine wheel at high speed. The ATS output shaft is connected to the main engine via a bicyclic gearbox. Here, the carrier of gearbox passes the lubricant in the housing onto the bearings of ATS, like turbine side bearings, drive side bearings, carrier arm bearings. From the previous experience, shows that one of the causes of failure of ATS functioning is the inadequacy of lubricant to the turbine bearings as well as drive side bearings. The operational time cycle of ATS depends on the lubrication of all the bearings. The advantage of splash lubrication is that it does not require oil pump and oil filter. Existing lubrication system. As you can see, left side figure, this is pneumatic starter with lubrication system. Here is the lubricant source. This is supplemental lubricant pump. With the help of pump, oil filled here the sump location. When start to rotate the disc, it will splash the oil towards these bearings as well as critical components of ATS. This right side figure, this is schematic view of air turbine starter. As you can see, this is the air inlet, turbine disc, this is shaft, sun gear, output shaft, clutch, and then this is the nozzle, this is shaft. Objectives. To design a loop rig test setup which resembles the flow of a lubricant in the ATS, to visualize and quantify the loop flow to the bearings regions of a air turbine starter, namely turbine side and drive sides, to understand the flow circulation, to measure the shaft and loop oil temperature to check the adequacy of the loop oil cum coolant. Coming to the experimental setup, based on our objective, we have designed fabricated loop test rig. This is schematic view of experimental setup. This side we will call it as turbine side. This side we will call it as drive side. Here there is an experimental setup used for this study, consists of loop rig to supply loop oil to the air turbine starter, and a support system of ATS or DC motor, thermocouples, and infrared camera. Here the loop test rig components like sun disc, carrier ram, turbine bearings, and drive side bearings are mounted on the main shaft, which is supported by the two bearings at the end. This test setup is designed such a way that structural loads and vibration of the shaft will be transferred to the support bearings at the ends. Like you can see, this is a bearing housing in right, and this is bearing housing left side. The housings, all the housings are made up of transparent material to visualize the flow field of the lubrication. In this experimental setup, the test rig is connected to the motor, the drive shaft and driven shaft is connected with the help of love coupling. As the lubricant oils passes, it reaches various internal parts of housing, as I said, like bearings and bearing holders. The DC motor is connected to the control valve. The drive unit helps to vary the speed of motor from 0 to 10,000 RPM, as well as to indicate the current, voltage and RPM. This is a photographic view of the experimental setup. As you can see the left side figure, this is the oil storage tank, this is DC control drive, this is test unit. This is 3 outlets from the unit, S1, S2 and S3. Then here is a collection charge with immersed thermocouples. As you can see the right side figure, this is, we can call it as turbine side, here is the drive side. So 3 outlets like station 1, station 2, station 3. S1 and S2 are loop oil collection from the turbine side bearings. S3 is loop oil collection from the drive side bearings. Here the bearings are visualized with the help of video camera. Let me see the video clip. Here I am explaining how we are measuring shaft temperature with the help of IR camera. This is IR camera. We are focusing on the shaft. After running 2 minutes of experimental run at each operating speed, the IR image can be generated with the help of LabVIEW software. This is the red hot point. This is the shaft location. This is the shaft. At the same time, we will get current and voltage and RPM with the help of DC control drive. Coming to the flow rate measurement, the flow rates are measured at 3 locations, S1, S2 and S3 by volumetric collection. The flow rates are measured after 2 minutes of experimental run at each operating speed. As you can see the figure, and this is a test setup with a loop flow rate measurement. This is the station S1, S2 and S3 location. This is drive side, this is turbine side. Coming to the results and discussion, the flow rates are measured after 2 minutes of experimental run and at each operating speed, and the values are tabulated here. The percentage of full speed from 7% to 100%. This is turbine side oil flow rate S1 plus S2. This is drive side oil flow rate S3. And then right side table, turbine side oil flow rate splits, S1 flow rates value and then S2 flow rates value. With the help of these values, we have plotted a graph. Let me see the graphical representation of speed versus flow rate. So this is a graphical representation of speed versus flow rate. You can see the left side figure. This is the blue color line is turbine side flow rate, orange color line is drive side flow rate. When compared with drive side flow rate, the turbine side flow rate is very low, up to 61% of speed. After that, turbine side is increases and then drive side is decreases. Here, as you can see, at 61% of speed, the turbine side flow rate comes to flow rate is suddenly comes to 21%. So because of this sudden drop, the oil flow rate, the bearing leads to failure or other critical components. So on the right side figures, this is a graphical representation of speed versus flow rate only at turbine side. This is station 1, blue color line station 1, orange color line station 2. Temperature measurement, loop oil temperature. Here experiments are conducted at various shaft speed. The thermocouples are installed to measure temperature at 3 bearings location, S1, S2 and S3. As you can see the figure right side, S1, S2 and S3. This is a test setup with loop and temperature measurement location details. And the three location loop oil temperatures and shaft temperatures are recorded before and after 2 minutes of experimental run at each operating speed. The loop temperatures are tabulated. Like this is initial temperature, this is station 1 temperature values, the station 2, station 3, this is all are non-dimensional temperature values. Initial temperature, these values are at degrees Celsius. Here as you can see right side graphical representation, the non-dimensional loop oil temperature as a function of speed. You can see the table from 7% to 35%, the non-dimensional values are keeps on increasing. But after that, the values are increasing and decreasing like that happen. So from the graph, I mean, you can see the graph, like loop temperature is not linear. So more deviations are there, some at some speeds. So at these points, the loop is not adequate. So at these points, the critical components leads to failure. Shaft temperature measurement. The temperature of shaft is captured by IR thermography at very sharp speed, and the shaft is painted black, and the emissivity of measuring point O is found to be 0.97. So you can see IR thermal images at different shaft speed. The shaft temperature at 7%, 35%, 69%, and 100% of maximum speed. In all thermal images, O highlighter is there, that is the shaft location. The second picture clearly shows that red hot temperature. In all figures, maximum, minimum, and average temperatures will appear. From the IR images, the minimum, maximum, and average temperatures are recorded and tabulated. As you can see, the left side table, the right side figure represents the graphical representation of speed versus shaft temperature. In this graph, the temperature of shaft is increasing approximately up to 85% of speed. After that, deviations are there. More deviations are at 61%, 96, and 100% of speed. As I explained previous slide, about loop oil temperature. When shaft temperature increases, the loop oil temperature also should increases. But loop oil temperatures are not linear. It's not increasing continuously, so it is decreasing and increasing. At this operating speed, the critical components of like bearings and other components leads to failure. This may be because of inadequate of lubricant. Coming to repeatability, each test was repeated 3 times. As you can see the left side table, this is the repeatability of turbine side oil flow rate, test 1, test 2, test 3, and then actual values. This is turbine dry side oil flow rate, test 1, test 2, test 3, and actual values. All the values are here. So here this right side figure, first figure, graphical representation of repeatability for S1 plus S2. This is turbine side. All the values are almost in the same point. And similarly, graphical representation of repeatability for dry side oil flow rate. So the maximum deviation among the different sets of reading is less than plus or minus 1.5%. So all these values of oil flow rate, oil temperature, and shaft temperature reveal that the test values are repeatable. Summary and conclusion. A flow visualization rig simulating lubricating oil flow inside an air turbine starter has been designed and operationalized. And the rig has been used to visualize the flow of lubricant around the turbine and drive side shaft bearings. The lubricant is uniformly distributed over the bearings at low speeds. However, at high speeds, a separation bubble appeared on the disc. The rig is used to quantify the lubricating oil flow rates through the turbine and drive side bearings of the loop rig. When compared with the turbine side, the drive side flow rate is larger up to 61% of shaft speed. After that, the flow rate increases at the turbine side and decreases at drive side. The variation of the loop oil and shaft temperatures also indicate the behavior of the flow. The repeatability test indicates that the readings of flow rate, oil temperature, and shaft temperatures are repeatable within plus or minus 1.5% range. And the loop flow visualization rig described in this paper and the associated procedure can be used to perform studies aimed at improving the oil flow rates to the air turbine starter bearings. These are the references. Thank you.
All right. Thank you very much, Saddam. Nice presentation and nice work. So the floor is open for questions. If anyone has questions, you may please raise your hand and go ahead. So while someone else is asking questions, Saddam, I have a question on does your test rig have provision to add dye to the oil to enhance the visualization, or you just use the oil as it is?
We just used oil, sir. That's all.
So is the clarity good enough for you to make visualization? Yeah.
No, sir. Actually, we supposed to do like with a dye setup, but we have not tried. So
Okay.
we completed last month only.
I see. Okay. Thank you. Okay, if there are no further questions, then let's thank Saddam Hussain for his wonderful work, and do keep up the good work, Saddam.
Thank you, sir. Thank you so much.
Welcome. Okay. Let's move on to the next talk. This is by Parag Rajpara, who is going to present the talk. And co-authors are Professor Rupesh Shah and Professor Banerjee from NIT Surat. Parag is going to talk about improvement in combustion and emission characteristics of methane-fueled upward swirl can combustor with hydrogen enrichment. So let's start with Parag's talk.
Hello everyone, myself Dr. Parag Rajpara. My topic of presentation is improvement in combustion and emission characteristics of methane-fueled upward swirl can combustor with hydrogen enrichment. The work presented here is a part of my PhD research work. Contents of presentation are research background, literature summary and objectives of present work, materials and methods, results and discussion, and conclusions. As we know that swirlers are popularly used in combustion systems to achieve faster mixing between fuel and air. In conventional combustor, the swirlers are mainly provided on the upstream end of the combustor. The swirling flow induces a strong recirculation region in the primary zone, which ensures better combustion efficiency and flame stability. However, the strategy of creating a recirculation region has disadvantage that it increases the residence time of the combustion products, which in turn favors the generation of thermal NOx emission. Also, the interaction between fuel, swirling air, and the primary jets creates a flow distribution that sets the combustor liner to a very high temperature. In order to resolve these problems of conventional combustor, the philosophy of upward swirl combustor was introduced. In upward swirl combustor, the swirler is positioned between primary zone and secondary zone. The primary air is forced to flow through a swirler in the primary region in reverse axial direction. The primary air and fuel interacts close to the combustor axis, and the products of combustion mainly flows in the vicinity of the combustor center line. This in turn reduces the liner roll temperature significantly in upward swirl combustor as compared to the conventional combustor. Also, the alteration in primary air direction reduces the hotspots of high temperature gradients in the primary zone of upward swirl combustor. This in turn reduces the generation of thermal NOx emission from upward swirl combustor. However, the major drawbacks of upward swirl combustor are it has poor combustion efficiency and it emits very high amount of CO emissions as compared to the conventional combustor. And this is mainly because of the improper mixing between fuel and air in upward swirl combustor. The main aim of this project is to enhance the combustion and emission performance of upward swirl combustor. In order to accelerate the combustion chemistry in primary and secondary regions, the fuel distribution system and air distribution system of upward swirl combustor were modified, and it was observed that the modified upward swirl combustor offers potentially improved performance as compared to the conventional combustor. In this research, all the experiments were initially carried out using methane as fuel. Now, we know that over the past few years, effort has been made to replace traditional fuels by environmentally friendly alternative fuels. And over the past few years, the use of hydrogen as an alternative fuel for gas turbine has been increased because of two main reasons. One is increased cost of fossil fuels, and the other is the negative impact of exhaust gas emissions on climate. Since hydrogen is a carbon-free and high energy density substance, the addition of hydrogen in methane or natural gas makes the system partially carbon free. It also promotes the rate of chemical reactions and reduces the concentration of CO emissions in the exhaust gases. It also extends flammability limits and reduces the overall fuel mixture cost. The main aim of the present work is to outline the role of hydrogen as a supplementary fuel in methane-fueled upward swirl combustor. In the present work, the effect of hydrogen enrichment on chemical kinetics, flame characteristics, and emission levels is analyzed under constant energy input condition. In a present work, the experimental method is used to measure the emission levels. These emission levels are measured using flue gas analyzer. All the experiments are performed under standard atmospheric conditions. In present work, the different methane hydrogen mixtures containing hydrogen concentration from 0 to up to 10% are used. The total energy input to combustor and total airflow rate at the combustor inlet are kept constant for all methane hydrogen fuel mixtures. The total energy input to combustor is calculated as mass flow rate of fuel multiplied by its lower calorific value. The total energy input to combustor is equal to 70 kilowatt and it is calculated based on the maximum fuel mass flow rate that can be obtained from the existing setup. The values of fuel mixture mass flow rate and the corresponding value of equivalence ratio for different methane hydrogen mixtures are presented in this table. Details of numerical modeling and analysis are provided here. The CFD analysis of reactive flow in combustor is performed using ANSYS Fluent. The turbulence is modeled using a large eddy simulation approach. For chemical reactions, a presumed shape probability density function approach is used. In order to include the effect of radiation on combustion, a discrete coordinates model is used. In present simulations, in the present work, the simulations are performed mainly for two cases. 0% H2, that is pure methane combustion, which is taken as a reference case, and methane hydrogen mixture containing 5% hydrogen. All the inlet surfaces of air and fuel are declared as mass flow inlet, and the outlet of the domain is declared as pressure outlet. Now coming to the results and discussion, the chemical kinetic effect of hydrogen addition is analyzed by plotting mole fraction profiles of several selected species. The flame species including CH4 and CO2 and the free radicals including OH and OH are selected to analyze the effect of hydrogen addition on chemical kinetics. The results are plotted on a plane perpendicular to the combustor axis at three different axial locations. Plane B is selected in primary region, plane D is located in the secondary region, and plane M is located in the dilution region. Now, the mole fraction profiles of CH4 are plotted on a plane perpendicular to the combustor axis at three different axial locations, and they are compared for pure methane combustion and methane hydrogen mixture containing 5% hydrogen. It is observed that the mole fraction of CH4 decreases when hydrogen is added to methane as compared to the case of pure methane combustion. On the other hand, the mole fraction profiles of CO2 reveals that the CO2 mole fraction increases in combustor when hydrogen is added as compared to the case when methane alone is burnt. This increase or decrease of the carbon-related species is partially due to decrease in the CH4 reactant mole fraction and partially due to chemical kinetic effect. The major reactions that are contributing to the CH4 consumption are the reactions of this reactant CH4 with the intermediate species. These intermediate species are very active during combustion and they play a vital role in combustion reactions. To interpret the chemical kinetic effect of hydrogen addition, the mole fraction profiles of this intermediate species are plotted on a plane perpendicular to the combustor axis at different axial locations. It is observed that when hydrogen is added to methane, the formation of intermediate species, the mole fraction of the intermediate species are increased as compared to the case of pure methane combustion. The major reactions which are contributing to the formation of this intermediate species are these two reactions. As the H2 mole fraction increases with hydrogen addition, the rate of reaction of this equation increases and thus it forms more amount of H. And therefore, the rate of reaction of this equation is promoted. Therefore, the rate of consumption of CH4 increases as the rate of reaction of this equation is promoted. This implies that the combustion reactions are intensified and the combustion of methane air flame is promoted. Also, the increase in CO2 mole fraction with hydrogen addition is mainly attributed to increase in the OH radicals, which promotes the oxidation of CO into CO2. Now, the effect of hydrogen addition on flame characteristic is analyzed by plotting temperature contours on horizontal plane and vertical plane of combustor, and they are compared for pure methane and methane hydrogen mixture containing 5% hydrogen. The temperature distribution reveals that addition of hydrogen up to 5% in the fuel mixture does not significantly change the flame region. However, for the same energy input, the average values of the magnitude of average temperature across the combustor is increased when hydrogen is supplied. The higher average temperature are mainly attributed to increase in the OH radicals due to higher combustibility of hydrogen than methane. This indicates that the burning rate of the fuel are augmented and the combustion is promoted. Then effect of hydrogen addition on emissions. This figure shows that the addition of hydrogen at same energy input reduces the CO emission levels, while the NOx emission levels are increases at with hydrogen percentage. The reduction in CO emission with hydrogen addition is mainly attributed to increase in the OH concentration, which encourages the faster conversion of CO into CO2. On the other hand, the rise in NOx emission with hydrogen addition is mainly related with the rise in the temperature of flame. As we have seen that the addition of hydrogen increases the mole fraction of intermediate species. This species increases the rate of combustion reactions and the rate of energy transfer during combustion. The kinetics of this equation increases with increase in the radical molar fractions, which in turn favors the generation of thermal NOx emission with hydrogen percentage. It is observed that when hydrogen is added up to 5% in the fuel mixture, CO emissions are significantly reduced without relevant increase in the NOx emission. However, increase in hydrogen concentration from 5% to up to 10% in the fuel blend has little effect on the CO reduction, but it has significant effect on the NOx, on the increase of NOx emission. Now, conclusions. The major conclusions from the present research are: addition of hydrogen increases the mole fraction of intermediate species, which in turn promotes the rate of chemical reactions. Addition of hydrogen up to 5% has very little effect on the flame region. However, higher combustibility of hydrogen increases the average temperature within the combustor, which contributes to improved combustion. Also, addition of hydrogen up to 5% can significantly reduce CO emissions without relevant increase in the NOx emissions in the exhaust gases from upward swirl combustor. Here are the references used in the present work. Thank you so much.
Thank you, Dr. Rajpara. So, we have any questions from the audience? You can please raise your hand and ask questions. Yes, please go ahead, Varghese. Is there a question from Varghese? Raised your hand. You're muted, Varghese, if you're asking a question. I think there is a raised hand, but I don't see any question. So, if there are no further questions, I think let's.
Hello.
Yes, please. Yeah.
Yeah, I just wanted to know whether any combustion instability associated phenomena is seen.
Sorry, sir, I didn't get the question.
Did you see only steady combustion, or what about combustion instability? Did you analyze that?
Sir, in this particular work, we didn't worked on combustion instability. Our main focus was on improving the overall combustion and emission performance was of upward swirl combustor.
Okay.
All right. Thank you so much, Dr. Raj Parag, for your interesting presentation.
Thank you, sir. Thank you.
So let's move on to the next paper. So the next paper is to be presented by Devesh Singh. He will talk about effect of casing geometry on the performance of centrifugal pump. So let's start with Devesh Singh's presentation.
Hello everyone, I am Devesh Singh. My paper ID is 052 and I am presenting here effect of casing geometry on performance of centrifugal pump. These are the table of contents and then introduction. Centrifugal pump is a machine that is used to transport fluids by the conversion of rotational energy to the hydrodynamic energy of the fluid flow. Fluid enters through the pump impeller along the rotating axis and is accelerated by the impeller. Flow into the valve chamber. This is the valve chamber from where it delivers through delivering pipe. This is the delivery pipe. And design of centrifugal pump is mainly divided into two subcategories. First one is impeller design and casing design. Impeller design is a rotating element, while casing design is a stationary element, which is an airtight passage surrounding the impeller. And it is designed in such a way that the kinetic energy of the water discharge at outlet of the impeller is converted. These are the three types of walled casings: volute casing, vortex casing, and diffuser casing. Volute casing is a spiral type in which area of flow increases gradually, where in vortex casing a circular chamber is introduced in between the casing and impeller. In diffuser casing, in this type of casing, impeller is surrounded by a series of guide vanes mounted on a ring, which is known as diffuser. And objective of the present work to compare the performance of different types of cross-sectional shapes like a circular, rectangular, and trapezoidal type of shapes. Volute casing of different types of cross-sectional shapes are then modeled and then analyze the performance characteristics. To study the pressure control of all the above mentioned volute cross-sectional shapes, based on the performance characteristics of different volute shapes, appropriate cross-sectional shape will be determined. The methodology used in this to fulfill these objectives. First is primary is the initial design of these type of volute casings, then geometry generation, then after that mesh generation to create a flow domains, then after that pre-processing where we can in giving input as boundary conditions, then after solver, then results, and then after the analysis of results we can come decide appropriate cross-sectional shape of volute. 3D design of impeller blade. This is the simple blade, and this is the blade with impeller outlet, and this is the complete assembly of impeller. This is the hub and shroud, and this is the dimension of casing. All casing dimensions are having with inlet diameter of casing same as a 1100 mm and exit area of 1376 mm square. This is the circular volute casing. Second one is the rectangular volute casing with aspect ratio of 0.7, and this is the trapezoidal volute casing. All are have similar exit area, and this is the complete assembly of centrifugal pump. This one is of centrifugal circular type of volute, and this is the rectangular type of volute casing, and this one is the trapezoidal type of casing. Mesh generation of impeller domain. Discoloration of the impeller. It is of structure type of meshing, where total number of nodes are 3,42,800 and 3,816 total number of elements. And boundary conditions are applied at the inlet and outlet domain of the flow passage along with the walls surrounding the flow domain. domain is taken as fluid domain and fluid is water at 25 degrees centigrade with reference pressure at 0 atm. Average static pressure of 1 atm is given at the inlet as the inlet boundary condition, and mass flow rate of water in given at the outlet of casing as the outlet boundary condition. Grid independency test. Overall performance of the centrifugal pump is first checked based on the mesh independency and turbulence model. For mesh independency test, variation of efficiency and impeller head of circular type of volute casing with flow discharge of 4000 meter cube per hour is studied at different number of elements, and then it is concluded that the impeller head and efficiency were mesh independent after 49,277 number of nodes. For selection of turbulence model, the setup file was simulated with different turbulence model in ANSYS CFX, and then corresponding their efficiency and head were found out. In this figure, we can consider that the hydraulic efficiency of the centrifugal pump for different turbulent model. It was found that the efficiency in case of SST model for all three types of the casing design was higher than the other turbulence models. Similarly, in case of the impeller head, so we can conclude that the SST model is used for further analysis. See there, as we can increase the discharge constant speed, pressure head decreases as the outlet of the volute casing. So this is the case of 3600 meter cube per hour. So maximum pressure head is like a approximate 75, and then this one is the case of the maximum discharge. And this one is the case for rectangular type of volute casing. Here also we can conclude that as the discharge is increases, the pressure maximum pressure is decreases. And we can see then here the maximum pressure is like a 743 kilopascal approximate, and here is 713. And at the higher discharge, it is approximately 640. And this one is the for temperature type of volute casing. Here in this case, similar pattern is followed. Maximum pressure decreases with increment of the volute discharge. Formula used. Various flow parameters are calculated in non-dimensional form to observe the pump performance deviations at various flow discharges. Expressions used to calculate these non-dimensional flow parameters are as shown below: flow coefficient, head coefficient, and power coefficients. After the completion of the numerical flow solution, flow parameters are calculated and will be put in a table format. Like this is the for circular type of volute casing, and this is the for rectangular type of volute casing. This one is for tabular type of volute casing, and this is the parameter of pump performance for all three types of volute. Geometry can be observed and compared by plotting graphs of some flow parameters such as hydraulic efficiency, impeller head, and pressure coefficient with respect to flow coefficients. So here we can see that as the at low discharge of flow coefficient, we can convert that rectangular type of volute casing can be considered, while at the higher flow coefficient we can consider for circular type of volute casing according to hydraulic efficiency and impeller head and pressure coefficient. And all are from these all three figures we can conclude that at low discharge we can use rectangular type of volute casing, and at high discharge we can use circular type of volute casing. It is observed that the hydraulic efficiency follows the parabolic nature of the curve, and in the impeller head for all the volute decreases as the flow discharge increases, which is also the pump characteristics of centrifugal pump. And it is also observed that the pressure coefficient for all the volute decreases as the flow discharge increases, which it is represents the characteristics of centrifugal pumps. Conclusion: the float simulation is carried out at constant rotational speed of 600 rpm with varying flow discharge with a constant interval of, and then for centrifugal pump with three different type of volute case geometry, it is observed that the centrifugal pump with rectangular volute geometry performs better at low discharge, but efficiency of circular casing is higher at at high flow conditions. This may be because of surge generated at the corner of the rectangular and trapezoidal cross sections at high flow conditions. The study may be useful for design improvement of the casing of centrifugal pump. These are some reference. These are the books we followed. Thank you to everyone. Here I am concluding my presentation.
Thank you, Devesh. Shyam Shukla, you have a question? Please go ahead. Yeah.
What is the specific speed of this pump which you have taken for?
This is 650 rpm I am taking.
Pardon? This is the speed of the pump. I am asking about the specific speed of the pump.
Devesh, the question is about specific speed.
G. Specifically, I am taking 600.
600 is the speed of the RPM, revolution per minute of the pump. I am asking the specific speed in NSUS or maybe NSQ or NSL, any unit.
Okay, I am just consider the RPM, 600 RPM, I think.
So I think Devesh, you need to look up what is the specific speed. Normally in pump literature, the speeds are converted to specific speeds. Yeah. So you can just look up. Maybe you have not calculated it yet. You have to convert RPM to specific speed. Yeah.
Yes. I am taking consider, but now at time I am not remember that what is the value at that time.
All right. Shraman, you have a question? Yeah.
Yeah, when you mentioned that you have mentioned different cross-sectional values, you have types. You are getting different flow like pressure rise or efficiencies at different flow coefficients, right? And it looks like your rectangular is more. It is better all across the any flow visualization in terms of because you did numerical analysis. I think that's okay.
Yeah. In case there is some region where rectangular cross section is better, and is some region where circular type of volute is better, and at higher volume discharge, circular type of volute is better, because here in this case occurring losses are less in comparison with rectangular. So in high region, circular type of volute is better, and in lower region and
when you're saying that losses, definitely the losses are changing, but what is that is causing the losses to change? Like for the same circular or the same flow rate, same velocity regime, like definitely it's a pump, so there is no change in velocities for the same mass flow, right? So in that case, what is causing this, the change in losses?
Turbulence created.
Would have been nice to see some contour plots as the flow develops from the volute, along the volute, basically. To have thrown up some light in how the flow is developing. Yeah, thanks. Nice presentation.
Okay, thank you.
All right. Thank you very much, Shaman. Thank you, Devesh.
everyone.
All the best.
Yes.
Thank you.
Thank you.
Let's move on to the next talk. This is to be presented by Ashima. She's going to talk about effect of surface roughness levels on axial compressor rotor performance. So we'll start with Ashima's presentation now.
Hello everyone. The topic of this presentation is effect of surface roughness levels on axial compressor rotor performance. So during this presentation, we'll be covering the following content. We'll begin with the motivation behind choosing this topic. Then we'll go to the objective. And since this is a numerical investigation, we'll go through the validation of the numerical methodology, then results and discussion, followed by conclusion and references. So the motivation behind this topic is, as we all know, that axial compressor performance plays a major role in the overall performance of the gas turbine engine. And one of the most significant loss in the axial compressor is due to surface roughness. As one of the researchers has reported that almost 45% of the total performance loss was coming because of the surface roughness. Hence, the study of the impact of surface roughness is important to build better designs, build better manufacturing strategies, and to have better prediction of maintenance schedules. The objective of this paper is to study the impact of different surface roughness levels on axial compressor rotor aerodynamic performance using numerical analysis and to understand the underlying flow physics. To validate the numerical methodology, a test case of NASA rotor 37 is taken. So first the baseline rotor is validated, then the validation of rough rotor is done with the experimental data provided by Suda. Now to make the rotor blade rough, Suda coated the baseline rotor blade with rough paint. That roughness paint had a value of 100 to 125 RMS microinches. But while coating the rotor blade with rough paint, it not only added roughness, but it also added thickness to it. So just to segregate the effect of thickness and roughness, he also coated the rotor with a smooth paint. So the smooth paint had the roughness value similar to the baseline rotor, but thickness is added to that. Therefore, for this study, we have validated all the three cases: baseline rotor, smooth rotor, as well as the rough rotor. So let us begin by the baseline rotor validation. So on the left hand side, you can see the NASA rotor 37 geometry. And on the right hand side, there are some geometrical parameters related to NASA rotor 37. Meshing is done using Numeka AutoGrid 5. And all the best practices for meshing are followed, like maintaining the O-grids at the leading edge and trailing edge. 3 different types of meshes, a coarse, medium and fine mesh, based on the number of node counts of 1 million, 2 million and 3 million respectively, are considered to do the mesh sensitivity study. So the boundary conditions are maintained as it was given in the paper, just to get more fidelity. The mesh sensitivity results show that the medium mesh is having a very good match with the experimental data, and taking the uncertainty into account, there's a good match with the experimental data. So similarly, a turbulence model sensitivity study is carried out by using various turbulence models such as BSL, SST, SA and BSL with laminar turbulent transition. So out of all these, the BSL model, which is the baseline K omega model, which is a CFX specific model and a combination of K epsilon and K omega model. So this BSL model shows the best match with the experimental data. So we decided to go ahead with the medium mesh and BSL model. So the final results for the baseline rotor validation are here. Here we have just shown the 1D total pressure ratio and efficiency and 2D total pressure ratio and efficiency. So both the charts show that there is a good match with the experimental data. Now to validate the smooth rotor, a thickness of 0.025 mm is added all over the rotor blade. So the results indicate that CFD is not able to capture the impact of the thickness change at all the operating points. So So this has also been reported by various other researchers. For our study, it is important to see if roughness impact is captured by CFD or not. Therefore, for further analysis on the rough blade, we'll see the delta values between the rough rotor and the smooth rotor. So for the rough rotor also, turbulence model sensitivity study is carried out with different turbulence models such as BSL, SST, SA and BSL with laminar turbulent transition. So the results indicate that BSL model predicts the performance to a good extent, and taking the uncertainty of 1.72% into account, this shows a good match with the experimental data. For the rough rotor validation, here we can see the performance map of total pressure ratio versus corrected mass flow rate. And if we compare at 20.31 kg per second, because the experimental data is also compared at that point, so we'll see that the percentage difference between the experimental data smooth and rough and the percentage difference between CFD data smooth and rough is almost similar, taking the uncertainty into account. Therefore, we can say that the impact of roughness is captured by CFD to a reasonable extent. So the Mach number counters at 70% span are also plotted, and this experimental data as well as CFD data match to a very good extent for the Mach number counters as well. And then the shock location at 70% span as given in the experimental data is plotted in CFD, and from here we can see that the baseline smooth and rough rotor show a similar trend. Therefore, CFD is able to predict the results to a very good extent. And hence we will say that our numerical method is validated, and we will move forward by using this method. So moving to the results and discussion section. So here we considered 4 different roughness levels, say having the equivalent sand grain roughness value of 9.84 micrometer, 20 micrometer, then 29.75 micrometer and 40 micrometer. And we applied this roughness on the rotor blade, and now we will see what happened when we applied roughness on the blade. So with this graph, we can see that the pressure ratio kept on reducing as we increased the roughness. And similarly, the adiabatic efficiency also kept on reducing. So one thing is that there is a reduction in the performance as roughness is applied. And this reduction in performance is not constant between any 2 levels of the roughness. So the reason for this deterioration in performance, which we saw in the 1D performance map, can be attributed to the fact that when we apply the roughness, the turbulent kinetic energy increases. So as we can see in this picture, that for the smooth, we had the lowest turbulent kinetic energy, and for the rough with 40 micrometer, we have the maximum turbulent kinetic energy. Now this increase in turbulent kinetic energy and hence the mixing results in an increase in entropy. So this increase in entropy gives us the loss, which is represented by also the total pressure in relative frame, which will be maximum for the rough rotor with the 40 micrometer. So here one thing is that as we apply roughness, there is performance deterioration, and between any 2 levels it is not constant, because what we see here is that as we keep on increasing the roughness, say from 30 to 40, there is a marginal change. So there was a lot of change when we apply roughness from smooth rotor to 10 micrometer, and from 10 to 20 also there is a change, 10 to 30, but there is no change from 30 to 40. So here, not only the performance parameters like total pressure ratio and efficiency are impacted due to the roughness, but also the choke flow is impacted. Now, as we can see from the graph, there is a reduction in the choke flow as we increase the roughness. This is because roughness increases the boundary layer thickness as shown on the right hand side figure and acts as a blockage. Due to this blockage, the throat area is reduced and hence the choke mass flow is reduced. Now another point to be noticed here is that the boundary layer thickness is almost constant when we increase the roughness from 30 micrometer to 40 micrometer. Thus, the impact of roughness is observed between 10 to 20 micrometer, but the impact of roughness is not similar between 30 to 40 micrometer. Now, in this graph, it can be seen that the performance deterioration is observed at all the spans from hub to shroud, and the performance deterioration at any two roughness levels is not constant at any span location. To conclude, it can be said that the performance of the rotor, say in terms of total pressure ratio and efficiency, deteriorates with roughness as loss increases because of increase in wall shear and turbulence kinetic energy. Another point is that this decrease in performance is not constant between any two roughness levels. For example, higher pressure ratio drop is observed from 10 micrometer to 20 micrometer as compared to pressure ratio drop from 30 micrometer to 40 micrometer. Another parameter, choke flow, reduces with roughness as the boundary layer becomes thicker. And the deterioration in the performance is observed from hub to shroud at all these span locations. These are some of the references which I used while making this presentation. There are other references which are also referred while writing the paper, the details of which are already given in the paper.
All right. Thank you, Ashima. So the floor is now open for any questions. Yes, Shyam, you have a question?
As it is said in the presentation that thickness effect is not captured by CFD, isn't it? So what could be the reason, and have you checked the solidity ratio, solidity of the runner?
So yeah, the thickness impact is not captured, and we validated that this is the same reported by other researchers as well. So there might be two reasons for it. One might be like the coating was not smooth when it was done in the experimental data, and we have not captured the 3D coating. We have applied a uniform coating everywhere, and the experimental data might be capturing some haphazard coating value which is present there. But we see that the impact of roughness, thickness is captured in the choke side when the throat area is increased. So we cannot neglect that because of the solidity and stuff, it is not captured. It might be that it is non-uniformity in the roughness applied, because of which this is coming in the experiment. Another thing is that we are using RANs here, and we are doing the averaging. So it might be the value might be so small that it is not captured in CFD. And if we use other models like LES, we might be able to capture it. So, but right now the concern was whether roughness is captured in this or not. So we went ahead with the differences in the smooth and the rough rotor and went ahead with the validation.
Yeah. So solidity says 36 numbers of veins are there. So
Correct.
solidity with respect to total periphery and with respect to surface roughness. If we can see to it, then it can give some answer to our own questions. Thank you.
Sure. Thanks, Shyam. We'll look into that as well.
There is another question from Nishab. Ali, you have a question?
Yes, sir. Hello, Asma.
Hi.
Is it audible? Okay,
Yeah, your voice is, yeah, please go ahead.
Thickness level is selected 9.84 and 29 point something. What is the basis of selecting these roughness parameters?
Okay, so the experimental data which was available with us was 9.84 micrometer. And then we went ahead and chose a paper by Gilje in which he has taken this 29, whatever value we have reported at 29.75 micrometer. So it was a operationally gas turbine engine. It's a GE engine which was operated for 20,000 cycles. And after that, he has reported this value of 29. So now we had the 10 micrometer and kind of 30 micrometer. So we thought of having an in-between value of 20 and a higher value of 40 just to see how the variation is there. So it's based on the operationally rough blade. and one is from the validation.
Is there any optimization of these values? Means the conclusion should be means what should be the optimum value of the roughness, so that there is means the maximum performance of the axial compression. Means what is the optimum compression means value of the roughness level.
So from the aerodynamic performance point of view, we actually do not want roughness. Addition of any roughness is interrupting our viscous sublayer and making it turbulent, which is adding the loss there. But from the heat transfer point of view, we need some kind of roughness. So we have not done any interaction study from that, but from the aerodynamic performance point of view, we do not want any roughness.
As possible is good. Okay, thank you.
All right. Yeah, sure. Thanks.
All right. Let's thank Kashima for her talk. Thank you very much.
Thank you, sir.
And we'll move on to the next paper now. Next talk is by Nishab Ali and co-authors. He's going to talk about flow investigation at U-turn with and without matrix in a 2-pass rectangular duct using stereo PIV. So let's start with Nishab's presentation.
Hello to everyone. The topic for this presentation is flow investigation at U-turn with and without matrix in a 2-pass rectangular duct by using stereo PIV. Now, first of all, I will try to introduce the gas turbine and its blades. As we know that the gas turbine, the high temperature and the process gases from the combustion chamber expand on the vanes of gas turbines, where it produces a very high heat flux on the leading and trailing edge across the whole of the pressure and suction side of the blade. This is the pressure and this is the suction side. So this high heat flux has to be removed for the continuous operation. Now we will discuss what is the requirement of the cooling of these gas turbine blades. The requirement of the blade cooling to increase the thermal efficiency, one of the most effective way to increase the turbine inlet temperature TIT. So therefore the modern gas turbines vanes have the temperature of around 16 to 1700 degrees Celsius. So in order to have a continuous operation without premature failure, the vane has to be cooled at around 1100 degrees Celsius, which is a material permissible limit. This is the temperature distribution across a blade. This is the leading edge, this is the trailing edge, showing the temperature at different sections. Gas turbine blades, typical actual view of the gas turbine blade, and this is the failed turbine vanes and blades. If the proper cooling system is not designed. And here the figure shows the internal view of the turbine blades. The figure shows here, you can see that these are the internal serpentine passages having the ribbed turbulators for breaking the thermal boundary layer. And here the channels of various aspect ratios from leading to the trailing edge can be seen. These are the cooling techniques we generally use for the cooling of the gas turbines. For mid-core region, the serpentine passages have the ribbed turbulators, which have the U-turn fluid generally experienced at the exit of these serpentine passages, the sharp U-bend. And the trailing edge have the pin fins, and the leading edge have generally the impeachment cooling. So to have the complete information of the heat transfer at these U-turn, in order to prevent the local hotspots, we require the investigation of the fluid flow in these sharp U-bend turns. Now matrix or lattice work cooling, having the high heat transfer and provide a structural rigidity to the blade, so can be substitute in the trailing edge also. These are the various parameters, and here we also can see that the fluid also experience a U-turn in the matrix structure also. So in this study, in this work, we have studied the flow physics at U-turn with and without matrix at a Reynolds number of 6200 based on the mean center line velocity and the hydraulic diameter of the duct, which is equal to 70 mm. The aspect ratio of the two-pass duct is 3.26. So therefore, for a better design of the U-turn, it is necessary to have a complete information and the heat transfer and flow behavior. Now we will move toward the experimental. This is the literature review. The researcher studied the U-turn by different position, different mechanism for the different shapes. This is the experimental setup. This is the experimental setup having the two-pass duct made of the plexiglass for the optical accessibility. This is the first pass and this is the second pass of the duct. This is the U-turn, and we have studied the flow physics by a stereo PIV. The cameras are being mounted on the rear side of the duct. This is the plane we have studied, plane number 2, which can also be seen here. The whole of the study is taken at two different locations, location 1 from here to here and location 2 with 10% area overlap, so that no area remain untracked. The cameras are installed here. This is camera 1, this is camera 2 at angle of 30 degree. The sampler configuration is used for focusing the inclined plane. These are the various dimensions of the U duct. This is the actual view, actual photograph. This is the U duct having the LCT also for heat transfer study. These are the cameras, 2D traverse, and the laser is mounted for having the optical sheet of approximately 1 mm thickness from the top side. Here we can see the matrix parameter. Table shows the stereo PIV parameters. What is the region of interest, the image size, calibration factor, frame rate. These are the result and discussion. The results are shown in terms of the mean velocities and the time average streamlines in order to have a flow topology. These are the X, Y, and Z directions. X, Y, and Z direction without matrix in first pass. These are the X, Y, Z normalized velocities with matrix in the first pass. Here we can see that the streamlines are straight without matrix in the first pass, and the U direction velocity increases from here to here in negative U direction because the flow is guided by the U-turn. Initially flow is coming in the plane means Z direction, and the flow is guided in this direction means U direction by the U-turn. Here with matrix we can see that normalized X direction velocity have lower values initially and then increases, and a waviness means the randomness in the streamlines can be seen by placing the matrix in the first pass. The y direction velocity is almost constant without matrix, but by placing the matrix, the normalized y direction velocity is initially higher positive, means the flow is going upward, and where the flow takes the turn means at x equal to 100 mm, the y direction velocity is reduced to a minimum value as the flow again comes in downward direction. This spot, blue spot, can be seen when the flow takes the first run, and this red spot means higher positive value in the y direction velocity when the flow takes second run to enter into the second pass of the duct. And we can see that as the flow is coming from the Z direction, here the normalized Z velocity is high initially in the near the first pass, and when the flow takes the turn, it reduces and becomes almost zero up to the end of the duct. But by placing the matrix in the first pass, we can see that this higher value of the Z direction velocities area reduces because the flow is retarded by the matrix in the z directions because of the friction penalty offered by the matrix structure. In order to understand the turbulent mixing momentum transfer, contours of the normalized Reynolds shear stress with and without matrix is shown in the figure left and right. This turbulent mixing generates due to the presence of the spatial gradients in the time average velocity. Reynolds shear stress in xy direction shows that at the end of the value of shear stress in xy direction for both of the cases is higher positive, shows the higher momentum transfer here and here, shows the higher momentum transfer at the exit of the U-turn, means the better mixing and hence the high heat transfer, which is also noted down by the other researcher. The zone of the high negative Reynolds stresses can be related to the flow directed upwards as indicated by the normalized average velocity components. This can be shown. Furthermore, the contours of the Reynolds shear stress in YZ direction show that at the entry without matrix there is high momentum at here. There is high momentum in this direction because the flow is coming from z direction with high momentum of the particles. After placing the matrix, the flow is retarded. Here we can see that the flow is retarded and having a low Reynolds stress at this location by placing the matrix. As the flow advances, mixing in y direction increases. So the value of contours start increasing up to the U-turn. Here we can see. Also, the contours of the Reynolds stress in xz direction without matrix decreases from start to end. Here we can see that it decreases from start to end. In z direction and with matrix and increment at most of the location with a random behavior, increment can be seen. Conclusions: placing the matrix in the first pass before the entry at U-turn, the flow pattern at U-turn has been changed. The time average streamline, velocity contours with the streamline show disturbances. Waviness in the streamlines can be seen. Reynolds stress shows that at exit of the U-turn, the shear stress in xy direction for both of the cases with matrix and without matrix are higher positives, so a higher momentum exchange and hence the high heat transfer, which is also found out by other researchers. It can be concluded that the matrix in the first pass duct completely change the flow behavior at the U-turn. Future scope of the work: to investigate the flow pattern around the U-turn completely, various other parameters such as vortices, normal stresses and turbulent kinetic energy budgets at different numbers and position need to be investigated. SPIV measurement of U-turn in horizontal plane need to. These are the reference questions and answers.
All right, thank you very much, Nishab. So the session is open for questions. If there are questions from the audience, please go ahead.
I have a quick question. Did you observe any contra-rotating vortex kind of structure around the band?
Yes, very good question, Goswami sir. Actually, we have this type of the structure, counter-rotating structure, but that is in the horizontal plane. We have tracked the U-turn also from the means when the camera is at the upside. And the laser from the laser have the horizontal plane and the camera is on the upper side. So we have that structure also, but we have not shown that in the paper because the paper size is limited and we want to show this in the journal.
Yeah, understood. Paper size is too much restricted here. Thank you.
Okay, so if there are no further questions, let's thank Nishab, and Nishab, wish you all the best for your future work as well. Thank you. Moving on, the next paper is by Sandeep Kumar and co-authors, and he's going to be talking about shear layer and vortex identification of rotating vortex rope structure obtained via POD. So let's start with Sandeep's presentation.
Hello, greeting to all. My name is Sandeep Kumar and I am going to present my presentation on shear layer and vortex identification of RVR structures via POD in Francis turbine. As we know, hydropower is flexible and most reliable source because it is very flexible because of change in demand of the electricity. So mostly in hydropower, 65% of hydro turbines are Francis turbines, and these turbines are designed for one single point that is called design point. It is also called the BP condition of the turbine. But due to change in the demand of electricity, the turbine is always run away from the BEP point. So due to this, the Francis turbines faces very we can say problems in that. So it has increase in fatigue load cycle of hydro turbines, it reduction in the life of runner, vibration and pressure pulsations are generated in the draft tube, and RVR is formed. RVR is basically rotating vortex rope, which is formed in the draft tube. All these are flow instabilities generated in the turbine because of this operational. So in hydropower, this is the design point condition. The flow is very smooth and streamlined, as we can see, and it is the part load condition when turbine run away from BP point lower than 100% load. As we can see, there is a vortex rope formed in the draft tube, and this is the high load condition in which turbine is run beyond the 100%. It is 110 to 120% load, and we can see a torch-like vortex rope is formed. These flow instabilities produce many secondary flow phenomena. So this is the measurement plane. We are taking three planes. One is the middle plane, one is the top plane, and one is the bottom plane. Middle plane, the top plane is 50 mm above, and bottom plane is 50 mm down the middle plane. So measurements are done in these planes. These PIV is sorted, and we have done some mathematical and statistical analysis on that velocity data and obtain the different energy modes of the flow field. So this can be done with proper orthogonal decomposition. The proper orthogonal decomposition is basically a phenomena in which we can describe the different energies of the flow field at different time steps. So here this is a matrix H in which velocity of a plane is aligned in a single column, and different column of this H matrix represent single snapshot. After that, we have this autocovariance matrix. In this autocovariance matrix, we can convert this autocovariance matrix in eigenvalue problem, simple eigenvalue problem, and we can find the energetic modes of the flow field. So the vortex identification algorithm is coupled with POD to identify the shear layer, identify the pure rotational zone, and identify the convective velocity zone in the flow field. So gamma 1 here represent is a function, dimensionless function, which is basically simply a normalized angular momentum, depends on the uh, angular momentum of the flow field. And this function basically gamma 1 identify the vortex center in the draft tube of a Francis turbine. So it provides the streamlined topology of the flow in the vicinity of a point P, and rotation sign. It also tells about the rotation sign of the vortex. The value of this vortex center uh, lies between 0 to 1, and the center of the vortex is lie between 0.9 to 1. The maximum value is the center of this vortex center. And gamma 2 basically is function. uh, Gamma 2 is basically a function is used to identify the vortex core. It is identify the boundary of the vortex which contains the rotation, which contains shear layer, and it contains some local dominated strain. So this algorithm is coupled with POD, and we can identify the various modes. As we see, the mode 1, which is obtained through POD. When we couple these two algorithm on POD, we can clearly see that on the right side that the flow field has some vertical structures present. It is the pure rotational case is represented by this circular mark, and the asterisk marks represent the pure shear layer, and the cross circle, which is at the left hand side of the photograph, it shows the maximum shear point, in which represents the vortex center. So in the left side, we can see the flow field, normal flow field, and when we apply this, we can identify the zones where we can identify the different kinds of phenomena generated in the trough. So this is the mode 3 and mode 4 of the flow field, and mode 3 represents some two vertical structures. As we can see, the streamline structure is there, which it only gives about the idea that only the two vertical structures are present in the flow field. But when we applied this algorithm on this flow field, we can see that in these vertical structure there is two type of things are happening here. One is the pure rotation, which is represented by this circular region, and one is the pure shear layer, which is surrounded by this centrical circle, the asterisk marks. As we can see, the boundary of the these vertical structure is, we have some shear layer formed in that region, and the maximum value of this the vortex center is represented by this cross mark, as we can see at the right hand side. Similarly, in mode 4, we can see that these modes have also some vertical structure, and it can also identify that the center of this vertical structure has some pure rotational case, and the boundary of this vertical structure has some shear layer form. Similar with mode 5 and mode 6, and we can see similar things. We can apply that vertical structure have been having pure rotation, and we can see the shear layer forms around by these vertical structures, and the maximum point of this pure rotation, the center of the rotation, is represented by the cross mark. So in this, so we can conclude that the snapshot of the POD has been employed to analyze, and we can find the shear layer formation along with large and small vertical structures. These vertical structures implant and show the shear layer formation and rotation of the vertical structures in the flow. So thank you, all of you, and
thank you, Sandeep, for this nice presentation. The paper is now open for any questions from the audience.
Hi, I have a question. When you are writing out that matrix of H, which you are then using to get the vertical structures later. So in that you have mentioned U to UN. So are you going to consider the whole domain, all the U values across the domain, or?
Yes, the data is logged at the frequency of 40 Hz, and we are taking here 250 snapshots there. So we arrange all 250 snapshot in a column matrix. So one column of the covariance matrix is a single snapshot, in which U and V both data is taken.
So if suppose I want to use your method in a commercial software, right? I can plug in my UDF, right? So to do that, and it is suppose it's a like just a because any snapshot of transient is also kind of a pseudo steady, right? So if I have a pseudo steady solution, I want to import like use your distinct method. So do I
Yes.
need to?
Yes, you can do it. The data here which is shown here is also turbulent steady, and we can also apply this method to transient simulations, transient PIV measurements also. So we also identify the formation of vortex roof in the elapse of different time.
Okay, thanks. Yeah, I like that vortex center identification part. That's very nice. Actually. Thank you.
Thank you.
All right. Thank you very much, Sandeep, for this wonderful work, and please keep up all the good work that you're doing. Thank you.
Thank you.
Okay, so moving on to the last paper of this session. It's to be presented by Shyam Shukla and co-authors. Shyam is going to talk about transient behavior of a pump intake and its impact on pump life. So let's start with Shyam's presentation.
Respected dignitaries and audience present here in this virtual presentation of FMFP 2020 conference, a very good morning to all of you. I am Rajvamsi Gangipamula, currently working with R&D Department of Kirloskar Brothers Limited, Pune. It is my pleasure to present my work on pump intakes to all of you. The topic of my presentation is transient behavior of a pump intake and its impact on pump life. Dr. Shyam Shukla sir and Ravindra Biraza sir are the authors of the work along with me. We are presenting a case study wherein we have resolved a critical site issue of vibration of pumps by CFD analysis of the sump. The uniqueness of this analysis is that we have resolved the site issue using pump flow study, checked the transient behavior of the flowing water and its possible impact on the pump that could lead to pump's vibrations. The present slide shows the contents of the presentation. It starts with introduction of the subject matter that covers the design objectives of a pump intake and transient nature of the flow. Next is objective of the present study, which drove for the numerical simulation approach. Then we will elaborate our research methodology aligning with the objective. Afterwards, we would describe the site issue. Finally, a discussion on CFD study and problem evaluation method following with major conclusions of the study. A pump performance and its operating life not only depends on its design, but also on the pump intake design. A poor intake condition adversely affects the pump performance. Moreover, it reduces the operational life of a pump. Hence, a pump intake should be designed properly and should be free from following adverse hydraulic phenomena. These are excessive pre-swell flow, which is due to high velocities or non-uniform flow of the approach flow. Second one, air entrainment or free surface vortices. It occurs when air enters from the free surface of the sump. It generally occurs due to the unavailability of sufficient water levels at sites. Third one, submerged vortices. Unlike free surface vortices, these arises from the pump intake floor and walls. Fourth one, non-uniform velocity near impeller eye location. And finally, transient behavior of velocity and swirl at impeller eye location. These are the major points which can adversely affect the pump intake design. The transient nature and its impact are explained in a point wise. The causes of a transient nature of a pump intake are high velocities, improper intake geometry, insufficient water levels at site, and the quality of the pumping water, and finally improper suction piping at site. After noting the causes of the transient nature of a pump intake, next comes the how to identify the transient nature of a pump intake. This can be done by the following ways, which is measurements at site, model tests of a pump intake, and the final and which is very commonly using nowadays is numerical simulations using CFD. Previous slide showed the causes and identification methods of transient nature of a pump intake. And the present slide shows the impact and remedies of transient nature of a pump intake. What are the impact of transient nature of a pump intake? It causes adverse impact on pump performance. It may reduce the pump performance in most of the cases. It induces lateral vibrations on pumps and also heavy noise. Then what are the remedies? It starts with design modification of pump intake using either model study or using numerical simulations method. Before coming to the main objective of the present study, I would like to give you a brief background of the site issue. In one of the sites, we have supplied 3 number of pumps. There was issue of high vibration in some of the pumps that we were not knowing in the beginning. The client asked us to find the root cause of the problem if possible. They have shared the details of the sump and we have taken up the project with the aim to address the site issue of pump vibrations. Objective of the present study is to predict the transient behavior of a pump intake in terms of vorticity and velocity measurements near impeller eye location of a vertical turbine pump, and also to evaluate the impact of type of pump suction on pump intake quality. The research methodology is divided into 3 parts. It starts with the description of site problem. Start point to address the issue was to study the data provided by the client and check the adequacy of the data. If data is adequate, then use the information to identify the possible causes of vibrations. After that, we use the data and formulated the strategy of CFD analysis in line with the site conditions and make focused attempt to find the root cause of vibrations if possible. And finally, problem evaluation method. A detailed post-processing of the CFD results to find the cause of vibrations in terms of flow parameters. It gives a clear picture of the problem and confirms the site problem with high vibrations of pumps. The pump intake at site consists of 5 pump chambers with 2 different types of pumps. Pumps P1 and P2 are double suction vertical turbine type of other manufacturer. Pumps P3, P4 and P5 are single suction VT type of Kirloskars. The geometries are also shown here for reference. Flow enters from a connected pipe into each individual pump chamber after passing through the screens and sluice gates. The present slide shows the details of 2 types of pumps installed side by side in the same sump. These are double suction entry pump and single suction entry pumps. As explained in the previous slide, double suction entry pumps are P1 and P2 and P3, P4 and P5 are single suction entry pumps. The problem at site is heavy vibrations are found in pump 1, which is of double suction type. Pump 2 is also found to be with vibrations more than the limit in specific combinations. The vibration spectrum was studied and it clearly indicated that 1x peak was found. This can be attributed to the mechanical unbalance and hydraulic unbalance. The mechanical unbalance was checked and found well within limit. Hence, hydraulic unbalance was suspected for the present problem. A numerical simulation planned for specific combinations which is more prone to vibrations in a double suction VT pump, which are P1 and P2. ANSYS ICM CFD has been used for meshing. The generated grid was a tetra grid with fine meshing near the walls and other important areas. Initially, grid independent study was carried out with swirl angle as the output variable and finalized the optimum grid. To align with the predictions at site, the 3D modeling was done with the actual measured site dimensions of the sump. The screens are also modeled with required porosity as per the test data. User surfaces are created at each suction location to monitor the mass flow rate and vorticity in axial direction. The graph also shows the optimized grid independence study plot. The slides hereafter will show the results and we will be discussing them one by one. The present slide shows the streamlines plotted in overall sump geometry for a specific combination under study. As already described about the sump, water enters from the individual pipe into common chamber and then into the respective pump chamber after passing through the sluice gates. In order to find the deviation of flow in its path from inlet to pump outlet, initially the normal velocity contours are plotted near sluice gate location. This is because of the reason that sluice gate locations can be the first element that can disturb the flow quality. The contours are found to be almost similar with the core region in the center. It is also expected from the results because the flow from each individual pipe is entering through the sluice gate. Hence, it can be established that sluice gate location is not any cause of the problem. Next, a normal velocity contour is plotted near the pump chamber entry location. Plan view shows the location of the plane. From the contour, it is clear that the fluid zone near the pump 1 is found with wall attached flows. Highlighted circle shows the same. Also, the wall attached flow impacting the core flow velocity traveling towards the pump suction of pump 1. Hence, the wall attached flow is found to be the part of the problem which is causing flow non-uniformity near pump 1 suction. Axial components of vorticities are plotted near impeller eye location of the both types of pumps and found that the pump 1, which is double suction type, is found to be with relatively higher magnitudes. In the single suction pumps, the vorticity magnitudes are comparatively very less. The high vorticity magnitude in double suction pumps, which are P1 and P2, are confirming the hydraulic unbalance near the suction, deteriorating the pump operational life by causing lateral vibrations over a period of time. These contour plots confirm that there is a hydraulic unbalance in double suction pumps P1 and P2. As shown in previous slide and this slide, it is partly due to approach flow conditions and partly due to double suction type of pump. These are the two primary reasons which are causing heavy vibrations in the double suction pumps. To find the exact factor of the hydraulic unbalance, the mass flow rate and vorticities at a suitable location in inlet was monitored in the solver, and fluctuations were captured. The same normalized plots are shown in this slide. The plots clearly shows that the pump 1 is found with maximum fluctuations of mass flow rate following with pump 2. In pump 3 and pump 4, there is no deviation at all. This clearly indicates the inherent transient nature of flow in double suction pumps compared to single suction pumps in this particular application. The magnitudes are also high in pump 1 due to its close vicinity to wall attached flow. The flow parameters which can be related to the vibrations is the vorticity magnitude. More the vorticity magnitude, more amount of lateral forces are induced in pump. The monitors clearly shows the high amplitudes in double suction pump, mainly in pump 1, which is aligning with the site observations of high vibrations with 1x frequency peak. The swirl angles calculated for pump 1 shows 20 degrees value, which is quite higher than 5 degrees as per HIS standards. Coming to the conclusions, this study gave a novel way to use CFD analysis for addressing site vibration issue. In this study, monitoring the flow parameters like vorticity and mass flow rate near pump impeller suction location are used as a method to find the inherent transient nature of a pump intake. The wall attached flow found near pump 1 location is causing the pulsating nature of flow and also triggering the imbalances of mass flow through each pump suction. The observed flow parameters variation in double suction pumps confirms the transient nature in this particular geometry for this particular combination. Also, the wall attached flow near double suction pump enhances the adverse flow conditions near pump suction and further causes vibrations. For single suction pumps, the observed fluctuations are very less and hence the vibrations are also very less. A numerical simulation approach with steady state simulation has been adopted in this study to find the root cause of the vibration problem at the site. We would like to thank the management of Kirloskar Brothers Limited and Research Engineering Development Team for their cooperation during this work. Thank you.
Okay, so let's thank the speaker, and I think we have Dr. Shukla in the audience to answer any questions. So if there are any questions, please do go ahead, and Dr. Shukla, I think, will be happy to answer them.
Sure.
So, Dr. Shukla, are these simulations unsteady or these were time averaged simulations that you did? I presume they were unsteady.
Yeah, this is what is the steady state simulation.
Okay.
And a kind of pseudo transient simulation we have done.
I see. Okay.
The interesting part of this simulation, since no question is there, I would like to add, which is not the part of the paper. But generally what happens at the minimum water level, we see the problem of vibration in vertical turbine pump. This was a peculiar case wherein we got the vibration problem at higher water level. And that is what was the interesting part of this. And the study was something which is generally not done in any sum flow studies or CFD analysis of any pump intakes. Thank you.
Yeah. So if there are no further questions, let's firstly thank Dr. Shukla and his team for the last paper. I would also like to thank all the authors. There were 8 interesting papers in this session, and all of them did a wonderful job. And that brings us to the end of this session. And thank you all for joining us in this session. And I think the next session is also on turbo machines. So those who are interested in turbo machines, please do rejoin in a few minutes from now. So the next session probably begins at 4:15. Thank you all, and take care. Thank you.
Thank you very much.
We thank you, Professor A.M. Pradeep, for sessioning this. Okay.
Thank you very much.
So the next session will start from 4:15.
Vous allez écouter à l'instant. qui hوں.
Hello. Hello.
Tu es trop grand pour comprendre des choses aussi petites.
Hello. Is there any organizer?
Thank you.
Tu es trop grand pour comprendre des choses aussi petites.
Good evening, everyone. This session will be chaired by Professor Abdus Samad from IIT Madras. Thank you.
Yeah, good afternoon, everybody. We have 4:15. We have to start, and this session will go up to 6 p.m. I am Professor Abdul Samad from IIT Madras. I'm working in the Department of Ocean Engineering, Fluid Machinery, Turbo Machinery area. Okay, so our first presentation will start from just please wait. I will find the name. Presentation title is Comparison of Turbulence Models for Predicting the Flow Field in the Draft Tube of a high head Francis turbine at part load operations. So can you share your screen and start presenting? Who is presenting today? Who is presenting? Subodh?
Yes, sir.
Hello?
Yes, hello.
Yeah, who is presenting? Subodh Kullar.
Yes, sir, I will be presenting. The video has been already submitted. Yes.
Yeah, so I think 15 minutes total time is given. So you try to finish in 12 minutes. Okay. And you introduce yourself first, then you start. Okay.
Okay, so myself Subodh Kullar, I am a research scholar at IIT Roorkee, and this is my work on. Actually, I'm working on the flow instabilities at the part load operation of a Francis turbine. So this work is regarding how we can minimize the computational efforts while getting the accurate details of the rotating vortex soap that is formed at part load operation. So you may please, the organizers, they may start the presentation. Yes.
Thank you, everyone. My name is Subodh Kullar, and the topic for my presentation is comparison of turbulence models for predicting the flow field in the draft tube of a high head Francis turbine at part load operation. So coming to the outline, the presentation will start with some background of the work, and it will be followed by limitations of the current numerical approaches and objectives of the present work. Then we will discuss the numerical modeling and results, and after that, lastly, the conclusions will be presented. Hydropower, as we know, is a renewable and clean source of energy. It's highly reliable and efficient and has a longer span of life. It contributes towards approximately around 1/6 of energy generation worldwide. Well, another important feature of hydropower is its wide operating range, which provides stability to the power grid. Energy generation from intermittent sources such as solar, wind, leads to grid instability issues, which can be easily handled by weighing the output of hydro turbines. Thus, the modern hydro turbines are increasingly subjected to off-design operating conditions. However, these operating conditions are a necessary evil. Operation means when the flow is different from the design discharge. If it is less, it's called a part load operation, and if the discharge is more, it is called a high load operation. For single regulated turbines, such as the Francis turbines, such off-design operation they result in less efficient operation, more fatigue loading of the turbine components, which results in a reduction in runner and blade life, and there are also some instabilities in the flow field, such as the vortex breakdown and other such flow instability. Now, vortex breakdown, it occurs because of the residual swirl present at the part load operation. And this residual swirl is due to the misalignment of guide vanes and the runner blades. As the swirl increases beyond a particular value, it results in vortex breakdown, and a spiral rotating vortex rope-like structure forms, which is in short form we call it as RVR. So this RVR rotates in the direction of runner rotation at part load, and its frequency is around 0.2 to 0.4 times the runner frequency. It leads to severe pressure pulsations and vibrations, and results in more hydraulic losses, which causes again reduction in efficiency. And there is also a variation in power output of the turbine, which we call as power swings. Now, because of all these problems, efforts have been made to study the formation and subsequent mitigation of the RBR. Both experimental as well as numerical simulations have been carried out for in-depth analysis of the flow field. However, the simulation of a complete turbine unit is complex and requires very high computational resources. It is because the numerical model, it consists of stationary as well as rotating components, and the geometries of these components are very complex. So, which also adds to the high demand of computational resources. Moreover, the flow field is also highly turbulent. So, there is a need to develop solution strategies that require less computational power without compromising with the accuracy of the solution. Now, this leads us to our present work, in which the numerical simulation of the draft tube, only the draft tube have been performed after decoupling it from the complete turbine flow field. To achieve this, at first, the transient simulation of the complete Francis turbine at part load operation was conducted using the Cape Silent turbulence model. After that, the velocity data near the inlet of the draft tube was exported at each time step and was used as inlet boundary condition for the decoupled cases. Thus, we need to solve only for the draft tube flow field using this method. Further, the performance of 3 turbulence models has been compared in predicting the swirling flow inside the draft tube for these decoupled cases. After that, the results have been compared with the results of the complete numerical simulation as well as the experimental results for the validation purposes. Okay, in this figure, it shows the complete numerical model from spiral inlet to draft tube outlet. The boundary conditions for the complete model simulations are also presented in the table. At the inlet, mass flow rate was specified, and while an opening type boundary condition was specified at the outlet. The turbulence model was chosen to be Cape Silent based on the literature that is present on this particular model. So, and the second figure, it shows the PIV measurement lines and the measurement plane at which experimental data is available for the validation purposes. Now, the results of the complete model simulations were validated with the experimental data and are presented in this table. The percentage error in the determination of these global quantities is in acceptable limits. The highest percentage error among these is in torque, which is around 12%. This also leads to higher prediction in the efficiency of the turbine as well. However, the numerical results are in good agreement with those already reported in the literature for this particular case. So, as mentioned previously, data which includes velocity components and turbulence quantities at a plane in the draft tube was exported for decoupled draft tube simulations. The plane that is shown here in the figure was chosen to be 15 mm below the draft tube inlet to avoid the influence of runner draft tube interfaces. A sample velocity profile is also shown in the figure. The 3 turbulence model available in NCCFX were chosen for comparison of the decoupled cases, and these models are Cape Silent, SST K Omega, and SST SAS. The first two are popular lens models. For the SST-SAS model, the mesh of the draft tube was further refined to fulfill the requirements of greater resolution and the current number. The current number, the CFL number, it was kept around 0.67, and the literature suggested to be below 0.9, so it was acceptable. This model, it is a combination of RANS and LES methods. It's a hybrid model, and it shows LES-like behavior in unsteady regions of the flow field, while standard RANS capabilities are provided in the stable flow regions. So the accuracy of the decoupled cases was then evaluated at the two PIV lines by comparing the mean horizontal and axial velocity obtained from the experimental as well as computed numerical model. As we can see from the graphs, the predicted axial velocities using all the turbulence models show good agreement with the experimental values at all points except in the central region of the draft tube, which contains the core of the vortex rope. However, the numerical results of the flow field in the draft tube with RANS model agree well with the simulation of the complete model. However, the SST-SAS model underpredicts the velocities in the central core. For the horizontal velocities, the results obtained from the UN simulations are again in good agreement with the reference values. However, there is a large variation in the velocity profile predicted by SST-SAS model as shown in the figure. This may be due to the lack of proper boundary conditions for this model. Thus, the results from UN's simulation suggest that the draft tube can be decoupled from the whole flow field, at least for these turbulence models, and can be investigated independently. The simulation time here was reduced significantly. RANS simulation took 62% lesser time, while SST-SAS model, it took around 47% lesser time. The main time it was consumed in loading and unloading of the boundary data using the photon subroutine. Now, in this figure, we present the results with the different turbulence models. At first, the pressure contours at the midplane of the draft tube are shown in the figure. The results for the UNs are consistent for both complete numerical as well as decoupled draft tube cases. The contours for the decoupled cases shows that the attachment of the core region with the wall, whereas the core remains more so centralized for the complete numerical case. The axial velocity contours at the midplane, the center stagnant region, which marks the presence of vortex rope, can be seen in the results. The velocity contours for SASST case shows stagnant region near the draft tube bend only. In the central flow region, the SST-SAS results, they deviate from the expected. Since the flow field is predicted on the basis of inlet turbulence quantities, the results show that they have a high influence on the flow field prediction. Now, in this figure, the pressure isosurfaces are plotted at a constant pressure of 112.5 kilopascal. And these structures, these isosurfaces, they give a visual representation of the RVR. Though the structure complexity of the vortex rope predicted by SST-SAS model is more, and it is how usually a vortex rope appears in the draft tube, but the quantitative results suggest otherwise. However, the vorticity signs along the Z direction for all the cases suggest that the vortex rope to be rotating in the same direction as that of the runner, which is again consistent with the experimental observations. Actually, we had also placed 4 monitor points at the draft tube wall to measure pressure amplitudes to perform the spectral analysis. But due to the dominant effects of stochastic fluctuations, frequency pertaining to vortex rope was not. These fluctuations may be due to the fact that the UDF input at the inlet acts as a step input, and thus the boundary conditions are changing at each time step. This may induce some sort of noise in the pressure data being recorded at the monitor points. Though the average pressure was same at the monitor points for all cases, spectral analysis in this case was not possible due to the noise. Now, finally coming to the conclusions, the study suggests that the flow prediction for the decoupled draft tube cases are consistent with those obtained from complete numerical simulations for UN's models only. For the hybrid models, the deviation in the flow field calculations may be due to incomplete information regarding the turbulence quantities. The reduction in simulation time and effort was the major positive outcome from this study. Similar to such methods can be developed to expedite the design process of the draft tube by accommodating the changes in the design more quickly and easily. So thank you for your time, and this is all I have.
Okay, thank you, Subodh. Yeah, so we don't have much time. So one quick question can we get from any audience? Abhishek, are you asking, or anyone? Is there anyone from audience asking any question or any clarity required? Okay, so if audience is not asking, I'll ask question. Okay, Subodh,
Sure.
are you there? Yeah, so
Yes.
meshing, like when you test with different turbulence model, meshing is most important. So how do you
Yes.
ensure that meshing was done properly?
So actually, we have monitored some mesh characteristics like the orthogonality angle and the aspect ratio, and they were maintained as per the required by the standards, and that were mentioned in the software manuals also. So based on that, the orthogonal quality it was kept. Although the minimum required is 0.2, but we have kept in case of decoupled draft cube cases, it was more than 0.85. So the mesh orthogonality quality it was monitored as well as the aspect ratio and other such mesh characteristics were monitored.
Okay, okay, okay. And what about convergence criteria?
The convergence criteria it was kept to be 10 is for -6 for the momentum as well as the continuity equation, and which was quite confidently met during the simulations.
Okay, so I think 15 minutes time allotted, and thank you so much.
Okay.
Okay.
Hello.
So yeah. So next presenter, can you upload your file or you can share your file? Next presentation is on hydraulic noise reduction in a volute pump using source modification, at-least data correlation, and numerical simulation approach. Here, the presenter is Rajavamshi.
Yes, sir.
Yeah, Rajavamshi.
Yes, sir.
Rajavamshi Gangpamula. Right?
Gangi
Am I
Pamula.
right?
Yes.
Yeah.
Yes, sir.
Yeah. So can you start, please? So
Yes, sir.
15 minutes maximum. So you have to
Respected
finish it.
dignitaries and audience present here in this virtual presentation of FMFP conference, a very good morning. My name is Rajavamsi Gangipamula. I am currently working with R&D department of Kirloskar Brothers Limited, Pune. To propel the research work, I am also doing the part-time PhD from BITS Pilani KK Birla Goa campus. Title of my technical paper is Hydraulic Noise Reduction in a Volute Pump Using Source Modification, a Test Data Correlation and Numerical Simulation Approach. Following are the contents of the presentation to be covered during my next 10 to 11 minutes of the presentation. It starts with the introduction part about the pumps and possible problems occurs at site, objective of the study, methodology followed in the present research, along with the study of test data and numerical simulations using CFD. Finally, a discussion on CFD results following with conclusion points are presented. Present slide is a small introduction to variety of pumps available and manufactured by Kirloskar Brothers Limited. The products mostly cover pumps, hydraulic turbines and valves. In pumps, the overall specific speed range is covered starting from radial to axial pumps. The major and common problems which occurs at site during pump operation are listed here. First one is performance achievement. The testing of pump in the test lab happens at conditions ignoring the approach flow conditions and system resistance. Though the pump is designed for a specific system resistance, in few sites it may vary due to approach flow conditions. This may lead to loss of performance. The provided curves shows the impact of system resistance and pump performance. Second one, cavitation. It is related to available net positive suction head, shortly known as NPSH. If the NPSH available at site is less than the required, the possibility of cavitation occurs. The figure shows the vane erosion due to cavitation. The third and most important problem which occurs at site is heavy vibration magnitudes. Image shows the pressure pulsations measured in the discharge piping which is related to flow-induced vibrations. Fourth one and the present research topic, noise. Generally, vibrations or noise are interrelated. The image shows the SPL versus frequency plot with vane pass frequencies. The present work focuses on noise generated by a pump due to a source and its attenuation methods. Noise generation mechanism broadly divided into three categories. First one is fluid-borne noise, second solid-borne noise, and final one airborne noise. The available literature, textbooks and industrial norms also specifies that the fluid-borne noise contributes more to the total noise generated by a pump. In fluid-borne noise, the vane passing frequency components contributes more to the noise generation. The measurement is done in terms of decibels with a weighing. The limit in most of the cases is 85 dBA. This in terms of the equivalent noise level generated by a pump. But again, the end user can ask for lower limits than this. Why noise measurement is important for pumps? This is basically due to two reasons. First one is environmental criteria. Industrial centrifugal pumps are subjected to specific norms and standards under which the noise to be limited below the specified value. The second one is pump diagnosis. Noise signatures of a pump can be used to diagnose the faulty pump operation or incipient failure. This is generally used to troubleshoot a problem at site to find the problem in pump operation. Hence, the noise prediction is very important in pumps. What is its impact? In the present digital world, numerical simulations have become very important tool to produce new designs and also to improve the existing designs. Hence, numerical simulations along with the test data correlation can be used to improve the pump design in terms of noise generated by a pump. Research methodology. After a detailed literature review on hydroacoustics of centrifugal pumps, a research methodology is planned to achieve the required objective. It starts with study of existing test data with noise measurements. We have selected a series of pumps for this purpose. This series indicates design of pumps for a constant specific speed. From a series development data, a pump is selected with the test data. This is to select a specific pump for numerical simulations. A steady state and unsteady state simulations are planned in this process. The present work is limited to steady state results only. The test data shows the geometrical and flow parameters of a pump designed for a specific speed. In this data, the noise levels are equivalent noise levels measurements available for each pump. From the literature, we used an empirical relation on power group, which is function of flow and design parameters. The relatively high values of power group are found in two pumps, aligning with high noise levels data from test. The drawback of this equation is it ignores the impeller volute interactions effect. But for a given pump, if we have any limited data, we can also predict the relatively higher noise generated by a pump. Hence, we wanted to select one pump from the existing four pumps which has high amount of noise generation, which is pump 1 in this case. The duty point of the pump is for a flow rate of 285 meter cube per hour, head 53 meter and speed 2900 rpm. Initially, mesh independent study has been conducted with hydraulic efficiency of the pump as a parameter to ensure that the mesh is suitable for the prediction of flow characteristics. The location of the impeller vane is kept near to the volute tongue and same is maintained in all future analysis. This is to avoid any error due to moving reference frame predictions of a steady state. The tetrahedral mesh with prism layer near walls have been used. Considering the transient analysis, the mesh size has been calculated with reference to blade pass frequency and speed of sound in water. K omega SST turbulence model is used in the analysis and ensure that the wall whiplash in the domain is in the range of 1 to 5. IAPW's IF97 model has been used for fluid. This model consists the compressible properties of water. We can also use the incompressible properties of water. But considering the future simulations of noise predictions under cavitation phenomenon, the IAPW's model is selected for this research work. Flow characteristics are plotted for optimized mesh in terms of head coefficient versus flow coefficient. The maximum deviation in numerical predictions compared to test data is found to be less than 3%. The slide also shows the contours of radial velocity and vorticity magnitude at a y-section. The contour clearly shows the negative radial velocity expanded near to the impeller trailing edge. Similarly, the vorticity magnitude is very high near trailing edge. The relative velocity plots were also plotted and observed that the lower velocities near the suction side of trailing edge and higher velocities near pressure side represent in the formation of a jet wake flow phenomenon in this pump. The presence of a jet wake flow and high vorticity peaks near the volute tongue signifies the hydraulic noise generation up to certain amount in this pump. The steady state results from the analysis indicated that the presence of radial velocity extension to impeller vane location and the jet wake flow phenomenon. This again signifies the existence of impeller volute interactions in terms of the flow parameters. It is to be noted that the reduction of the radial velocity extension and vorticity magnitude can lead to the reduction of pump hydraulic noise. Hence, a modification required to serve the purpose. The major design parameters which can impact the impeller volute interactions are 1. vane trailing edge profile. Second one, radial clearance between impeller and tip and volute tongue. Third one is volute tongue radius. We selected volute radius as the design parameter in this study. The volute tongue radius ratio has been changed from 0.093 to 0.135, which is nearly 45% more than the existing. We can also check the impact of other noise sources like impeller vane trailing edge profile also. During preliminary studies, using the steady state simulations, we can verify the impact of any specific noise source on variation of flow parameters at different locations. It is used for further study of transient simulations. Comparison of the contours shows that there is a relative reduction in magnitude of negative radial velocity extension and vorticity magnitude near volute tongue region. This is due to the modification of the noise source, which is the volute tongue radius in this case. To quantify the effect, it is necessary to conduct the transient simulations, but the preliminary steady state results indicated that there is a reduction of hydraulic noise due to source modification. To confirm the observed noise reduction, we used acoustic models which are Curl and Proudman type. These two methods are generally used for aeroacoustic analysis. It is also to be noted that the literature is not extensively available on the uses of these models for pumps. To use the models for pumps, the corresponding properties like speed of sound in water and the far field density are changed. The contours are plotted for curl acoustic power on impeller vanes and Proudman acoustic power at a specific Y section. From the contours, these points are noted. The curl acoustic power variation is relatively very less with the noise source modification. But the Proudman acoustic power is relatively found to be reduced. It indicates the reduction of quotable noise source, which is the broadband nature type. Following are the major conclusions from the present study. In industrial pumps, for safe and effective operation of a pump, it is very important to limit the noise magnitudes below the certain limit. The power group has been used preliminarily to find the pump with the maximum noise source. This can be used when the test data of equivalent sound pressure levels is not available. The high magnitudes of vorticity and extension of radial velocity towards the vane trailing edge signifies the hydraulic noise generation in the present pump. Attenuation of the same leads to noise reduction also. The mesh size to be selected carefully to predict the noise characteristics for a given target mesh frequency. The study also concludes that the steady state simulations proved that the impact of noise source on flow parameters are predicted qualitatively using radial velocity and vorticity profiles. Use of acoustic models like curl acoustic power and Proudman acoustic power also indicated the relative reduction in noise due to modification of volute tongue radius. Finally, preliminary steady state results showed the noise reduction on a relative qualitative data manner. Hence, the quantitative reduction also expected from transient analysis results. We would like to thank the management of Kirloskar Brothers Limited and management of BITS Pilani KK Birla Goa campus and mechanical department of KK Birla Goa campus for their cooperation during the research work. Thank you.
Okay. Thank you. Thank you, Mr. Raja Vamshi. So you are there only, right?
Yes, sir.
Raja?
Yes, sir. Yes,
yeah.
sir.
Yeah. So we have some time to discuss on this paper. Is
Yes,
there
sir.
anyone to ask question or any clarification required from audience? Audience not raising any hand. I think audience is not having any question. Okay, so I have few questions. Like you have your experiment in one slide, you're showing your experiment has wider range, but your CFD only 3 points CFD have done.
Yes, sir.
So why is CFD normally it will be easier? You can take longer operating range or flow range, but you are doing experiment longer and CFD is smaller. I mean, I don't understand that.
No, the CFD actually for hydroacoustic settings, we started with the duty point, which is the best efficiency point here. Once the standard settings and validation is done using the transient simulations, we can do for the other parameters also. I mean, the off design conditions like left side of the flow, duty flow, and right side of the flow. So for flow validation, because we are using star CCM plus tool, so for flow validation, I consider the operating range only, where 60% to 120% of the flow. So if the noise is limited in that range, that is sufficient as a designer. Okay, pump is good in terms of quality. I mean, in terms of noise quality. So that is why I kept for 3 points only.
Here I have a few points actually. Whenever, I have point. So whenever we do CFD simulation, so normally we try to validate for wider range for validation part. But whenever you are analyzing for your specific noise characteristics of flow analysis or efficiency or something, so that time if you are designing only for that BEP or 10% or 20% plus minus BEP, that is okay. But validation must be proper. So meshing also, meshing and validation, this is most basic part.
Yes, sir.
So the CFD, maybe you can take more point and try to check wider range things are working properly.
Yeah, in the present work, actually, I have not added in this paper, but we have done till shut off head also.
Okay. Okay. So yeah, normally in academic research, whenever you are submitting thesis or paper, your committee will be asking why not wider operating range, because CFD just you give run and forget. Right.
Yes, sir.
Experiment.
Yes,
sir. Experiment also easier once you have one basic setup.
Okay.
But CFD validation, like meshing parameter and this comparing with experiment, those parameters you have to check properly.
Yes, sir.
Things looking okay, but still your committee will be asking that one. Okay.
Yeah, sure. I will consider these points for the experiments and numerical simulations also.
Yeah. So
thank you, sir.
I think audience is not having any question. Okay, then Mr. Raja.
Yes, sir.
You can. Yeah, you can close your presentation. We'll move to the next presentation. Thank you very much.
Thank you, sir.
Thank you very much. Okay. So next presentation is on mathematical modeling of fuel transfer pump for combat aircraft fuel system application. And here presenter, I don't know who is the presenter, Anant, right?
Yeah, I'm presenting, Anant, yes.
Anant, okay, Anant, please, again it will be recorded video, right?
Yes.
Yeah, okay. So please introduce yourself and.
Okay. Hi, I'm Anant Pai. I'm a JRF at VIT Vellore. The paper that we going to present today is a mathematical modeling of fuel transfer pump for combat aircraft fuel system applications. So basically what we have used is a one-dimensional theoretical approach to predict the pump heads for a centrifugal pump. And then we validated the results with the results we got from the experimental test center.
Oh.
Hello everybody, my name is Manglo Anant Pai and it gives me immense pleasure to present my paper titled Mathematical Modeling of Fuel Transfer Pump for Combat Aircraft Fuel System Applications here today at FMFP 2020. And I would like to give you a small short presentation on this today. Model combat aircraft fuel systems are configured with a pump-based transfer system running from the auxiliary tanks to the feeder tanks, and the fuel from the auxiliary tanks is fed to or transferred to the feeder tank with the help of fuel transfer pumps, and the most commonly used fuel transfer pumps or auxiliary fuel pumps are centrifugal pumps. So the main purpose of a centrifugal pump is to transport fluids by raising the specified volume flow to a specified pressure. The centrifugal pump used in this paper is a single stage pump operated at ground level with jet fuel A1 as the working fluid. So there are various methods to predict the pump performance, and in this presentation we'll provide a theoretical procedure to predict the pump head and the flow pattern in the pump. We know that there are various methods like CFD, experimental methods and theoretical methods in the literature which are used to predict the pump performance and the flow pattern. However, the aim of this paper is to predict only the pump head characteristics of the candidate pump using a purely theoretical procedure and compare them with the experimental results. The experimental test rig is a high-speed specific pump, and it uses jet fuel as the working fluid. This is operated for a certain operating range for a set of flow rates, and the pump heads are calculated from this. The theoretical procedure used in this paper employs velocity triangles and several semi-empirical relations to model the flow in the pump. Then we model the various losses in the impeller and the volute, approximate the slip factor, and then finally predict the pump head. These pump heads are then compared with the results from the experimental test rig, and we check the validity of the calculation procedure used and the choice of the equations that are used. So here we have a cross section of the centrifugal pump used. As you can see, we have the impeller, the involute, the housing, and we also have an inducer to minimize the cavitation. Here we have the input parameters, and the operating flow rate is given here. Another approximation we used was the mean thickness of the blades, because the thickness of the blade varies across the length of the blade. We calculated the volute area using the volute width and the base diameter and the volute angle inside the volute, and as you can see, the shaft speed is 12,500 rpm, which is quite high. Now moving on to the velocity triangles in the methodology, as you can see that the velocity triangles at the inlet and the outlet of centrifugal pump have been drawn. So we have V1 and V2 as the absolute velocities, Vm1 and Vm2 as the radial velocities, Vr1 and Vr2 as the relative velocities. We have the inlet and the exit blade angles beta1 and beta2, the inlet and outlet peripheral velocities U1 and U2. We have the tangential components of the absolute velocities Vu1 and Vu2. And then we have the impeller velocities, which we know from literature given in this table over here, and these are the velocities that we'll use for in the future in this method. So the first step is to calculate the theoretical head or the Euler head, which is given by this equation. This for a pump with no losses. Next we calculate the slip factor. Because there are a finite number of plates in the impeller, the friction area in the pump reduces. This causes a pressure loading on the plates and results in a flow pattern on the trailing edge of the plate. We calculate the slip factor using the Stodola approximation to calculate, which is sigma. Next, the constant for phi2 is the ratio of the radial and peripheral velocities at the outlet. Once we calculate sigma, we simply incorporate it into the theoretical head to calculate the head loss due to slip. Once we have the head loss due to slip, we have to model the hydraulic losses in the pump, which are the impeller losses and the volute losses. The impeller losses occur in the impeller due to changes in flow direction, diffusion, and friction. So in this model, we have considered 4 types of impeller losses, which we will discuss in detail in the upcoming slides. So the first loss model is the impeller shock loss. At off-design conditions, the inlet velocity angle of the relative velocity does not match with the impeller inlet angle at the blade leading edge, and this causes a shock. This is modeled using the equation given over here. The constant C SHI is equal to 0.5 as per literature. The impeller friction losses are modeled using a theory of flow through pipes, and this is given by the equation over here. So we're using average values of velocity, hence we have the average relative velocity given here. In the next slide, we'll see how to calculate the constants which are given in this equation. So the impeller diffusion coefficient CDI from the previous equation is calculated using this. Next we have the impeller friction coefficient Fy, which is calculated using the average Reynolds number because you're using average velocities. We also have to calculate important hydraulic diameter because the flow through the impeller is irregular, and hence we have to consider the hydraulic diameter. Also the roughness of the material used in the impeller is cast iron, and we consider surface roughness. Once we calculate all these friction coefficients, we simply incorporate them in the friction loss equation to calculate the impeller friction loss. So next we have the diffusion losses and the I losses. The diffusion losses occur due to flow separation in the impeller. So this is calculated using this equation, and we use the relative velocity of the inlet to model these losses. The impeller I losses are calculated using this equation, and these losses occur in the impeller I. Ci is a constant which is equal to 1 for a single stage pump. We calculate the I velocity using this equation. Thing to note here is epsilon 2, which is the blade thickness coefficient that has a constant available from literature. After the impeller losses, we start modeling the volute losses. The volute losses occur due to changes in cross-sectional area, swirling flow, and friction inside the volute. We know that once the fluid enters the volute to the velocity V3, it can be decomposed into a velocity parallel to the volute and a velocity tangential to the impeller. So through this velocity components, we can define various losses. First is the volute shock loss, which is the difference between the volute inlet velocity and the through flow velocity given by the equation here. The constant CSHV is equal to 0.25, which has been assumed for a particular volute. The velocities in the volute can be defined using the equations given here below. So next we have the volute friction losses. These are calculated similar to the impeller friction losses. The theory of flow through pipes is used to calculate these losses. As you can see, the equation here is used to calculate the volute friction loss. The only difference being that we use volute dimensions and volute velocities to calculate these losses. We have the usual friction coefficient over here, CFV, and FV here. So we have the hydraulic diameter DHV for the volute, and we have the length of the volute, which is again being averaged. In the next slide, we'll see how to calculate these. So now we have the friction coefficient FV, and this is calculated again using the average Reynolds number in the volute. We have the hydraulic diameter of related using the equation over here. So the constant CdV, which is the volute diffusion loss coefficient, is assumed to be 0. Losses inside the volute throat and are calculated using the dimensions from the volute throat. This is calculated using this equation, and we have another coefficient here called the volute throat friction loss coefficient. And then calculate the final pump head and see how the head varies with the flow rate and how the losses also vary. Quite insignificant in this case. Next, in blue, we have the volute losses, and these decrease significantly with the increase in the flow rate. We can observe here that at the lower flow rates, volute causes a significant reduction of head. This is mainly because of the shock and diffusion losses. The swirling flow in the volute results in a kind of circulatory flow at various flow rates, especially when the pump is not operating at the design flow rate. After a certain point, it stabilizes and we can see that the losses decrease. Then finally, we calculate the pump head using the equation given here. So we have subtracted all the losses from the theoretical head, and we have plotted the variation of the pump head with the flow rate. In black, we have the theoretical head, which is the head for a lossless pump. And in red, we have the experimental values, and in cyan, the predicted heads from our theoretical approach. As you can see, there's a large variation between the theoretical head and the present study. This is mainly because of the hydraulic losses. The viscosity of the pump also causes a further drop in the pump head. Now we can see that the difference between the predicted head and the experimental values are not so high, hence it shows a good agreement between the two. There is a max difference of 10% between the predicted heads and the experimental values, and this difference may be due to the loss equations for the losses used, which usually have uncertainties of 20% to 30%. So this shows that the equations that we have used are valid, and the calculation procedure is good enough to use for the candidate centrifugal pump. And finally, we list the conclusions of the paper. A theoretical procedure was used to predict the head of a centrifugal pump with jet fuel A1 as the operating fluid. The losses were modeled using empirical relations, and it was observed that the volute losses and fluid slippage were the major head loss contributors. The predicted head was compared with the results from the experimental test rig at the test center, and there was a good agreement between the values with the maximum variation of 10. This showed that the validity of the calculation procedure and the choice of equations used was adequate to predict the pump head characteristics. Thank you very much.
Thank you, Anand.
Yes, sir.
Yeah. So you have done all the calculations, and you are getting 10% error. You're saying.
Yes.
So 10% acceptable or not acceptable or what?
We're doing this project with an organization, and their expectancy was 10 to 15%. And because of the loss calculation equations we have used, there'll always be uncertainties of 20 to 30%. And some of the other assumptions we have done is since the width of the blade varies over its length, we have taken the average of that. So that also comes into play when calculating the loss equations. So if you employ a purely theoretical approach, I think we should expect at least 10 to 15% error for this pump at least.
Okay. So from audience, anyone has any question or any clarification or anything? Audience, anyone can ask any question? Yeah, I think audience is not having any question or any discussion they want to do. Then yeah, so you finish your presentation. Thank you very much. We'll move to the next presentation.
Thank you.
Yeah, nice presentation.
Thank you.
Next presentation is Anant is done. Next is transient RANS solution approach for predicting rotodynamic coefficient of seals. And in this case, presentation will be done by Dhrumil Ganatra. Am I right?
Yes, sir. Good evening, sir.
Hey, good evening. Can you introduce a little bit about yourself and start presenting?
Sir, I am working as a scientific officer in Indira Gandhi Center, and I am involved in thermal hydraulic calculations for different subsystems of fast breeder reactors at IGCAR.
Okay, okay, okay. Yeah, please start presentation. Thank you.
Greetings, everyone. I am Dhrumil Ganatra, and topic for my presentation is transient RAN solution approach for predicting rotodynamic coefficients of seals. I'll cover the introduction, methodology used for simulations. In results and discussion, I will present the validation of the CFD model and influence of rotor eccentricity on rotodynamic coefficients, followed by conclusions and some important references. Seals are widely used in various turbo machinery for controlling leakage from high pressure regions to low pressure regions through rotor stator clearances. Although the primary objective of seals is to control leakage, response forces imparted by the seals on rotor have a very strong influence on rotodynamic stability of the machinery, and hence these seals play a crucial role in successful full load operation at high rotor speeds. Dynamic coefficients, namely direct stiffness, direct damping, cross-coupled stiffness, cross-coupled damping, and added mass components account for the forces generated by the seal's working fluid on rotodynamic components as per equation 1. The forces Fx and Fy are imparted by the seals are a function of stiffness, rotor position, damping, rotor velocity, added mass coefficients, and acceleration. The diagonal terms are called direct stiffness, direct damping, and direct inertia, and off diagonal terms are cross-coupled stiffness, cross-coupled damping, and cross-coupled inertia terms. This equation 1 will be further simplified, as we'll see, because for gas seals this contribution of inertia term will be negligible and will restrict our motion in x and y direction at a time for easing computational effort. Also, in practice, rotor is not perfectly concentric with setter, and there is always a minute eccentricity present in the rotor setter systems. This is because of manufacturing tolerances and assembly difficulties, particularly for long and slender turbo machinery. Eccentricity influences the rotodynamic coefficients and in turn its stability. Hence, the evaluation of rotodynamic coefficients for different eccentricities is critical for ensuring the stability of high-speed turbo machinery. If you have a 2 degree of freedom system where rotor is allowed to vibrate simultaneously in x and y directions, the combination of vibration motion in 2 directions can produce many different type of rotor whirling models. These three shown in figure 1 are some of the rotor whirling models that are commonly used. The straight line whirling, circular whirling orbit, or elliptical whirling orbit. Irrespective of the rotor whirling model that we use, whether it is one of these three or any other rotor whirling model, the rotodynamic coefficients that we finally get will remain same for a particular eccentricity ratio and excitation frequency. In order to reduce the computational time, a one directional straight line rotor whirling model is employed in this work, that is as shown in figure 2. The rotor center given by C is given a whirling motion, sinusoidal whirling motion around the seal's center O with using dynamic mesh smoothing method, and spin is given on the surface of the rotor using moving wall boundary condition. This is the x direction whirling and this is the y directional whirling. Now for our purpose, since we are using a straight line whirling rotor model, either whirling in x will be given or whirling in y will be given to reduce the computational effort. The del is the maximum amplitude that should be less than 10% of the seal clearance for the applicability of equation number 1, and omega is the angular frequency. For gas seals, contribution of inertia coefficients is negligible compared to damping and stiffness coefficients, so we get a simplified equation 4 from equation 1 when we restrict the motion of rotor to x direction and y direction at a time. First one is for x direction whirling, and second is for y direction whirling. This fx and fy on the left hand side are obtained from the transient CFD analysis, and x and x dot, that is the rotor position and rotor velocity, we already know as it is our excitation signal. So we now have a system of equations that we can use to find the rotodynamic coefficients through equation number 4. If eccentricity is not equals to 0, that means rotor is not perfectly concentric with stator. We require at least 2 simulations for each eccentricity ratio, one with whirling in x, another with whirling in y, to get all the 8 rotodynamic coefficients important for gas seals. Figure 3 shows the geometry of the experimental fully partitioned damper seal used for the simulations. Since this is a non-axisymmetric geometry, therefore a transient CFD method will require a full 360 computational model. Figure 4 shows the computational model and mesh of the FPDS used for simulations. Dynamic mesh smoothing algorithm, spring-based, was used for updating mesh after each time step for positioning of rotor at a prescribed location using equations that we already discussed. The solver used for this particular work is ANSYS Fluent. Validation of the model is done against the experimental results published in the open literature, and table 1 and 2 in the subsequent slides will show the operating conditions and the CFD setup. Equation 5 shows the x direction whirling, where del is 30 microns, as the test seal clearance is 0.3 mm in the reference, and frequency in the reference is given as 20 to 250 Hz. So here for validation of model, we have used 6 frequencies in these frequency range for validating the model. These are some of the geometrical parameters, operating conditions, and details of the CFD model used for the simulations. The CFD studies were carried out 120 Hz whirling frequency to study the influence of time step size. It was observed that the change in the direct stiffness and damping coefficient is less than 2% and 0.25% once the number of time steps per cycle are greater than 45. So it is ensured that at least 45 time steps are used per cycle for all the simulations. Also, studies were carried out using realizable K epsilon and K omega SST turbulence models. However, appreciable differences were not observed, and realizable K epsilon model was used for all the subsequent studies. Now, figure 5a shows the displacement of rotor from seal center. As you can see, it is this displacement is shown from the seal center because the eccentricity used for validating the model was 0. And so we can see that if we take the average of fx and fy that were obtained from the CFD simulations, these will add up to a mean of 0 because eccentricity is 0 for the validation case. And C effective is a combination of damping coefficient and decoupling, cross coupling stiffness coefficient. The variation of this we will see in the subsequent slide. Now, the figure 6 shows the comparison of CFD results with the experimental data. It can be observed that the coefficients obtained via CFD simulations agree well with the experimental data available in the literature. Now, influence of rotor eccentricity was studied by carrying out CFD simulations at different eccentricity ratios from 0 to 0.5. Now, whenever the eccentricity is greater than 0, as we discussed, 2 simulations are required for whirling in x and y. This eccentricity ratio is basically a ratio of rotor eccentricity to the seal radial clearance. For all the subsequent simulations, rotor eccentricity is assumed to be in x direction and its whirling frequency is taken as 120 Hz. This equation 7 and 8 shows the location of rotor center with respect to seal for a whirling in X direction and for whirling in Y direction with identical amplitude in X and Y each and 120 Hz frequency. Figure 7a shows the displacement of rotor from its eccentric position. This is from eccentric position and not seal center as the case for eccentricity 0. So if you see again the mean value of displacement is 0. This is because it is from eccentric position of 0.3 eccentricity ratio. So if we see that the forces that are obtained through CFD will not add up to a mean of 0 as did for the validation case we discussed. So here some finite forces will be present in the system for a positive eccentricity ratio. These figures are for eccentricity of 0.3. Now figure 8 shows the variation of rotordynamic coefficients with eccentricity ratio. It can be observed that the direct stiffness coefficient Kxx increases faster than Kyy and Kyx cross-coupled coefficient increases faster than Kxy with increasing eccentricity ratio. This is because whirling was given in X direction and Y direction, but eccentricity was always present in X direction. So Kxx and Kyx component increases faster than Kyy and Kxy respectively. However, if we see damping coefficients, although these coefficients increases with increasing eccentricity ratio and K and Cxx increases faster than Cyy and Cyx increases faster than Cxy, the increase is not that much stronger compared to stiffness coefficient over here. The coefficients increase with increasing eccentricity ratio, however. I'll summarize this presentation with conclusions. A transient RANS approach using dynamic mesh was utilized for evaluating rotordynamic coefficients of fully partitioned damper seal using 1D rotor whirling model. Validation of the CFD model is carried out against the experimental results published in literature. The magnitude and frequency dependence of predicted rotordynamic coefficients for the FPDS using whirling rotor model were found to be in good agreement with the experimental data. Simulations were carried out at 120 Hz whirling frequency to study the influence of static eccentricity of rotor on the rotordynamic characteristics. The magnitude of all rotordynamic coefficients increases with increasing static eccentricity of rotor. However, as compared to stiffness coefficients, damping coefficients are less dependent on the direction of whirling rotor for finite eccentricity present in the system. These are some of the important references used for the presentation. Thank you.
Okay, thank you, Drumil. So we have few minutes, 2-3 minutes.
Yes, sir.
Is there anyone in audience who can start discussing or asking question? No one is there in audience. Okay, so yeah, so then I'll ask some question. Which software you used or you coded it?
ANSYS Fluent.
ANSYS Fluent. Okay,
Yes.
so ANSYS Fluent module is aerodynamics.
Sorry, I'm not able to hear. Module you are asking?
In ANSYS Fluent, rotordynamics modeling is there, or you just put some user-defined function?
No, this user-defined function was used to give the profile or the dynamic mesh movement, sinusoidal movement.
Okay. 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 And meshing and everything is on like in ANSYS platform.
Yes, sir. Yes, sir.
Okay. Okay. So I think audience is audience. They don't have any question. So yeah, then you can close your presentation. Thank you very much. This is very nice work.
Thank you, sir. Thank
So we'll move towards to the next presentation. Presentation is which one? Performance improvement of Darius hydrokinetic turbine through design modification. Authors are Maitreyi, Pranav and Shravan. And the presenter is presenting.
Hello, am I audible?
Yeah. Yeah. I can hear. Who is presenting, please?
Abhishek. My name is Abhishek. I'm the president.
Abhishek.
Hello.
Yeah. I cannot hear. Who's presenting?
Now, my name is Abhishek, sir. Abhishek.
Abhishek is presenting. So can you introduce maybe one or two sentences and you can start presentation.
Yeah. The group consists of Abhishek, Maitreyi, Pranav, and Shravan. We are actually a group of bachelor mechanical students from Vellore Institute of Technology, and we did this project in IIT Chennai only under Dr. Dhiman Chatterjee. And the topic is improvement of Darius turbine by design modification. And we have compared various points and added some of our modifications and tested out the final results to see their performance.
Okay.
Wishing a good day to all. This presentation is for the proceedings of the 8th International and 47th National Conference on Fluid Mechanics and Fluid Power at IIT Guwahati. And the authors are Maitreyi Saini, Abhishek Kaimer, Pranav and Shravan Kumar. We are a group of mechanical engineering students from Vellore Institute of Technology, and the project was conducted at IIT Madras under Dr. Dhiman Chatterjee, and the topic is performance improvement of Darius hydrokinetic turbine through design modifications. And let's see what all the contents are.
And so, we will start by introducing our work, followed by the methodology we followed, and at last, we will conclude our observations and results. We know that in our ever-growing world, energy needs is constantly increasing. Thus, there is a constant shift towards sustainable energy technologies. India has many potential sites to harness hydropower, though the conventional turbines use potential energy accompanied with large construction and maintenance. While at the same time, a lot of energy upstream remain untapped, which has a lower velocity and without no head. And thus, the recent focus has shifted onto hydrokinetic turbines that use velocity of flowing water to generate electricity. And among the various hydrokinetic turbine technologies that is available, cross-flow turbine is suitable for riverine system and thus can operate under shallow water conditions also. And under cross-flow turbines, H-type Darius turbine is easy to design, install and has lower fabrication costs and thus was chosen for this project. And in this paper, 3 design modifications have been made to enhance the self-starting characteristics of the Darius rotor as well as the power output. Conventional braid profiles are used and modified to make a symmetric profile. And here we have given the diagram of a basic Darius rotor. The design parameters were selected in accordance to the various geometrical constraints and basic formulations related to the Darius type hydrokinetic turbine. And we have designed the setups in SolidWorks software. The 2 blade profiles which were considered include Pinaka 0021 and S3525, which were selected from other profiles based on our literature review and groundwork. And in this table, we can see the table 1 represents that of the basic rotor design towards which the other designs are compared, and all other 3 tables are different design modifications. Here, as per the table, you can see in the second design we have varied the chord length. The second design has 2 sub designs, and you can see the chord length respectively, which is given. And in the design 2 also we have varied the rotor radius as well as the chord length. And design 3, this set of values are considered, and Here we have taken the solidity as 0.5 and the number of blades is taken as 3. As stated in the parameter list, design 1 takes into account chord overlapping ratio for variations, which is this red line shown here divided by the chord length of the larger aerofoil. The second profile includes smoothing of the conventional S-blade profile edges for better aerodynamic designs. And the third design incorporates a pivoted flap structure where the length of the flap is 1/4 the total chord length and the gap in between the two structures is 1/12 of the total chord length. And the angle is considered from -30 to +30 degrees. Negative angle indicates that the flap is pointed towards the rotor center and positive angle indicates that the flap is pointed away from the rotor structure. Now, coming into the simulation setup and meshing. The setup includes a rotating domain around the dairies rotor to monitor the RPM of the rotor in accordance to the different TSR value considered. And the 2D simulations were made using ANSYS Fluent module. The transient fluent condition was used in the analysis along with a K and K epsilon realizable turbulence model with standard wall functions. The inlet velocity magnitude was taken to be 2 meters per second. The rotational velocity was assigned to the rotating domain based on the TSR. Now coming to the setup meshing. Inflation layers were used around the blade profiles with proper refinement to get proper results and variations as the water interacts with the blades, considering the boundary layer theory. Also, as we can see, the rotating domain has much finer mesh compared to the channel. This was done to improve the effectiveness of the stimulation and provide results at the same time. Coming to the result part of the presentation, here the CM values have been plotted against TSR values, and what we can observe is that it gives us a particular bell-shaped structure which is observed at all Darius rotors. All Darius rotors follow this similar trend, and thus here we can observe that the blade shape of design 2 is such that the resultant lift and drag force complement each other and yields better performance, and thus this rotor is suitable for higher RPM applications. And so in the graph we can see these two graphs corresponding to design 2, both subsections A and B of design 2, and this is the basic rotor and this one is the design 1, and thus design 1 has better performance due to low COR, which results in lower solidity and hence more drag force to start the rotor at low flow velocity conditions, and thus at lower TSR value design 1 is found to have an higher CM value than the other designs, and thus the application actually depends on the CM value required and the TSR value under which it can be operated. In the third design, you can observe from the graph that the 0 degree has the comparable CM value when compared to basic rotor. The brown graph is the basic rotor, and at the same time the 0 degree gives us a better CM value at a higher TSR. So based on the values in which the rotor is being used at higher TSR conditions, 0 degree as well as -10 degree shows promising results at a higher TSR value. So this can be employed at a better TSR values. Whereas all the positive angles doesn't show that much of a promising results, and thus negative inclination, which means the flap towards the rotor center, gives better output when compared to the other ones. Now, when we compare the power coefficient, that is Cp to TSR, we can observe for the first two designs that large C/over condition, solidity of the rotor increases, which results in reduction of rotor operating range, and hence rotor attains its peak Cp value at lower TSR values, which can be observed here. And thus, as it moves towards the increase in lift force, the rotor reaches its peak Cp value at a greater TSR level. And now when we look into the design 3, we can observe that the modified aegis rotor with a flap gives us a 5% increase at 0 degree and attains a Cp max value of 0.09 at TSR4. And thus the negative 10 degree as well as the 0 degree modified flaps gives us promising results when compared to the base rotor, which has been also found out. And by observing the velocity and pressure contours, we can observe that there is a velocity and pressure drop in the rotor vicinity, clearly indicating that the stream flow energy is being utilized by the rotor. Also, velocity and pressure varies prominently as the water flow past the blades. And thus, from this research, we can conclude that as the drag force on the blade profile increases, it attains a peak Cp at a lower TSR value as seen in the first design, whereas for the increment in lift force, rotor attains a peak Cp at a higher TSR value, which is seen in design 2. And for design 3, it can be seen that at negative 10 and 0 degree flap orientation, there is an enhance in the Cp value by 3% and 5% respectively. The pressure difference which is created across the blade profile as the water moves in the upstream, which results in the driving force of the rotor and helps it to rotate. The negative pressure areas creates a suction force. And also the low velocity areas generated in the vicinity of the rotor depicts that the kinetic energy of the water is extracted by the rotor. And thus, the present study which has been done would be useful to develop the prototype of improved hydrokinetic turbine having self-starting characteristic under different operative conditions. Here we have taken a scaled down model. A scaled up model can be used for all practical purposes. And thank you for the kind attention. Thank you.
Thank you, Abhishek. Can you hear?
Yes, sir. Yes, sir.
Okay.
I can.
Abhishek, yeah. So, is there in audience who can ask or discuss something on this topic or on his presentation? Audience. I think audience is not asking anything. So I'll ask. Okay. Yeah. Okay. So my network is a little bit poor, so I'm moving my computer. So Abhishek, can you tell me grid dependency test? Have you checked? Grid dependency.
Sir, yes. Sir, we have carried out the grid dependency test.
Okay. So and convergence check whether things are converged properly.
Yes, that convergence has been. It showed convergence, sir. It did show.
What is the criteria? I mean, only visual or any mathematical comparison is there?
There was visual criteria has been done, and since we had some restrictions regarding the down model, the same mathematical restrictions carried out.
Okay. So you are confident that your result is okay, and that can be used.
Yes, sir. Yes, sir. 100%.
Okay. So I think the audience is not having any question.
Okay.
We'll move to the next presentation. Thank you very much. Thank you, Abhishek. Abhishek and team. Thank you very much.
Yes. Thank
Our
you,
next
sir.
presentation is visualization of Kaplan turbine runner blade, a case study, and presenter is Atul S. Tumane. They have
Yes, sir,
some
I
more
am
authors
available.
also, but presentation will. Sorry?
Atul S. Tumani, I am available for you.
Yeah,
Am I
yeah,
audible,
Atul.
sir?
Yeah, yeah, I can hear you. So can you introduce
Yes,
yourself and
yes, sir.
start presentation?
Yes, sir.
Mm-hmm.
My name is Atul Sudhakar Tumani. I am
Mm.
a research scholar. I am doing my PhD from Professor Ram Institute of Technology, Banera, Amravati. And
Okay.
my research center it is Central Water Power Research Station, Khadakwasla, Pune, where I am doing my project work.
Mm.
Now, here my topic it is cannibalization of Kaplan turbine ML a case study. My paper ID it is 162.
Yeah, okay. Please start.
Hello, my name is Mr. Atul Estumani, research scholar. I am pursuing my PhD from Professor Ram Meghe Institute of Technology and Research, Barnera, near to Amravati, Maharashtra. Research station, that is Central Water Power Research Station, Khadakwasla, Pune, where I am doing my research. Guided by Dr. K. Kumar, Scientist C in CWPRS. About CWPRS, with the dawn of independence and launching of planned development of nation's water resources, CWPRS became the principal central agency to cater to the R&D needs of project in the field of water and energy resources development and waterborne transport. Today, CWPRS a part of Union Ministry of Water Resources and it is one of the foremost organization in the world in the field of hydraulics and allied research. CWPRS provides specialized services through physical and mathematical model studies in river training and flood control, hydraulic structures, harbors, coastal protection, foundation engineering, construction materials, pumps, turbines, ship dynamics, hydraulic design of bridges, environmental studies, earth sciences, and cooling water intakes. The study conducted by CWPRS are able to provide hydraulically sound and economical viable solution to various problems associated with projects on water resources, energy and waterborne transport including coastal and harbor engineering. So here about my topic it is cannibalization of Kaplan turbine runner blade a case study. Paper ID it is 162. Presenter myself, Mr. Atul Sumani. About introductory part, we know that energy it is prime factor in nation's economy and social growth also. With increasing environmental concerns, there is an active worldwide focus on energy generation through renewable energy sources. And due to these factors, India is looking towards energy generation through renewable energy sources, especially solar and wind. India has abundant hydropower potential of about 84,044 megawatt potential at 60% load factor, which will result in a total installed capacity of 1,48,701 megawatt based on probable average load factor. So technical capabilities of hydropower such as quick startup, black start, spinning reserve, voltage and frequency regulation are more suited to stabilize the dynamic grid. Operation and maintenance is the key area for development of hydropower. For example, due to siltation and erosion problem, every year Blade Runner replaces in Himalayan region hydropower station. Other maintenance issues are operation time of runner, noise and vibration, cavitation and pressure fluctuation. So that's why India has very large potential of hydropower generation but we know that maintenance issues are very severe in India. So, problem description if we see here, case study of frequent blade failure of Mahagenco unit 12 megawatt Dudhganga hydroelectric project. It is reported in CWPRS. And runner blades have been broken down twice in 2008 also in 2016 also since the commissioning of unit. It is 1999. On initial findings, the unit was developing a reasonable noise and vibration as compared to another unit. Secondly, the unit was getting cavitation where the stream of water bubbles used to disperse heavily on tail race section, and the unit power was fluctuating while connected to the grid. As you can see these are the blades of Kaplan turbine blade, and these are the broken blades from this blade only. Okay, so if we see the next part, we see some solution technique we have started. We had already completed, that is various templates have been prepared for operational range of governor control system of 11 degree to 33 degree blade angle position at idle and full load condition. Templates for blade opening at idle and full load positions are prepared to check the opening between the blades. And in the second figure we can see off-centric position of two blades which has caused the churning effect on the blade and subsequently developed the cascade effect on the blade. This has developed the heavy noise and vibration and cavitation also on the tail race section. As you can see from this diagram, first diagram indicate the various template and second diagram it is off-centric position. Okay, off-centric position of the two blade which has caused the churning effect on the blade and subsequent developed the cascade effect on the blade. About cannibalization, as we have given the topic name also from cannibalization. So cannibalization, it is generally used in Royal Navy and US Navy. Navy operates ships, submarine, aircraft, we already know, to meet its defense requirement. When the required parts are unavailable, then in that case what we do, the parts can be taken out from the other equipment in order to keep operational or maintenance schedule on track. This process it is cannibalization. So cannibalization be a necessary during the period of high intensity operation. Okay, so cannibalization also applied with resultant risk involved in the process. About cannibalization of runner blade. So hydro turbine unit capacity of 12 megawatt with an annual generation target of 27.5 million units. So unit had already lost its annual generation target. Why? Due to the frequent blade failure since commissioning. So the unit had incurred huge loss in revenue during the breakdown and downtime during the ordering and replacement of new runner unit by original equipment manufacturer. So the downtime loss during the process of approval it is very high. So on successful root cause analysis of frequent blade failure of Kaplan turbine unit, a novel approach of cannibalization of runner blade has been taught. So what we do here in this process, mild damaged previously breakdown blade were picked up for cannibalization, and we do TIG welding on the broken pieces. Okay. Next part, tungsten inert gas welding. What we do here, tungsten inert gas welding. We already know tungsten inert gas welding, it play major role in high quality welding for structural application. Careful attention has been paid to edge preparation, joint fit up and control of welding parameters etc. to weld the broken blade assemblies. After welding, die penetration testing and ultrasonic testing also carried out to validate the welding intact and non-presence of void. For precision welding, we do this. About assembling of turbine blades. On identifying the root cause of frequent blade failure, the off-centric position of two blades have been rectified by placing the sizing washer at the piston assembly of control mechanism. As we can see from figure number 3, there we can see blade with hub assembly and piston and washer assembly also. So the angle of individual blade angle and opening position are synchronized with governor control mechanism. The level of vibration measurement is periodically measured and the reading at the various point it is below upper limit of it 4.5 mm per second as per ISO 10816. The unit have been generating the year target of 27 mega unit each year during the operation cycle during 2017-18 and 18-19 respectively. So the unit is exploited for operation on generation mode till to date with the cannibalized bed. So we can see that the unit is exploited for operation on generation mode till to date with cannibalized blade. Still it is in working condition. So galvanized thinning of blade during the operation. During routine inspection of the turbine unit after running for a year with cannibalized blade, new hairline crack have been appeared on the new non-welded blade. We can see this new hairline cracked here. This is 4 number blade. Sorry. So this is 4 number blade and this is second number blade. So why this occurs here? So on investigation of hairline cracks developed on the runner blade, the cause of crack was due to the galvanic thinning. The effect of galvanic thinning is due to two different materials such as welded material and original blade material in the solution of water form and electrical conductivity. This galvanic action causes the other blade to be weaker and develops the crack etc. on the blades. The blade have been re-welded with TIG welding in SITU and the unit has been put into operation. So in this way, finally we have completed our cannibalization process. About conclusion, the root cause of failure of blade on 12 megawatt Dudhganga hydropower plant was identified and the most effective method of cannibalization of old runner blade was undertaken in order to save huge generation loss due to downtime for the replacement of new blade, considering resultant risk involved in the safe operation and upkeep of unit under generation mode. The effect has been rectified by the proper positioning of spacing washer in the piston rod assembly. The huge saving of energy, about 100 million unit was generated till to date by the process of cannibalization. The resultant risk involving continuous close monitoring of healthy condition of turbine by noise and vibration. And still it is working condition. So that's why scheduled inspection and maintenance on the unit rewarded in avoiding of huge generation loss due to catastrophic failure of the turbine. So in this way, finally we have concluded our presentation part here and still it is in working condition. This 12 megawatt Dudhganga hydropower plant unit, it is in working condition using this cannibalization process. So thank you very much.
Thank you, Atul. Audience, do you have any question or discussion here? Audience, no one is asking any question. Very good audience. So anyway, I have some question. I have only one question. So cannibalization, whatever technique you are saying, whether globally the same technique is used or you are only using?
No, actually it is not used globally generally because for this type of process, that TIG welding process, still that type of cannibalization process, still it is not working in hydropower units. But if we use this type of technique, so it will be better for downtime loss also, because downtime loss will be very high generally in hydropower units, generally in Himalayan region also, where the filtration and erosion problem is high. Because every year we have to replace this blade and it will something 5 crore cost for blade. So it is very high cost. So any replacement is also very lengthy process. So that's why it will get benefit if we use cannibalization process.
Okay. Okay, Atul, thank you very much. Very nice presentation. We'll move to the next presentation, next and last one. Okay. Last presentation will a pilot study of retrieving energy potential during minimum discharge through irrigation dependent hydropower plant, right? And presenter Maya Kurlekar. Am I right?
Yes, good evening, sir. Good evening,
Yeah,
sir.
yeah,
Am I
please.
audible? Just a check.
Yeah, I can hear you. Please
Yeah.
introduce yourself and present.
Yes, sir. Yes, sir. Yes, thank you so much, sir. This is Maya Kurulekar, a research scholar. I'm working as an assistant professor in Vishwakarma University, Pune. Earlier presenter, he had already oriented about you, about CW and PRS. So I'm also working under the guidance of Dr. K. Kumar, scientist CW PRS, and Dr. Shardul Doser, Vishwakarma Institute of Information Technology, Pune. So I would request the organizers to move on to the presentation.
A very good evening to the respected chair, academicians and students present over here. I, Mrs. Maya Kurulekar, presenting a pilot study on retrieving energy potentials during minimum discharge through irrigation-dependent hydropower plants, working under the guidance of Dr. K. Kumar, Scientist C, Central Water and Power Research Station, Pune, Dr. Shardul Joshi, Professor at Vishwakarma Institute of Information Technology, Pune. The growth of any nation is driven by energy, and now in the era of requirement of sustainable environment, clean and green energy is the prime focus. Thus, energy generated by renewable energy resources is the active focus today. Solar, wind, geomass, and hydropower are considered to be renewable energy sources. Hydropower contributes almost 16 to 19% of world's energy production and accounts for 71% of renewable energy in the world. In comparison to solar and wind power, the hydropower has high capacity factor of around 50%. We know energy requirement is dynamic in nature. Therefore, the operational and functional capabilities of any type of power plant should be in line with this dynamism. Here, the hydropower add additional feature to adapt these dynamic changes and requirement. Any new hydropower plant has to be dealt with many parameters like water availability at that location, rearrangement of population over there, effect on ecosystem, and so on. All these limitations turned our focus to small hydropower plant and how existing system can be improved. With this knowledge, the problem was identified to work on such small hydropower plant and improvement in existing system of power plant. Any multi-purpose reservoir is designed in consideration with requirement of the respective area where it is located. Irrigation-based storage reservoir is primarily focusing on allocating water for irrigation and then for power generation. For social requirements, benefits, it is very important to balance the water release towards irrigation and power generation. In such case of irrigation-based power plant, the units generally employs the type of reaction turbine to take the advantage of low or medium head and high discharge. As we all know, during monsoon, the requirement of water is taken care by nature, and thus the release of water towards irrigation is less. During this lower release of water, the power units could not able to tap the energy due to restriction on operational limitations, of course, because they may experience cavitation and then leads to noise, vibration, and following disastrous failure of units. In this graph, we can see that under low flow condition, the efficiency or the behavior of different turbine is decreasing. Most of the irrigation dependent power plant are type of reaction turbine of Kaplan, which are operated under low head and high head discharge. From the graph, it can be seen that if the Kaplan turbines are operated at part flow conditions, the efficiency falls drastically due to cavitation and creates noise and vibration. And this is where the circumstances leads to reasonable loss of power generation, which is universal in nature. Therefore, this paper emphasizes on utilizing untapped energy during lower water release in irrigation dependent power plant. We have selected the case study of Dhoom Dam of district Satara located in of Maharashtra state. The figure shows the layout of canal of Dhoom power generation. This is a power plant of capacity 2 megawatt, which is having 2 units, each unit of 1 megawatt. We have even obtained the capacity factor with the available data from the commissioning of the year, that is from 91-92 to 2017-18, and the capacity factor is observed to be 0.3150, nothing but 31%. Even the average power generated by both the units from 91 to 2017 is observed to be 5.519 million units per year, which is against the annual target given to the the hydropower plant as 10.56 million units per year. The average energy loss due to the low discharge is found out to be 2.6919 million units per year, converting the same power loss in kilowatt observed to be or arrived at 311.56 kilowatt. So this much power actually we can generate. Thus, we propose the methodology to retrieve the power from minimal discharge as well. First, close conduit inline axial turbine in the existing suction pressure tapping line from the penstock, which is used for auxiliary circulating pumps. Second, arrangement of split type Kaplan or propeller turbine installed in the structure of irrigation gates. Thirdly, arrangement of very low head Kaplan turbine in the canal in which the energy developed through the water release from the turbine and the release through irrigation gates. This is during minimal discharge. In the photo, you can see that the typical reaction type of turbine provided with number of tappings. The existing power plant is having the penstock of dia 2500 mm and the circulating pumps of capacity 15 kilowatt each to give services to the auxiliary ends. In the solution, in the proposed solution, we have mentioned that the inline axial flow propeller turbine that can be installed on the modified piping of diameter 500 mm to generate the power of 150 kilowatt with design head of 14 meter, 1.3 cubic meter per second of flow, and with the efficiency of 80 to 85%. In the slide, as you can see that the existing layout of power plant in the figure 4 and in figure 5, we can see that in what way the modifications are suggested. So here what you can see that the modified piping of diameter 500 mm having inline turbine. This is the typical photo of inline axial flow propeller turbine. Secondly, we have given the solution to reduce the water loss and generate additional power by using the prefabricated frame replacing existing gate. it has units like generator, turbine in itself, so that during lower release of water, the effective utilization of water can be made without wasting. On third part, we have given the solution of using very low head turbine, that is VLH turbine, which is having the range of flow from 10 to 30 meter per second and the output range from 100 to 500 kilowatt. At the end, we could say that the proper allocation of water to irrigation or to any purpose, that is very important. Even the optimal utilization of water for power generation is another important concern. In this paper, the methods suggested that will definitely allow to run the power plant during low and high discharge conditions. During low discharge condition, each power unit that would able to generate 150 kilowatt, that is both the units that would generate 300 kilowatt in combination, and during high discharge condition it is mean for 2 megawatt, so additionally it can generate 300 kilowatt, so in total 2.3 megawatt. Definitely such type of solution would serve or would serve the best energy recovery model in case of irrigation based hydropower plant. The structural modeling and analysis of split type embodiment with existing gate assembly is considered for the future study.
Okay, thank you. Thank you, Maya.
Thank you, sir.
Yeah, we have a few minutes, 3-4 minutes time for discussion on this paper.
Yeah.
Is there anyone from audience can ask question? Audience, please. Okay, as usual, audience is not asking any question. Good for the presenter, especially for the students. Okay, they do not get any question.
Okay.
Yeah, so now I have question.
Yes, sir.
Your data is from practical field, right?
Yes, sir.
Okay, so the same concept is being copied by others, or it will be copied, or it is just basic idea?
This is basic idea, sir. This is we are yes. This is we are yet to test, so we have given the solution.
Okay.
Yeah.
So okay, what is the opinion for the engineers or other people who are working in the field? They are thinking this is viable. I mean.
Yes, sir. Yes, sir. When we have visited the power plant, the case study which I have mentioned, so they actually think that this would be viable.
Okay.
Yeah.
Okay. Thank you, Maya. I think no one is asking question.
Thank you, sir.
Yeah, then I'll close this session. Thank you all the presenters and all the audience. And all the presentations were very nice, and maybe because of recorded video, everything was smoothly running. Because every time whenever we conduct any conference or anything, even class also, we face lots of difficulty in internet. But here everything was smooth actually. It was very nice. Yeah, papers were also very nice. Thank you very much to everyone.
Thank you, sir.
We thank Professor Abdul Samad for chairing this session. So from here we are done with the session 6 and second day of FMFP 2020. Tomorrow, day 3, we will begin with the keynote lecture at 9 a.m. and the presentation session will start from 9:30.
Yeah. Okay.
Okay.
Yeah.
Good night, everyone.
Okay. Thank you. Bye.